Okay, we're live on YouTube. Great. And
Nice.
the webinar has now started, and we should start to see attendees rolling in a minute. Great. All right. Good morning, good afternoon, good evening. Welcome to the second day. Well, actually, officially for me, it's the third day now of NeuroMatch 3.0. My name is Medina Sarvastani. I'm a postdoc at Max Planck, Florida, and I'm your on-camera host. And in the background, we have Amit Rahane, who's handling the tech session, and he'll be your off-camera host. And before we get started, and our second speaker also joins, I just wanted to tell you a little bit about the format of the session and give you just a few reminders. So with these interactive sessions, we're really doing an experiment in trying to translate the in-person poster sessions at conferences to the virtual format. And I think most of you know that this is a little bit more challenging than translating a traditional talk. So each speaker will have 5 to 10 minutes, somewhere in that period, to give a broad overview of their research. And then we'll open up for Q&A with the hosts, the other panelists, the audience, and just have sort of a more casual conversation. You can put your questions in the Q&A and please upvote each other's questions. And also feel very free to use the chat to ask for clarification, to post papers, to put comments. This is all your space for interaction. Let's see. Great, and I should also note that our first speaker had to cancel, unfortunately, due to sickness, and we all understand that. Hopefully she can join us next year. So we'll start with our first speaker, Kazuya Horibe, who is a PhD student in theoretical biology at Osaka University, and he's going to tell us about the surface geometry of the cerebral cortex, and how it induces topological changes of cortical traveling waves. Kazuya, take it away.
Okay, thank you for introducing. So I will share the screen. Can you see my screen?
Yep, that looks good. Okay.
So yeah, firstly, I will briefly explain my research about the numerical simulation on the cerebral cortex neural activity. So the background is we have 2 ways of the signal propagation in the brain. The one is the nerve fiber. The second is the pattern dynamics on the cerebral cortex. For example, this is a mouse of the cerebral cortex, and the neural activity propagate like a traveling wave. And also, this is also the mouse cerebral cortex, whole cerebral cortex, and this neural activity propagate like the spot pattern. So the traveling direction and speed could encode the brain function. So we are interested in the phenomena. And this is a peak brain. This is a more complicated geometry. So this is interesting phenomena. This is also the neural propagate on the cerebral cortex, and the neural traveling wave influenced to the geometry. So we want to understand how surface geometry controls the signal propagation, so using the mathematical model. The setup, the mathematical model is here. We use a very famous neural activity model, Fitzhugh-Nagumo. We use the traveling wave solution, and we also set the very simple geometry, like a 2-dimensional Gaussian function. So we can add it, and use multiple Gaussian function. We can estimate the very complicated the geometry like the human brain. So this is a demonstration with using the real human brain. So the black line is a neural dynamics wave, and firstly we propagate the one traveling wave, but after that like the front of the brain, the traveling wave, the split and multiple dynamics. So we want to understand how does the surface geometry control the direction and the topology of the traveling wave. So this is too difficult to understand the geometry of the surface. So we simplify the very geometry. So we set up the three condition of the surface. So this first is a flat surface. So this is just to propagate the traveling wave. And the gently curved surface is like the transiently the bended to the traveling wave, but this is return the original shape. And the sharp curved surface is the traveling wave, the split like this here, and make to the independent wave. So the wave has been, the wave front collision is a precursor to that particle chain. So we try to understand geometrically. So we use geodesic equation. This is the shortest path on the curved surface. And we compare the wave front of the traveling wave and solution with the shortest path equation. And we can estimate we can guess the traveling wave of the shape using the shortest path. Yeah. Yeah, this result means only geometrical structure we can guess the direction, the speed of the traveling wave. So using the more complicated structure geometry, we will expect the traveling wave on the real surface geometry of the cerebral cortex. And after that, we try to understand the influence between the neural activity and the geometry during the brain morphology, like a very early stage in the brain. Yeah, that's all.
Okay, great. Yeah, I have a couple questions.
Yeah.
So this must influence cortical wiring, right?
Yeah.
How do you think about that?
Yeah, exactly. I think that for example, this is a human brain, the very early development stage. In this case, in this region, the neural fiber is a very not matured. So most neural activity occurred on the cerebral cortex and make gyri. So in the very early development stage, this surface neural activity is dominant. So after that, we should think about the neural connectivity.
I see. Okay, and then can you go back a few slides to where you had the bifurcation from the very sharp peak?
Yeah, this one.
Yeah. So where the pattern actually bifurcates and splits off, they go two different directions. I mean, that seems like that would have functional consequences. Like, for instance, I'm a visual scientist, so if these traveling waves are in response to a visual stimulus in the world, then it seems like now you have two very different regions of the brain representing the same point in the visual world. But I guess you might say that this sort of bifurcation would then induce wiring between these areas, or how do you think about this?
Yep. Yeah, you mean the biological function of the splitting, right? Yeah, exactly. You said the visual information is the most understandable example, I think. So you can imagine the visual cortex, we can propagate to the same information to the region of the cerebral cortex is one idea. Yeah, actually we also try to find the phenomena which affect to the split, but I haven't found yet. So yeah, visual information processing is I think the most reaching problem.
I see. And do you think that in your simulations, the wave propagation and these three surfaces, are they equally efficient or energetically cheap? So I'm thinking, for instance, if these wave fronts were seizure activity or something, is it correct for me to think that these sharp curved surfaces would result in smaller propagation or slow down propagation?
Yeah, you mean does this way does the velocity of the wave is change or not?
Yeah.
Okay, I see. Yeah, in this simulation is speed is constant.
Right.
But the real brain, I think there is a different density of the neuron, and so that the velocity the change during the each region, I think. So yeah, in this the numerical simulation is a very primitive result, but if we apply the real data, we should change the velocity each region. I think. This paper discuss the changing velocity each region on the mouse cerebral cortex.
Okay, cool. And is it feasible to think that you could eventually get to a point where you can, so now we have 3D atlases of several brains. We of course have it for the mouse, but the mouse brain doesn't really have too many gyri. But when we get to the point where we have good 3D scans of, let's say, pig brains or ferret brains that have folds, then you could take that 3D model and use your model to really predict wavefront propagation patterns all across the network.
Yeah, I think so. And actually, recently a lot of the species of the brain surface of the geometry of the surface can get the 3D structure. So yeah, we can try to propagate the several species brain, and we can yeah.
I see. This seems like this would have immediate application for migraine traveling waves, epileptic traveling waves. Okay.
Yeah.
That's very interesting work. Thank you. We have no, I think we should move on. Thank you, Kazuya.
Yeah, thank you so much.
Yeah. Okay. Great. Let me pull up my notes. Our next speaker is Xiaoxuan Wang from Shenzhen University, and she's going to tell us whether and how resource sharing resists scarcity, behavioral neuroimaging, and endocrinological findings. And you might notice that this is a very different direction from Kazuya's talk, but this is the result of the search algorithm. Some talks, because of our different time zones, can be grouped together, and sometimes we get to learn very different topics, which can be fun. Okay, Xiaoxuan, take it away, please.
Yeah, thank you for introduction. My name is Xiaoxuan. I'm master of Shenzhen University, and this is my tutor. Her name is Van K. She's an expert in empathy and neural decision making. And today I want to briefly introduce a word from our group. The project title is Whether and How Resource Sharing Resists Scarcity. And we think the cognitive empathy play an important role in people resource sharing behavior. And in our daily life, we are sometimes in risk and we will be facing limited resources. According to the hypothesis of rational man, people should, as possible as collecting resources for themselves, regardless of other people's needs. But sometimes you will find other people, some people are still willing to helping others, even sacrifice their resources and their survival chance. So we are interested in when and why resources sharing persists under shortage. We think this finding on this issue may be enrich the knowledge about how to promote people human prosociality. So we developed, there is some briefly background, is some correlation brain region. So we develop a novel paradigm. We ask participants to decide how to allocate their relieving resources. Before this man is the true participant. He will come to our experiment and he will know his, and we will call him decider. We will tell him that he will receive 8 seconds unpleasant noises. Otherwise, meanwhile, his or her confederate 8 seconds noises too. So, but we will give this decider a relieving resources. This resources can use to balance the noises time. The resources have different amounts. So we ask the decider to decide whether he wants to share these resources to his confederate. Because we're interested in the neural mechanism of the sharing behavior. So we put the decider into a fMRI scanner and he will finish the task in the scanner. This is the process that he or she should finish. After he finishes his choice, we will ask them to fulfill the questionnaire of kinetic and affective empathy. We have 2 behavior indicators. One we call sharing rate. This means we calculate the percentage, how much the decider give other people. And other indicator we call changing rate. This changing rate will show the the ability of the sharing behavior. The calculated is the sharing rate in sufficient condition minus sharing rate in insufficient condition. Because we are still working on the data analysis, so we just showed some simple results that is in the behavior level, the safer, the more sharing. And we found that the kinetic emphasis play an important role in resource sharing behaviors. Just the different level kinetic empathy will engage different level the stabilities of people resource sharing behavior. And we use the GLM model to find the activation in two brain region. One is called the TPJ. The TPJ, we used to think that he is used to inferring the intention of others. And another brain region is called inferior occipital gyrus. And these two brain region is correlation to resource sharing behavior. But the further data analysis we are still working on, so I just show this today. Thank you.
All right, that's very interesting. Thank you. I have a few questions in the few remaining minutes we have. What was the gender of the participants, of the deciders, and does that matter?
Yes. 25 female, 25 male.
And their results are the same regardless of gender?
Oh, we didn't. We just calculate the total average behavior data, but do not separate the gender.
I see.
So, I think maybe we can try it.
Yeah, that would be interesting. And just a very broad question. This idea that because humans have empathy, this produces sharing behavior even though when resources are scarce. Is that unique to humans, or is there evidence of other animals sharing resources in scarcity?
Yes, but we always do humans experiment.
Yeah, of course, that's the best case.
Yes.
But do you think? But do other animals also do this behavior?
Yes,
Yeah,
we can
okay.
see in animals like monkey or dolphins or elephants. You can see this, but I haven't read some about research.
That's really interesting. And I mean, if you can study anything in human, you should just do that. Yeah. Okay. Great. What's next in this research?
Next.
Yeah. Can you tell us what the next steps are? What's the future work here?
Oh, the future work.
Yeah.
In this paradigm, you can see people should know what risks they will be facing. So I just finished a data collection is people decide how to allocate their relieving resource under uncertainty. They do not know what risks they will be faced. He just receives some information and then he will just know that he maybe will be in risk or maybe will be in safe, and then we do ask him to allocate these resources against.
I see. That's very interesting. Okay, great. If there are no questions from the audience or panelists.
I have kind of a question.
Yeah, please.
Do you think the behavior would be different if there are multiple deciders?
Can you say again? I can clear you.
Do you think the behavior would be different if there are multiple deciders?
Yes. Let me see something. Sorry, can you pardon?
No worries.
I mean, you mean there are multiple people with resources that can distribute them.
Mm-hmm.
I see, cool.
Can you type? I cannot hear clear.
Yeah, it's Eden actually just put it in the chat. Thank you, Eden.
Oh yeah, thanks.
Sorry, let me find the chat. Can you tell me how to open the chat?
Yeah, Ami, do you know what it looks like on her? So on the bottom panel?
Oh, I found this.
Yeah.
Yeah, I got it.
Yes. Is there?
It's not that important if it's.
We have a minute. It's okay.
Okay.
Yeah.
There are multiple. Can you clarify the questions? I'm not very.
So in this regime, you have one person that decides resource allocation, and you have one person that accepts the resources. Correct?
Yes.
So what were to happen if you had multiple people assigning different or even the same sets of resources?
We recruit 55 people. They not all behave the same behavior. There are they will be different by specific persons, but we calculate the average behavior in the human.
Okay.
Sorry, I don't know.
No, it's okay. Okay, great. So
the behavior sure will be different in different people, but there is a tendency in the whole human brain.
Do people tend to be more generous if they are making a decision together?
We don't have multiple people come to our experience times.
I see. What would be your guess? What would be your hypothesis? Would people be more selfish or more generous if, let's say, 3 people decide together?
No, every time we recruit one person to do the jobs.
Okay.
So we don't have a group of people together in the same time to finish the task. I think we can try to do this work in the future.
Yeah. I guess it is hard to get multiple people in the same scanner.
Yes.
Yeah. All right. Thank you. It looks like that's all the questions. Great. Thank you so much, Xiaoxuan, and thank you to our first speaker, Kazuya, and to the panel or to the attendees. And I hope you guys enjoy the rest of Neuromatch conference, and also the recording for both of these talks will be on YouTube. You can find the link on the public calendar. And have a good rest of your day. And thanks to Ami for running a smooth technical session. All right, bye.
Thank you.
Bye.
Thank you.
Bye.
There are still a lot of people putting a lot of effort in doing fundamental like data gathering, and which is okay, but there's a lot of data out there which needs to be analyzed and understood better. So I am drawing from different branches of neuroscience. I'm looking at what is going in that direction and analyzing. It is by all means not trivial to do systemic reviews and meta-analysis because there are issues with the methodologies whereby even the studies from which we draw data from need to be fairly selected and not biased. But, that's a different issue. So this is broadly what I'm doing. So there are some old theories and open questions. I see there are other talks related to this topic in the session. So I will defer to them to go in more depth, but very quickly, volition versus agency. They are also called incompatibilists versus compatibilists, and they all go back to a study by Libet in 1983, which is going to be presented in more detail. And a lot of open questions still: what determines free will? What is free will, and where does it fit in neurocognition, and how does it manifest? And a lot more questions. So the studies of reference are the classical Libet studies, which identified what is called the Bereitschaft potential, where type 1 and type 2 decisions were used to determine that some free will is actually an appearance of some kind of other decision made a priori by the brain. And there has been after Libet study, there have been a lot of studies which replicated and validated those studies. And now we can look back and say, maybe this was some kind of herd behavior which needs to be investigated further also by neuroscience. So, and there is a lot of what I call free will deniers which have followed Libet. Now we have to thank, I think it's called Schurger, is it, and Dahin. There's been some, apparently Mr. Schurger or Dr. Schurger looked at this Bereitschaft potential again in the light of new data, and he kind of started reconsidering it. There is a link to the paper. And more recently, there's been some analysis of these new studies, volition and the brain. And then I have been lucky to read about Lavata's work, and there is a lot of interesting work coming out for which we are thankful. So I think the most important of these findings, the most important which I managed to find and to look at, are we have been able to identify metacognition, and metacognition manifests as a kind of signal that precedes decisions. There are some studies which I list showing that metacognition is just one of the areas of research which relates very closely to free will. So we may not be able to observe free will itself because we don't know how to define it, so we cannot observe it, but we can observe decision-making, metacognition, and other dynamics which are related to free will. So we can start getting close to free will. And what can we see? As far as I understand from reading the work of my colleagues, is we can see that there are common activation patterns and possible overlap of indicators and changes in certain biomarkers. So far, what I have been able to draw, the conclusions that I can draw from looking at this work is that there is a system level activity. Now, I read and I learn from Michael Fox, who is one of the proponents of the network brain. I propose that I look at this, rather than a network, in addition to a network level, I see this what I call the system level, which I myself trying to identify and understand. But ultimately, it is the phenomenon of free will cannot be detected or attributed to a single activity of a single region. This is also true about other phenomena of the brain that we are not analyzing, but in this case, it's applicable to free will. So that metacognition and decision-making are very closely related to free will. So we need to start looking at the data that is emerging from this research in this field. So my work is theoretical because experimental, it's very delicate and very complicated. So we do need theories and we need to develop theories, because without the theories, we cannot justify the request for funding for the experiment. So when we are looking for equipment and want to do some research, they say, yeah, but then if the theory is limits, then, I'm not going to get the support from the research funding agencies. Many of the challenges are applicable to neuroscience as a whole, not just to free will, and are, in my experience so far, it's difficult to differentiate between healthy. So there is still work to be done in understanding whether this research applies or how it applies to healthy patients versus patients who have some conditions, because the definition of mental health itself is very feeble. So, even super healthy individuals may not have all the cognitive functions always available for testing when we need them. The resting state is, not easy to really rely on what we consider resting state. Randomness of decisions, there's certain non-random decisions, which are part of this experimentation protocol so far, are also very based on very big assumptions. And then, of course, the usual challenges of accessing imaging. There are no protocols, issues of privacy, ethics, finding the equipment, finding the recruit subjects, etc. So for me, it's very important to use and find existing data, which is already out there, which we can potentially leverage to provide more experimentation and support this new theory, the direction of this new theory, which, I am only relating, and I've seen this work emerge from a bunch of other directions that I'm looking at. So I don't know if I've spelled the lens correctly here. I don't know. I always can't remember if you put lens with the E or without, but basically, so what are the neurocorrelates? Actually, by the way, you will have noticed that I've changed the title. The title of the abstract was Neurocorrelates of Free Will, but I thought it was a bit pretentious. So the actual title now is the Free Will is coming back. But we can still say that what we are considering a neurocorrelate is like an indicator, and what we can observe, it really depends on the theory, and it depends on the technology available. So I'm particularly interested in learning more about the action potential, which I think could be related to the Barashov potential. I haven't found information about that. I like to see someone is doing this. The indicators, the biomarkers relating to free will that I've seen relevant so far are chemical, in terms of the blood oxygenation level dependent. And I think electric biomarkers are going to tell us a lot if we continue the EEG studies, maybe refine it further to understand more the correlation between different synaptic events. And I'm not looking at the genetics at all. So what will be the future work? Well, obviously this is very broad outline to consolidate the theory and actually to align the theory with other changes, paradigm shifts that we are seeing elsewhere in neuroscience and in science in general. We need new experimental protocols and establish new research collaborations. I would say, especially between those who have the data already, who have heaps of data in their databases, and those who have the new theories. So, can we, people with new theories, go and access your data? But to do that, we need your help, because the data is not readily usable without interpretation and understanding. And I think we need to divert resources to novel experiments. We need to move away from doing a lot of the funded research, which is completely pointless, which I sadly come across a lot, and we need to try to convince the funding agencies to put more money even towards the new theories, even if they're still, a bit controversial or maybe untested. So I have a very long list of references. only a few here, which was also partially reported in short without the full citation for indication. And I want to thank everyone who has encouraging me to pursue this line of work and accepting my abstract. How am I doing for time?
You have your last minute.
Okay, I'm done, but I'm finished.
Thank you.
Thank you for listening. Thank you.
We have a couple minutes for questions, and please share your questions in the question and answer panel for Paola, and we will briefly post her Twitter as well if you want to carry on asking questions to her. And Paola, one question I have in my mind is, how do you, for example, you are giving some examples throughout the decision-making processes from the neuroscience.
Yes.
How do you define, I mean, we know that free will is much general concept than decision-making, and it can involve in many different executive functioning. And I mean, could you please elaborate that how we can, I mean, is there a way to look at the quantify the free will in more general way instead of looking for one specific function?
This is part of the problems or challenges for this research, that really we don't have free will. We don't have, there is no way that free will can be defined because it's a very broad behavior. It's more like a guiding principle. And when we go and look at the experiments that have been done, and again, I'm very interested to see what my other presenting colleagues have, the experiments, they have to be narrowed down to the point where their value in terms of free will, actually, what does it say about free will, is questionable, or it kind of reduces. So it depending, I've seen all sorts of experiments done, but the tapping of the fingers, which is Libet's original work, it's not significant of free will in any way. So I think that's a very good question. Thank you for that. And I think this is the first task on our to-do list. Let's define a set of behaviors that we can call free will, but they should be meaningful, really. Just tapping of the fingers is bits. It was okay 40 years ago because we didn't have the technology that is available now. But now that we can look directly into almost real time, we need to set out, write out the experimental protocols, and that itself is a very big job. So let me work on that.
Thank you very much. Thank you, Paola. Now we will move to our next speaker. He's Uri Maoz from Chapman University, UCLA, and Caltech. His lab specializes in volition, decision-making, and moral choice. He uses the combinations of empirical techniques and theoretical modeling to develop computational account of volitions, with an emphasis on the decision-making processes that lead to voluntary action and on the role of consciousness in such processes. Classical studies from mid-1980s has claimed that consciousness doesn't have a critical play causal role in action formation. Now he will challenge those claims, and his talk title is On Volition and Consciousness, Deliberate and Arbitrary Decision. Yep, it's yours. Uri, we can't hear you. Please unmute yourself.
Here we go. I think you can hear me now.
Yes.
Okay. Thank you very much. Thank you for inviting me for this talk. And yeah, thank you for Neuromatch for that. And yes, as you mentioned, this is the title of the talk, and let us start. Now, when we make decisions, if you're deliberating whether to raise your right hand or your left hand, there is an intuitive order of events that we think happens. The first thing that we feel happens is that we consciously decide which hand to raise, okay? And then after that thing causes us to raise our hand. That's maybe what we intuitively feel. So if we look at the intuitive order of events, we have the onset of the conscious decision, then there would be information that exists in the brain about perhaps the action, and then there would be movement onset. But the Libet experiment that Paola already mentioned potentially challenges that. So there are a few versions of it, but one version is people were asked to, whenever they have the urge to do so, raise their right hand or their left hand, and at the same time look at this dot that is rotating and just say where the dot was when they first had the urge to move. So at some point, they have an urge to move and they move, and maybe they say the dot was at, I don't know, 10. Now, at the same time, their EEG is recorded from their brain, and this thing called the readiness potential or Bereitschaftspotential is being recorded from their brain, and that seems to be some kind of precursor to voluntary action. So if we look at the order of events, we have movement onset here with this readiness potential here, and we can see that already somewhere here, the readiness potential is starting to be apparent. So this is perhaps where we could say, there seems to be some kind of preparation for action. However, people report having made the decision to move only here. So the Libet order of events seems to be different from the intuitive one, where there's information that exists in the brain about the action before people report the onset of the conscious decision to move. So what happens here? I mean, this is kind of a weird situation where you say, well, it seems that, there's information that exists in the brain. So maybe if a neuroscientist would record this in real time, then they could say, oh, the person is about to move, but the person does not yet know perhaps that they're about to move. And that's what got people puzzled. And this raised this idea that maybe the decision was made unconsciously. Now, this experiment was done in the mid 80s, and just to say, it has been replicated a few times, and I mean, we've done this as well, and I mean, this phenomenon does replicate. This experiment does replicate. But let's go a little bit into what's going on here. Let's look at the argument, the inference from the Libet experiment. So what did Libet find? Well, Libet found that the readiness potential precedes the reported decision onset. Now, Libet already concluded from that decisions in those experiments seem to be made unconsciously. And then further on, Libet and others have then said, well, maybe generally decisions are made unconsciously. Now, if generally decisions are made unconsciously, that's already interesting, because if decisions are really made unconsciously, then this leaves no role for consciousness in decision making. And that really challenges some social pillars like free will, moral responsibility, perhaps even legal responsibility, economical theories, and so on. However, we have to be a bit careful. Each one of these leaps rely on certain things. And I will just mention some of them. They rely on some other factors as well. As I mentioned before, the interesting bit is if you can go in and in real time say, the person is about to move, but the person maybe does not yet know, or the person is about to raise their right hand, but the person does not know that they're about to raise their right hand. So the interesting bit is if these decisions are decodable from the brain online and in real time. The second thing is, okay, this readiness potential or some other things that have been developed since, are they really an early predictive signal, or is it really that, so is it just maybe some kind of a bias, or is it really that the decision has been made? That's it, it's been determined. Now, if it's interesting, at least it's more interesting and more frightening, if you will, if it's really been determined. That's it. The decision has been made. The person is not aware of it. If it's just some kind of a bias, maybe it's not so interesting. Last but not least, these decisions in Libet experiments were just, okay, raise your right hand or your left hand for no reason and no purpose. But what about more general, does this generalize to deliberate decisions, to which university are you going to go to your decision on a life partner or things like that? These meaningful, big decisions, do they generalize to those? And so I will talk mainly about the third. I will just very briefly mention some work we've done earlier on about the first and the second of these factors. So are decisions decodable from brain activity online and in real time? Well, we investigated this using epilepsy patients, with the help of epilepsy patients who were implanted with electrodes for clinical purposes. And we created this real-time system that we played a version of rock, paper, scissors called matching pennies with them. And they supposedly they played against me, but in reality, they actually played against themselves, because we designed this real-time system that decoded their brain activity as it happened online and in real time, and we were able to decode quite well which hand they would raise. Again, I don't have that much time, but you can read more about this in this paper from some years back. So it seems that yes, decisions can be decoded from brain activity online and in real time. Now, what about this early prediction versus early determination? So here we collaborated with some other researchers, right, asking again, do the early prediction signals reflect early determination of the choice or just some kind of a bias? So we used, the task in humans would be a temporal discounting task, kind of like, do you want $1 now or $5 tomorrow? But we reanalyzed some monkey data that other people in the lab of Deo Lee at Yale collected. And monkeys don't care that much about money, but they do care about juice, apple juice. So do you want less apple juice now or more apple juice later? Now, the interesting thing for us, and again, very briefly here, is that we were able to find cells in the monkey's brain, in the DLPFC and ventral striatum and other regions that actually can predict where the monkey would have a preference to select, like a bias of some sort. And this bias came up before the monkeys even knew what's going to be on the left, what's going to be on the right, the big reward, small reward, or anything like that. So it's this pre-deliberation bias. I mean, we did some computational modeling work that, of course, I won't get into. But the bottom line was that these early predictive signals do not reflect determination. They just reflect some kind of a bias. And they come, again, even before the monkey can start deliberating. And again, more information can be found here. So this suggests that this early predictive signal, I mean, it's not the kind of direction that you would want for the Libet experiment, but it's maybe some kind of weak evidence. So let's focus on the last thing here. So do the Libet results generalize from arbitrary to deliberate decisions? And this is joint work with Liad Mudrik, Christoph Koch, and Gideon Yaffe. What we did was we asked people to rate how much they would like to donate $1,000 to different charities. Some of those were more like vanilla flavored kind of ones where people generally would like to donate. And others were more contentious ones, pro-life, pro-choice, pro-anti-guns, and so on. And we had people make deliberate decisions. So this, if you chose the Hunger Project over cancer research, then the Hunger Project would, that would determine a $1,000 donation to the Hunger Project, an actual donation. And some of those were hard because maybe these two for you were things that maybe it was something you rated close to each other, and this might have been easy because for you, this is an easy decision. Now, these were the deliberate decisions. We also had people make arbitrary decisions. And here, no matter what you chose, both got $500. So you could not affect the choice. So what happened here? Basically, behaviorally, we got what we expected. So these are reaction times in hard decisions and in easy decisions. And what we see is that deliberate decisions take longer to decide than arbitrary ones, as you'd expect, and harder decisions take longer to decide than easy ones. If we look at consistency with, in the beginning, how much you ranked the different ones. So if you look at the consistency in your choice, we can see that it's very high for deliberate decisions, especially for easy ones, and it's at chance, roughly at chance for arbitrary ones. Now, if you look at the neuroimaging, EEG in this case, you can see this is a subject by subject. Here you can see that some kind of downward trend for arbitrary decisions, but not for deliberate ones. And if you look on average, you can see a nice readiness potential for arbitrary decisions, but you do not see a readiness potential for deliberate ones. We had to run various controls that I won't go into, And then we also had some kind of drift diffusion model. But the bottom line was that these neural signals that were associated with arbitrary decisions just do not seem to generalize to deliberate decisions. So what I would say here is, I mean, if you think that deliberate results pose some kind of a threat to our notion of volition, so whatever threat that is, it does not seem to generalize to deliberate decisions. And I would say that we care more, again, about deliberate decisions. I mean, yes, you could say that you know, raising my right hand or my left hand is some form of freedom, but especially if you think about free will as that thing that enables moral responsibility, then, I mean, nobody's going to take you to court because you raised your right hand and not your left hand for no reason and for no purpose. But they would hold you, you know, praiseworthy or blameworthy if you saw a burning car and you ran to help, or you just kind of took a picture with your phone and posted it on Instagram or something like that. So these deliberate decisions, I would argue, are ones that we care more about. And our results here suggest that whatever the Libet findings threat to free will is, it doesn't seem to generalize to these deliberate decisions. And I would say that our results, therefore, put the onus on those that think that the Libet results do generalize to meaningful decisions to show that. Because honestly, for many years, it was just kind of assumed that arbitrary decisions would just generalize to deliberate ones. And if you want to know more about that, you can find it in this paper from last year. So I would say, at least in my opinion, that these results really kind of put a dent in this argument from the Libet experiment, going from the Libet findings to the general claim that decisions are made unconsciously. So in conclusion, I think that the Libet experiments do not provide compelling evidence that consciousness has no causal role in decision-making, especially not in meaningful decisions. And more generally, I would say that the neuroscience of volition should move, and actually is moving, beyond Libet, in particular, also looking at deliberate decisions. I want to end by just mentioning one thing. There is now a large ongoing project about how the brain enables conscious causal control of decisions and actions, really going towards the other question of not how consciousness is not related, but how consciousness is related to decisions and actions. And I mean, I lead this project, but there are a lot of people involved from all over the world, neuroscientists and philosophers. It's called the Neurophilosophy of Free Will Project, and you can find more information here at neurophil-freewill.org. And I would shamelessly say that we are seeking postdocs, PhD students, and research assistants. So please contact us if you're interested. And I would finish by acknowledging this work. Some of it was done at Caltech, some of it was done at UCLA, and much of it was done at Chapman. And I want to thank all those who have helped with all of this. So thank you very much.
Thank you, Uri. We have a very short time for one questions from our audience. Muhammad Amin Samipor is first saying thank you for your interesting talk. And he's asking, how could feelings affect the reaction time in decision? Could it be also specifically involved in arbitrary decision?
Feelings. So I think, I mean, first of all, I should say that I don't know of any specific studies that have looked at feelings. But in terms of reaction time, I mean, sorry, you're asking, okay, feelings and volition, I don't know of studies. Of course, people have looked a lot into the neuroscience of emotions. I would not be surprised, for instance, if your emotions would affect reaction time in the sense that if you're more angry, then maybe that you would respond more quickly. Maybe if you're sad, we know people tend to respond more slowly. So those kinds of things I would expect to see, but I don't know of a systematic study that have looked into those as part of volition. So these are speculative answers.
Thank you, Uri. We have another questions which we don't have time to answer it lively, but Uri will be around to answer it in the chat. And now we are going to move to our last speaker, and Jasmine Walter. Jasmine is doing her PhD under the supervision of Jennifer Wind and Thomas Andrein at Monash University. She explores the use of neural data to understand subjective experience in disorders of consciousness. Her talk titled, "What is it like to have a disorder of consciousness? Interpreting neural measures of conscious level." The stage is yours.
Cool, thank you very much for that introduction. So today I'm going to be speaking about disorders of consciousness, which are conditions that arise due to that leave people with significant impairments to wakefulness and consciousness. And we currently know very little about what conscious experience is like in these conditions. So neuroimaging-based assessments could eventually play a really important role in the evaluation of disorders of consciousness, but it's currently unclear what neural assessments of conscious level can tell us about consciousness in these patients. So today I'll talk about how considering a wider range of evidence, like where these neural assessments have been applied in other conscious states and clinical populations, may help to clarify their clinical value in evaluating patients with disorders of consciousness. So the traditional diagnostic model for disorders of consciousness involves breaking patients into the following categories based on bedside physical examination of their behaviour over time. So patients are diagnosed as being in a vegetative state if they display reflexive movements and eye opening, and in a minimally conscious state if on top of this they display behaviours thought to indicate consciousness, like localisation to painful stimuli, visual pursuit and command following. So these diagnostic categories are designed to separate conscious patients from unconscious ones, but these behavioural criteria actually have quite a high rate of misdiagnosis. And this was first shown when it was discovered that some vegetative state patients could show signs of conscious mental behaviour when given a task in an fMRI scanner. So when told to imagine playing tennis, the brain activity of this patient in the vegetative state was very similar to that observed in healthy controls, showing that she was able to willfully modulate her mental activity. And this finding suggested that consciousness was present in a subset of vegetative state patients who displayed no intentional physical behaviour. So although this task-based fMRI assessment can provide strong evidence for the presence of consciousness and sometimes for other cognitive capacities, it doesn't provide evidence for their absence. So there could be conscious patients who can't respond due to damage to the brain regions that might be involved in performing or comprehending the task, fluctuating levels of arousal, so whether the patients are asleep or awake, or a lack of ability or desire to participate. So an alternative strategy is to develop passive assessments of consciousness. So in this study, for example, a range of EEG measures were investigated in resting state data as possible indexes of conscious level. So a range of properties that might have an intrinsic correlation with the presence of consciousness or conscious level have been investigated as passive assessments. And because these assessments don't require participation from the patient, they could, in theory, have specificity about consciousness in all patients and not lead to any false negatives, unlike task-based paradigms. So in practice, there are a couple of challenges remaining in implementing these measures. So firstly, we don't really have a reliable ground truth about consciousness in these patients to evaluate these neural assessments. And this is because subjective reports are often really limited or completely inaccessible in disorders of consciousness. So these assessments are normally evaluated against behavioural diagnosis, which we already know tends to have quite a high error rate in identifying conscious patients. And secondly, it seems that consciousness isn't necessarily the kind of phenomenon that can be described by a single unidimensional property like the ones that have been proposed. So it's not clear that we've even been looking for the right form of ground truth to evaluate these assessments. There's a growing consensus that consciousness is multidimensional, meaning that it's made up of multiple properties that can vary independently. And this means that it might make more sense to represent consciousness in a spider plot like this, where possible dimensions like attentional control, semantic comprehension, and metacognition could vary independently to produce a wide range of qualitatively different conscious states. And if we do try to describe consciousness in terms of levels, we might be missing out on information that has a lot of clinical and ethical relevance. So if this is a more appropriate way of conceptualizing consciousness, but we know little about its qualitative nature in this sense in disorders of consciousness, how can we make progress in meaningfully interpreting unidimensional neural assessments in disorders of consciousness? So the strategy I'll discuss today involves looking at a broader range of conditions and conscious states where these passive neural measures have been applied. In most of the states I'll consider, we know a lot more about both the presence and subjective quality of conscious experience due to the greater availability of subjective reports. So I'm going to take measures of brain complexity as an example today. There are a range of different measures that are thought to quantify some aspect of the complexity of a signal, but despite adopting slightly differing definitions of complexity, these measures have all been found to more or less converge so far on the level of application to neural data. So I'll consider them as a whole for the rest of this presentation. So complexity is being applied quite widely to a range of conscious states, some of them occurring within individuals, some of them in clinical populations, but today I'll discuss some possible trends emerging in the intra-individual conscious states and set the clinical populations mostly to the side. So which dimensions of consciousness correlate with increased or decreased brain complexity? Improving our understanding of this relationship might clarify the clinical value of complexity-based assessments in the challenging case posed by disorders of consciousness. So there's quite a rich pool of evidence to draw from, which I've summarised in this table, which shows the states and conditions that have been found to have either higher or lower complexity on average than healthy waking states. And the middle column is where a further comparison was drawn within healthy waking consciousness, which itself isn't really a heterogeneous state in terms of complexity. Okay, so which qualitative features of consciousness might be common amongst high complexity states? So I've highlighted a few examples here. So the particular states I've chosen here on the right have higher complexity than their comparator state on the left. And all these states with relatively increased complexity also seem to have relatively reduced executive and cognitive control and reduced automatic constraints on thoughts, like affective and sensory salience. So attention isn't strongly guided in these states by either deliberate or automatic constraints. So the states with higher complexity seem to be characterized by a more diverse, associative, more frequently changing train of thought. And psychedelics, ketamine and REM dreaming all also seem to involve an increase in sensory richness, but it's less clear whether this is the case for mind wandering. And the waking states, at least with comparatively lower levels of complexity, are generally characterized also by a relatively greater degree of executive control and cognitive functioning. So in disorders of consciousness, complexity has always been found to be lower than in healthy waking controls. And the main two examples we find elsewhere for low brain complexity, apart from in clinical populations, are in non-REM sleep and anesthesia experiences. So for a long time, these states were presumed to be unconscious and are still sometimes used as a proxy for unconsciousness or very low conscious level to validate assessments of consciousness. But it's now known that conscious experiences can regularly occur in these states. So conscious states occurring during non-REM sleep are reported to be mundane and fragmented and less perceptually vivid than REM dreaming. And anesthesia awareness, which can occur in up to 30% of patients, has been reported to involve highly perceptually decoupled and fragmented experience. And there's also some evidence that executive function and meta-awareness might be more resistant to anesthesia than to natural sleep. So they might persist to some extent in certain low complexity states, but data about this remain very limited. So where do disorders of consciousness fit in here? So considering evidence in other conscious states suggests that increased brain complexity is probably more highly correlated with some dimensions of consciousness than with others, and that perhaps it isn't measuring conscious level in general, and this is probably also true of other unidimensional assessments of consciousness. But are disorders of consciousness more likely to have qualitative similarities with other low complexity states like non-REM sleep and anesthesia? So the extent to which we can draw inferences like this is still quite unclear. And there's also the additional question of how brain injury itself might affect these measures. So damaged tissue might reduce overall complexity and cortical activity, which has been found to be the case for other TBI patients, but it's far less clear what the effects on consciousness will be, and we'll probably see a lot of heterogeneity amongst DOC patients. Okay, so deepening our understanding of these different neurobiological and psychological factors affecting particular neural assessments in a broad range of states, especially those that might have parallels with disorders of consciousness, may refine our understanding of what they can tell us in cases where subjective reports are unavailable. So to come back now to the methodological issues I first mentioned. So firstly, in terms of the lack of reliable ground truth, so with further research, this indirect evidence may help to refine our interpretation of unidimensional neural assessments in disorders of consciousness and help to clarify their potential clinical role in the evaluation and management of these conditions. And second challenge, so the inability of unidimensional measures of consciousness to single-handedly capture all of the variants that we care about in these patients. So based on this broader evidence that we've considered about brain complexity, it seems that it might be more informative to study the precise dimensions of consciousness and cognition that might correlate with particular neural assessments rather than using them to draw any really general conclusions about conscious level or consciousness. And passive neural assessments of conscious level might have greater clinical value as part of a richer multimodal assessment paradigm for consciousness that considers a range of data sources about different conscious dimensions. So thank you very much for your attention, everyone. I'm happy to answer any questions.
That was a nice talk. Thank you, Jasmine. And we have some time for questions. And could you please elaborate for these illnesses we are mentioning here? They are quite complex. And the concept we are talking about, the consciousness, it's also very complex. And I find it quite hard to follow up how you can find some, even for the symptoms, it is changing person to person for these patients, how you can go into details to look at some notions, which is even we don't know for normal patients what it is, like consciousness or free will, and you are trying to do it. I'm just asking, could you please just elaborate for us how how to look at this concept in patients, which symptoms are changing basically individually for individual differences?
Yeah, I completely agree that it's a very complex problem that we're trying to address, and that the idea of having neural correlates of consciousness, that's already one of the biggest challenges or biggest mysteries that we still have in science. But I think, so the point I was sort of trying to make here is that this multidimensional sort of model of consciousness might allow us to move towards a more individualized way of assessing these patients rather than just breaking them into categories based on whether consciousness is present or not, even though that's also important. But yes, basically I agree, and I think it's going to be a big challenge to get more details about what consciousness is like in these states.
Mm-hmm.
But I think, by looking at learning what these measures are actually correlating with in healthy people, which is also not completely obvious, will be a good first step, both in healthy people and in clinical populations where we know a bit more about experience. That will be a good first step in sort of trying to make progress on this really difficult topic.
Yeah. Thank you very much, Jasmine. It was a really nice talk. And let's thank to all our speakers. And thank you again very much, Paola, Uri, Jasmine, for your beautiful talks. And
Uri,
many thanks
I'm sorry. Do we have time for Uri to ask one more question?
Since we don't have anyone after us, I think we have time for asking one more question.
Thank you. Jasmine, I'm just wondering, again, I might have misunderstood these, of course, quick talks, but it seems, and I think it's actually a strength of what you're doing, is that you're not tied down to any specific theory of consciousness, right? You're just kind of trying to to look at complexity measures and so on. I just wanted to basically to ask that and ask if that's intentional or this that you're not committing to any kind of theory of consciousness.
Yeah, thanks for the question. It's very intentional for this approach to be sort of theory agnostic, I guess. So, I mean, it's more just looking at correlations between different measures and different sort of phenotypic outputs we could be seeing. So yeah, I didn't really want to dive into ideas about what the actual neural constituents of consciousness might be. But yeah, I just took complexity as an example because that's one that's come up quite a bit and has had quite a lot of practical application. But I think there could be a whole range of different properties and that correlate with consciousness. And I also think that complexity could be a feature that correlates with consciousness according to quite a number of theories of consciousness as well. So it's agnostic in both those senses, I guess.
Okay, thank you very much.
Do you have any more questions? If not, again, let's thank all of our speakers for their beautiful talks, and many thanks to our audience for being very active and asking instructive questions. And I should also thank to Mariam to help us with the technical help at backend. I hope you enjoyed the sessions. I will enjoy the rest of the NeuroWatch conference. Thank you very much for everyone. With the technical help at backend. I hope you enjoyed the sessions. I will enjoy the rest of the NeuroWatch conference. Thank you very much for everyone.
Awesome. So the session is live on YouTube. I'll start broadcasting and letting people in the session now. Cool.
Perfect. Thank you, Aditya, for taking care of all the tech stuff.
Attendees are in.
Okay, attendees are starting to arrive. Okay, it's the hour, so we can start. So welcome everyone, both the speakers and the attendees, for this morning session. Well, morning for Europe, and I'm Alberto Antonietti from Blue Brain Project in Geneva, and I'm glad to be here to host this session. We have a free, wonderful talk. Very focused on a specific team, so the algorithm worked pretty well. So we will see 3 talks about the hippocampus and spatial navigation, and we will start with Xinglong Su. He's an assistant research fellow. He started his own lab at Academia Sinica in Taiwan. He used to work at the Janelia Research Campus, and he's enthusiastic about understanding how computations of neural circuits during behavior arise as a consequence of cellular and biophysical properties of individual neurons. So I will leave the floor to him, and if you have questions, please use the Q&A box, and I will read the question to the speaker. So please, thank you.
Hi everyone, my name is Xinglong Xu, and I'm an assistant research fellow at Academia Sinica in Taiwan. So today I'm very excited to briefly share 2 stories with you about cellular mechanisms for rapidly dynamic neural code in spatial navigation. I've been working on neurons for years, Even so, when I have a chance to take a step back and just look one neuron that I stem, I still feel stunned by the complexity that a single neuron can offer. Besides the morphology, there's a great variety of different ion channels with biophysical properties and their spatial gradients. And there are synaptic connectivity divided by local microcircuit architecture, molecular machineries, and so on. So one can hardly look at this complexity without asking what are they doing there. So as a neuroscientist, I'm totally fascinated by this question. And the question is whether there is some sort of causal link between the complexity of single neural integration and computation and a complex and dynamic circuit function during behavior. I'll put it in another way, how the properties of single neurons can explain the complex circuit function. So I'm particularly interested in the brain region, the dorsal part of the hippocampus. Hippocampus is very important for memory and spatial navigation. And these two functional aspects might be related as the memory being proposed as a form of navigation in abstract mental space. The idea of hippocampus as a spatial navigation system was born out of the discovery of a place cell. Here I show you a spatial firing map of a typical place cell, where the cell only fired more when the animal was near the bottom right corner of this oval-shaped environment. So that place is called a place field for this particular cell. For most of the hippocampal pyramidal neurons or a given environment, we know most of the cells are silent cells, and only a relatively small fraction of them are active place cells. However, these two functional identities are actually can rapidly interconvertible. So a very elegant study done by Abelis group a few years ago, they found that when they has an intracellular coding using patch clamp from hippocampal CA1 region, when they identify a single pyramidal neurons, which is a silent cell, they can inject current to the soma to produce a very small depolarization by just a few millivolts. They rapidly convert a function of a silent cell to an active place cell. The opposite was also true when they start with a native place cell. They can convert it to a silent cell by just a few millivolts small somatic hyperpolarization. So, but you might say, well, this is not surprising if that constant current just pushing the overall synaptic depolarization profile above or below the action potential threshold. But the most remarkable finding in the studies, they found that not only the spike is highly sensitive to the voltage, but the subthreshold membrane potential, the activities also have a very nonlinear dependence on the somatic membrane potential. So there must be some sort of magic ingredient here. So when you walk away, I hope I can deliver a view that a nonlinear single neuron property are very well positioned to mediate this kind of type of highly nonlinear response during behavior. We could possibly serve as a putative biological substrate for some sort of context-dependent neural representation. So the first story is the cellular mechanism for the phenomenon that I described, and the gist of the idea is that I can recapitulate or reproduce very quantitatively the phenomenon that observed in vivo by using acute brain slices, whole cell recording from the soma and weakly activating distal synapses with the stimulation pattern that mimic when an animal passes through a place field for a place cell over a time course of seconds long. And the parameter they can use to describe this highly sensitive response baseline VN relationship has a parameter that's nearly identical to what's observed in vivo, including the voltage sensitivity and the amplification ratio, etc. So I can use this strategy to perform very detailed mechanistic analysis, including pharmacology and biophysical analysis, such as compare the amplification mechanism in the soma versus in the dendrites. And as well as computational modeling, which I can quantitatively reproduce the amplification effect observed in vivo using biophysically realistic channel properties. So I can finally test the idea that's the hypothesis generated by these studies, and then use a half-fixed animal that perform virtual navigation. So once the animal learns to navigate in this oval-shaped spatial tuning according to animal's position. But if there are some sort of behavioral context or test engagement, they can deliver this very slow modulation to the system, they can, the modulator of single neuron excitability could engage this substratial gating of the sodium channel near the initial part of the axon. They can dramatically amplify the second long synaptic response, and therefore, like a toggle switch, turn on and off the neural representation of space. So now I only talk about this sodium channel property near the initial part of the axon, but we know there are all sorts of very rich diversity of ion channel and biophysical properties with a spatial gradient. If we put an intracellular recording in the dendrites, we can see this kind of or none or action potential-like events that can initiate in the dendrites and propagate to a certain part of the cell called dendritic spike, as demonstrated by this biophysically detailed computational model that I've established and constrained by many of my experimental data. So the idea, the line of thinking of the function of nonlinear local commutation is not only they participate in this moment-to-moment input-output transformation, but also due to their spatial proximity to the input, they are very effectively engaging a signaling pathway. They can produce long-lasting synaptic modification or synaptic plasticity by some sort of dendritic nonlinearity like dendritic calcium spike or plateau potential. So the second story is whether this dendritic nonlinearity can produce or support this context-dependent, highly nonlinear neural representation for the space. So consider this scenario. This is a picture of a corridor in Genelia. And on the two sides of the hallway, there are two bathrooms for different genders. But just 50 or 20 meters away, there are another hallway that look exactly identical, except that the spatial arrangement for this bathroom are exactly the opposite. So after a few mistakes, when I just started at Genelia, I realized I really have to learn some sort of context-dependent navigation strategy, which probably means I have to remember where I just came from before I enter the hallway, or look at a subtle size on the wall to know where to get to. So the question is, what kinds of cellular mechanism can support this context-dependent navigation, and what underlies the learning component? What support the learning component at a cellular level to acquire this context dependence? So this is a realization of task in our experiment, where the animal was trained to navigate a virtual T-maze. It recognized initial cues and passed through a region where there's no informative sensory or visual cues, and they have to turn left or right to collect the water reward according to the initial cues. But once the animal learned the task, it looks like this. It has to turn to the side direction where the side of the wall have the vertical stripe in the initial part of the maze. And in the delay, in the middle delay region where there's no informative cues, because of it's a VR, we can strictly control the kind of information the mouse can see. So for any differential neural activity observed for that region, it cannot simply be explained by a gross difference of the sensory inputs, or the visual input in this case. So this kind of spatial information has to exist somewhere in the brain. 20 years ago, from a few very beautiful studies, we know there are place field firing can strongly be modulated by the animal's travel trajectory. So therefore, whether the place cell can fire for or express its place field depending on whether the animal turns to the direction the animal turn in a given task, which is some sort of choice-related place cell firing. So the question here is whether the local nonlinear events were able to support this kind of very rapid and reversible context-dependent neural representation. So the short answer is yes. Once the animal learned the task, I start to patch a neuron from a dorsal CA1, and if the CA1 pyramidal cell is a silent cell, I deliver a very short current pulse when animal pass through a fixed region during the delay, but only applied to one trial type. And to treat this very large and short current pulses can trigger the calcium plateau potentials. If we start from a silent cell like the example shown here, and only trigger the plateau potential in one trial type, like the right turn trial here, but not the left turn trial, they can immediately induce, just within a few seconds, a very robust place cell firing that lasts throughout the recording session, but only in the trials in which the plateau potential was triggered, but not the other trial type. If we look at the firing frequency plotted as a function of ML's position, we see the firing field induced during the induction site has a very dramatic difference between the two trial types. If we look at the intracellular membrane potential, the synaptic depolarization also shows a very dramatic or very remarkable difference between the two trial types near the induction site after the induction. So, for the sake of time, I just want to give a very, very high level and very short summary, which is the effect of nonlinear local integration here seems to be drive the potentiation of synapse and therefore the support a manifestation of the bias selectivity to the combination of initial cue and the place. And what I don't have time to cover here is that the specific test engagement driven by learning seems to play an important role to determine whether the initial cues are meaningful context for this system. So with that, I want to thank my previous advisor, Nelson Spruceton and Xinyu Zhao, who I designed all the behavioral tasks with together. And finally, I want to end by saying that my lab is recruiting academia in Taiwan, academia Seneca in Taiwan. So welcome everyone is interested. Thank you.
Thank you very much, Xinlang, for the wonderful talk and very nice experiments. While the question and from the audience can arrive, I will say that it's impressive that also in the virtual reality setting, the mouse is able to learn this not so easy task, not so easy also for us human as you mentioned. So really impressive work. And so we have one question. I will read it to him. So from Aditi, do you see any EC CA3 input differences for context-dependent inputs?
ECCA3 input. What's the question again? Could you repeat?
So if you do you see any EC/CA3 input differences for context-dependent inputs?
Yeah, that's a very interesting question. I mean, for now we only record from the soma, and there's no control of which input we are actually looking at in the in vivo condition. But I guess part of the one way to approach that question is really a fundamental question of how the plateau potential plasticity rule work, like how much or how specific they're to a particular pathway, and even the inhibitory circuits, microcircuits. So that's actually one of a focus of one of the project I want to start on in my lab. But the general idea from older work is that the seems to CA3 might be greatly potentiated by the plateau potential, but I think the evidence is more indirect.
Perfect. Thank you very much for answering the question and for your talk. I think it's time to move on with the second speaker today. So thank you again, Xinlang. So the second speaker, we still will see hippocampus and virtual navigation. Our speaker is Sebastiano Curreli. He's a postdoc at the Italian Institute of Technology, and he got his PhD at the same institute in Genova under the supervision of Professor Alexander Dityatev, and he continued the work with Professor Dityatev at the German Center for Neurodegenerative Diseases until 2016. And so Sebastiano, the floor is yours, and I encourage everyone to send questions. If you send them earlier, it's easier to ask them. Thank you.
Okay, good morning, everybody, and thank you, Alberto. So now I work with Tommaso Fellin at Italian Institute of Technology, and I spent this postdoc working about spatial navigation and associated calcium dynamics. And during this neuromatch talk, I'll show you the results that demonstrate that hippocampal astrocytes do encode spatial information in their calcium signals. Let's frame the problem first. So to flexibly interact with the world, animals rely on perception of physical features of the environment. And in the nervous system, these physical features are encoded in neural activity patterns. For instance, we find a representation of space in the hippocampus, where place cells encode position, restricting their spikes at specific spatial locations. However, whether spatial information encoding could extend beyond neural circuits is currently unknown. And indeed, brains are not made solely of neurons. In fact, in the central nervous system, neurons are surrounded by glial cells, and astrocytes are the most abundant non-neuronal cell type. They are non-electrically excitable, but they exhibit a form of activity as a fluctuation of intracellular calcium concentration. These calcium signals can regulate a plethora of functions, including neurovascular coupling, synaptic plasticity, and network dynamics. As you can see in the cartoon, calcium signals can be quite heterogeneous. They can be restricted to subcellular regions of the astrocytes as the somata or processes, and they can involve the one cell or encompass multiple astrocytes. Using functional calcium imaging, we can observe the temporal profile of astrocytic calcium dynamics at specific subcellular regions. Importantly, calcium dynamics relate to neuronal activation, neurotransmitter release, and correlate to neuronal responses in vivo. For example, in the somatosensory cortex, astrocytes respond to whisker deflection with calcium increase, suggesting that astrocyte calcium dynamics can indeed be involved in information encoding. With this in mind, we formulate the hypothesis that astrocytes may encode navigational information in their calcium dynamics. And to test it, we coupled virtual spatial navigation and two-photon calcium imaging. Mice run along a virtual corridor provided with visual features, and at the end of the run, they get teleported back at the beginning of the track. To visualize calcium dynamics in vivo, we implanted a chronic window above the hippocampal CA1 area, and we specifically labeled the astrocyte with GCAMP6F. This enabled us to record astrocytic calcium dynamics with subcellular resolution, allowing to extract calcium activity at specific subcellular locations while knowing mouse kinematic parameters. We frame now the problem using an information theory approach, where R, the response, is our calcium signal, and S, the stimulus, is the position in the linear track. Using Shannon definition of entropy, we can compute mutual information as the intersection between entropies of astrocytic signals and position. We measured mutual information in 356 astrocytic ROIs, and on average, 46% of astrocytic ROIs encoded information about position. Here you can see the average fluorescence signal as a function of position for a sample of 5 astrocytic ROIs. I refer to this function as the response profile. And in gray, you can see the preferred spatial region that I call the response field. At a population level, we can represent each ROI as a row and color code its response profile. We can order rows according to the center of the response field, here marked as yellow dots, while magenta dots highlight the width of response field. I thoroughly tested how robust the relationship between calcium activity and position is using several resampling approaches. Here, for instance, if we arbitrarily divide the trials enough, being either even or odd, we can see that the overall pattern is comparable, demonstrating the robustness of response profiles. On the right, you can see quantification of response profile features. They have a median width of approximately 50 centimeters, are uniformly distributed along the corridor, and importantly, the difference between the response field center computing using either half of the data or the whole data set is centered at 0, quantifying how robust the response field estimates are. Then we move to investigate the subcellular organization of astrocytic spatial information encoding. In this example, I've labeled somatas as yellow and processes with magenta. On the bottom, you can see the same ROIs color-coded as a function of their response field position. And you can see that there is quite a diverse scenario. Some astrocytes show multiple response fields position, while others show quite an homogeneous response field tuning. If we sort ROIs according to their identity, either being a soma or a process, we can show that both maps have a similar pattern. Quantitatively, we can see that somata and processes have similar response field width and distribution along the linear track. If we now move to a population level analysis measuring pairwise features, we can see that neighboring areas have quite high correlative, temporal correlation. However, neighboring areas can encode for different preferred spatial locations, as you can see here in this graph, where the pairwise distance on the x-axis shows that as a function of the pairwise distance, the difference in response field's position grows and plateaus within 40 microns up to 40 centimeters. This can be due to a population effect, either relating to neighboring ROIs coming from these different astrocytes or to ROIs belonging to the same astrocytes. Thus, we focused our analysis on astrocytes showing spatial modulation at the soma and at least at one more ROI. And we can see that the response field's distance grows as a function of the distance from the soma, indicating that within the same astrocyte, ROIs can indeed exhibit different spatial tuning. Then we asked whether the information contained in the astrocytic calcium dynamics can be decoded on a single trial level. So we asked whether observing a single astrocytic response, we could predict discrete portion of the linear track the mouse was in. We performed this task using a support vector machine, and results can be summarized in a confusion matrix, where the x-axis indicates the actual position and the y-axis the predicted one. The color code indicates the fraction of observation classified in each possible slot, and the correct decoding lie on the diagonal. As you can see, the darker diagonal tells us that when the decoder is asked to choose between 3 discrete positions, it performs quite well. Therefore, we increase the granularity of decoding, increasing the number of discrete positions up to 12, thus testing the spatial resolution of the decoder. As you can see, across increasing granularities, we can consistently decode the mouse position. And quantification of decode performances shows that we can consistently decode the mouse position better than chance, that performances related to the respective chance levels are quite stable. Importantly, position misclassifications are more likely to happen between close by location. This data led us to another question, namely, how does this astrocytic spatial information encoding relate to the neuronal representation of space? To address this question, we upgraded our preparate to perform simultaneous calcium imaging of astrocytes and neurons during virtual navigation, labeling astrocytes with GCAMP6F and neurons with JRCAMP1A. This enabled us to visualize simultaneously spatially modulated astrocytes and place cells that here you can see color-coded according to their place field position. We can now investigate the relationships between these two coexistent spatial representations. And at the population level, astrocytic and neuronal response profiles show spatial pattern along the linear track. We can see that the neuronal place fields are sharper than astrocytic response fields and that they have different distributions along the linear track. First, we characterize whether the neuronal and astrocytic spatial representation relate to their anatomical layout. And we examined temporal correlations as a function of pairwise distances with pair composed of a neuron and an astrocytic ROI. And we can see that in general, correlation is quite low. And that regardless the distances of the pairs, the place field positions are basically unrelated and plateau at 60 centimeters. Therefore, we asked whether these two spatial representations could be the substrate of population coding. We used the information breakdown approach, an application of information theory that allows to study the mutual information that a stimulus gives about a set of responses. And here I will focus on response arrays made of just 2 pairs. The basic idea is that the mutual information of response array with the stimulus can be decomposed as the sum of the information provided by each element of the response array that I will call I-lin, and the differential term, which is the delta I. The delta I is basically our gain in information observing 2 responses instead of 1. This term can be either negative, indicating redundancy in information encoding, or positive, indicating synergistic information encoding. Importantly, delta I can be further divided in 3 terms. 2 of those are indicating whether our gain in information is independent from the stimulus or dependent from the stimulus. So the blue bar is the one you're going to need to pay attention to. In general, we can find both synergistic and redundant pairs among all the astrocytic combination, all the ROI combination possible, being either all astrocytic, all neuronal, or composed by mixed population. If we focus on the latter, the most interesting one, the one composed of an astrocyte and an astrocytic ROI and a neuron, we can see that synergistic ROI pairs have most of their information gain related to the stimulus, while redundant pairs have negligible stimulus component. Thus, to conclude, I've showed you that astrocytic calcium activity is reliably modulated by the animal position in the virtual track. Therefore, spatial information indeed extends beyond neural circuits to astrocytes. Somatime processes of astrocytes are both involved in information encoding, and they show distinct spatial tuning. Astrocytic calcium signals can be used to decode the animal's position on a single trial basis. And during virtual navigation, CA1 neurons and astrocytes both encode spatial information at a population level, and their coexistent spatial representation provides synergistic information about the animal position. Thus, overall, this demonstrates that during virtual navigation, neuronal circuit and astroglial networks synergistically encode information about space. So let me acknowledge my mentor, Tommaso Fellin, Jacopo Bonato, and Stefano Panzeri, to whom I collaborate pretty tightly at the Neural Coding Lab, and Sara Romanzi and Luca from the Optical Approaches to Brain Function Lab that I work in. And of course, the support of our founding agencies. Thank you, everybody.
Thank you very much, Sebastiano. Great talk and very elegant studies. And we have two questions from the audience. One is from Daniel. Do you think this coding is a side effect of the way astrocytes interact with place cells, or do astrocytes use this information to participate in the network?
Well, that's a pretty neat and nice question. And yet I can't provide a straight answer. What I can say is that what we think, we are speculating that astrocytic information encoding is a form of nonlinear integration of presynaptic inputs. However, to be completely fair, to test this hypothesis or other hypotheses related just that, for instance, the perception of the nonlinear integration done by neurons, we should perform perturbation studies in the neuronal circuits to see how this affects astrocytic spatial encoding.
Thank you. And then we have a second question from Carlos. Is it possible that sparse representation of the spatial maps on astrocytes is due to the use of static big region of interest when extracting a calcium signal on astrocytes? Maybe a deeper segmentation of the main processes of the astrocyte or the glia could increase the sharpness of the spatial map?
Well, that's indeed a nice point, and I would like to be able to answer to this question. Yet we know that we are doing an approximation both at the temporal scale and at the spatial scale, because we are sampling pixels of a size of 0.6 microns as a side. And so we know that we have already a big approximation over there, because we know that astrocytic calcium dynamics can be quite spatially confined even in sub-resolved astrocytic processes. So yeah, I mean, I would like to be able to respond, but I don't have a straight answer.
Thank you very much, Sebastiano. So we should move on to our last speaker of this session, again on hippocampus and navigation task. She is Elinor Derl. She is a postdoc and research associate at the Dartmouth College. And please, Elinor, the floor is yours. And I encourage again to send questions to our speakers. And you are muted.
Hi everyone. So thanks for coming. I will present our latest results about place cells and how they do not seem to encode spatial connectivity in a forum navigation task. So I will not talk about the global location aspect of our results here, but you can ask questions about it, of course. Roddy Greaves, the co-first author, is in the audience, and he will also be able to answer some of the questions if you ask them in the chat or in the Q&A. So why do we think that place cells might encode connectivity? Well, place cells have an activity which is very specific to location in space. We think they altogether support a cognitive map of space which allows us to navigate flexibly in all the environments that we know. But of course, what's the point of having a map if it doesn't integrate information about the connectivity of environments? So because place cells have this very nice spatial firing, we thought that they might also encode spatial connectivity. So to test this, we built this four-room environment. So we have these rooms, they are geometrically identical, and they are connected by these saloon-type doors that our subjects, which are male rats, can use to transition from one room to another. And we can lock the rooms by inserting small locks here at the top of the doors, which do not change the visual aspect of the doors, but they change the connectivity of the environment. So this is the protocol that we used. We have 5 sessions intermingled with rest periods where we take the rat out of the environment and we put him on this platform here. We start with 2 sessions where the connectivity is open, meaning that all the doors are pushable. And then we have 2 sessions where one of the doors will be closed, so the rat cannot go through them anymore. And we have a last session where we go back to baseline. And what happens during a session? Well, first the rat is allowed to explore without reward until he's visited all the boxes once. And then we start trials. A trial starts by the experimenter ringing a bell. So you can see the bells here, they are attached to the corner of each box. And the bell indicates to the rat that this is the next goal location. So we ring the bell, we throw food in the environment. And the rat then will do what we call a goal-directed trial to reach the goal box. And then he will start foraging in the box, which you can see these 2 types of behavior here in gray for foraging and black for goal-directed. Once the rat has spent enough time in the box, we start the next trial, which will lead him to a different box. And the sequence of goal boxes is the same for all 5 sessions. So let's look at our results. So the first question we asked is whether rats can represent, can remember the connectivity of the environment. And this is not so obvious because the open doors and the closed doors look exactly the same from the point of view of the rat. They are different from the top, but we don't observe rats looking at them from the top so much. So this is a video of a rat going through an open door. And this is a video of the same rat trying to go through a locked door. So you can see that he cannot go through. Which also means that nothing indicates to him that the door is blocked. He just has to experience it. So how did we quantify this? Well, we looked at the number of door pushes per door and per minute. And we compared this number between open doors and closed doors. And you can see there is a significant difference between these 2 types of doors only in the closed session, so session 3 and 4. And then interestingly, the effect perseveres in the last session, where all the doors are now open, and we interpret this as being a sign that rats have a memory of the connectivity of the environment. They are not just using immediately available cues. So we show that rats can learn the changes in the connectivity. An important thing for later that we'd like to mention is because the rats know the connectivity, their behavior, especially in the goal-directed phase, will be very different around the closed door compared to when the door was open. And we know that behavioral differences such as speed or head direction or direction of movement can influence the firing activity of place cells. but we are not studying these effects. We are studying the effects of changing the connectivity. So to avoid these confounds, possible confounds, we remove this part of the data from the analysis, and we will only focus the analysis, or most of the analysis, on the foraging data, where you can see that the behavior is more homogeneous. So this is an example place cell. This shows in gray the trajectory of the rat, and in red single action potentials of the cell. And this below shows a rate map, which tells you the firing rate in each location. Red and yellow indicate high firing rate, blue indicates low or no firing rate. So you can see this cell had a very stable firing across the 5 sessions. We analyzed this on the whole population of place cells that we recorded. So first, we looked at the correlation between rate maps, which gives you an idea of how similar they are. So we first correlate the 2 open sessions, and then correlate one open and one closed, expecting that if there is an effect of connectivity, the correlation would drop in the second group. And we show the correlations here, and you can see that there is no visible effect of closing the door. Actually, the values are slightly higher, but not significantly. Then we focused on the activity around the door, so in a 25 radius around the closed door. And we also compared open and closed doors, and there is also no effect. We also did analysis of place fields. So for example, here we detected place fields around the door. So you can see here the extent of the place field. And we looked at what we call bridge index, which is how much does the place field connect the 2 boxes or stay on one side. And you can see here a visualization of the field extent. So fields that have a low bridge index are at the top, and fields that have a high bridge index are at the bottom. And there's only a few fields that actually really cross the doors. Most of the fields do not cross the door. And this thing does not change when we close the door. It doesn't change at all. This is an example of how many fields were not crossing the door, and you see it's not changing. So there is no effect. So far I've shown you a few of the analyses that we've done on rate maps or place fields. We've done some more analyses, and they were all not showing any effect. They were not showing any effect of closing the door. We also had another completely different set of recordings where instead of closing a door, we close all the doors, but one way, so that the rats can now only transition clockwise or anti-clockwise, but not both in the test sessions. We did the same analysis, and they were also not significant or not showing an effect of connectivity. So before finishing, I will just mention this complementary result, because at this point, I imagine you might be wondering if there is a difference between the foraging phase and the goal-directed phase. So to answer this, we computed the similarity, again, in terms of map correlations between foraging rate maps and goal-directed rate maps. We can see an example cell here, and you can see it has a place field next to this door, which is still visible in the goal-directed, except when the space is not sampled, like here. So we computed correlations between these for all the cells. And if there is remapping between these 2 phases, we would expect a set of correlations around 0. If there is no remapping, stable place field, we would expect that the correlations will be skewed towards 1. And what we got was the blue distributions, which are significantly different from the shuffle distribution around 0. So it shows that there is no global remapping of place cells when we compare these 2 task types. And the other interesting thing here, so you can see 5 curves in each of these groups. Each of these curves indicates 1 different session type. So if there was an effect of connectivity on this, we would see 2 of the curves corresponding to C1 and C2 being separate from the others, and we do not see that they all overlap. So again, there is a very stable spatial firing between the 2 task phases, and this does not change depending on connectivity. So to conclude, we found no detectable effect on the parameters that we looked at of changing the connectivity. And this is when we control for other factors, such as not changing the geometry and trying to focus on similar behavior. And this is in contrast with past results, like those of Albert et al., where a detour situation was created by placing a transparent barrier. But we actually know from other experiments that transparent barriers can affect place self-varying. So maybe this explains the difference. And also models like the one of Stackenfeld et al., which reproduced the results of Albert et al. So where else could connectivity be encoding, or how else? Well, we did not look at replay or theta sequences, but it is possible that we would see an effect of connectivity on these phenomena. The thing is, how would we differentiate effects of just the behavior from effects of connectivity, especially on replay? If the rat only does detours, it will replay detours. Does it mean it's encoding connectivity or just encoding behavior? We will leave this question for other people who can record with multiple tetros and make it really stable if they want to reproduce our experiment. And last, probably connectivity is encoded somewhere else, because the rats know about the connectivity. It could be in CA3, it could be in medial anterolateral cortex, it could be in subiculum, or maybe a more remote region like prefrontal cortex. And so, of course, I would like to thank all the co-authors of this study, especially Rodi, who is the co-first author and did like 95% of the analysis. Our funder, the Human Brain Project, the IBN for their support and discussions, our subjects, the rats, Neuromatch for allowing us to present our results. And if you want to look at our preprint, you can scan this QR code here. Thank you.
Thank you very much, Elinor, for the great talk. And I encourage everyone to look at the preprint. You can also find the link in the chat box directly if you don't have to, if you cannot scan the QR code. And very nice study. And I have some questions, but before I will ask one from the audience. And if you have questions, just please ask. So Aditi is asking, do you think no effect in spatial selectivity between open and closed doors cases of foraging could be due to the possibility that the animal had the top view of the entire arena during inter-trial rest periods?
It's a good question. So I think the fact that the rat could see the whole environment just maybe allowed him to have a better cognitive map of the environment. And so he should actually know the connectivity even better from this. And the fact that, as we show, the rats do not use the closed doors when they are closed shows that they know about the connectivity. So why did we not see any effects? I think it means it's not encoded in CO1.
Okay, perfect. So we also have a comment from Katherine. In addition to saying that the talk was great, also the very cool way to illustrate the contribution of the different authors in your previous slide. I also appreciated it. So we have another question from Leonie. Very cool set of studies, I agree. Can I ask what your predictions for the one direction only navigation study were?
What is the prediction for the one direction navigation? Prediction regarding what? Sorry.
I think in general, what did you expect when you tried the second protocol?
With this other condition, instead of changing one door, if you want to know, actually, when I started the experiment, I only closed one door one way, and I saw that it wasn't changing anything on like the first place that I recorded. So I thought, okay, I'm going to change all the doors. And even because when you change all the doors, supposedly you should see an effect. It's all 4 doors that are affected. And even doing that, there was no effect. There was also, other interesting things about this configuration, which is that it sort of changes like the hierarchy of the environment, because the first maze all open, each box is connected to 2 other boxes. But with the one way, each box is only connected to 1 other box. So it also conceptually sort of changes the way the environment is organized. So for me, it's a stronger change, and still we did not see an effect.
Perfect. Thank you very much. Then we have a question from YouTube, because we also have the YouTube stream. Why can you decode so well the last bin of the linear track at every binning sides?
I think this is for another talk. Maybe, because we don't have a linear track.
That was for that was for Sebastian. Yes. Sorry. Yeah. Okay. Yeah, we have a bit of delay with YouTube. Okay. A very last question from Sepide. Very nice data. Would you say that your results argue against a predictive code in CA1?
So I would think so, because you would expect that when the doors are open, the place fields would sort of extend through the doors if each place field indicated the possible predicted futures. And we don't really see that. And we also do not see any changes of field extent around the fields which do extend through the door when you close the door. So I think this argues against the idea of hippocampus as a predictive map. But again, we are only looking at dorsal CA1 in a few rats, so it's only a small view of the whole hippocampus. As I said, maybe this predictive coding is happening in CA3. And maybe in our conditions, the predictive model and the successor representation would not see any effects. We don't really know. So maybe successor representation people will tell us more about this.
Okay, we have a last minute question from Aditi. It's time, okay. Do you see differences between proximal and distal CA1 for spatial connectivity?
I have not looked at this. There is the histology in the preprint if you want to look at it. And it's true that we do have some rats that are more proximal, more distal or more proximal. The thing is, none of the cells, I mean, there is no significant effect that we saw. And even when we looked at individual cells around the door to see if they remap because of connectivity, there was like 3 cells out of 53 cells which are around the doors that do something. And so even this shows that probably it's not due to anatomy, it's just a global effect.
Perfect. Thank you very much, Elinor, and thank you
Alberto.
Sebastiano and Chun-Liang for your great talk, and to all the audience that asked many questions and interacted so nicely. So I have to close the session now. Again, thank you everyone for participating, and enjoy the rest of NeuroMatch 3.0. Bye everyone.
Bye. Excellent. Thank you.
And biophysically grounded mean field models of neural population under electrical simulation. We have a fantastic line of speakers ahead of us, and we'll be starting up with Honjie B. B is a postdoc researcher at Okinawa Institute of Science and Technology. He's working in the lab of Dr. Tomoki Fuka, and he will be starting up with his presentation right now. Over to you, B.
Okay, thank you for introducing Amita. Okay, I will start my presentation. So I focused on the gamma oscillation in one inhibitory spiky neural network. As we know, in the experimental results, we for the rodent, they always they are in the awake or sleeping state. The neurons in the cortex usually show the asynchrony and the irregularity, and also has the fast oscillations. Fast oscillations in the figures show the raster plot. So actually, most of the theoretical scientists want to know what's a reason. So here they give one idea to show that. Here they built the neural network, and they assume one neuron can receive the inhibitory input and the excitatory input. If one neuron, the two input can cancel each other. So in that case, the network can controlled by the noise or fluctuation. So in that case, following this idea, they build exactly the models. So in this two equation here, show the last term show the input. In the right hand of the equation here, the first term shows the external input, and the last one shows represent receive the presynaptic input. So in that case, using the mean field method to we show the equation in the square. Here, if the system the k go to infinite, and first we assume if the I bar is positive. So if k go to infinite, it means the failure rate go to positive infinite. So the result is R bar is negative. So they are contradiction. So another way, if we assume I bar is negative, so the failure rate go to 0. We got the result is R bar is positive. See, they are also contradiction. So for the large k limited, the only state stable state is the balanced state. So we can get, so in that case we can get the irregular spike and asynchronous. So following this idea, my project group builds the quadratic integral failure model. Here the member of potential is second order. So in this case, they think about the instantaneous synaptic and also build the network. This network follows the distribution of the integral is a Laurentian distribution. Here the big delta k is the width of the distribution, and the k bar is the average of the integral. And also here the big I and G represent the current and the coupling strength. And in that case, we plot the raster plot and mean member of potential and the failure rate. We find the collective oscillation in the left figure show. And also for one neurons, they show the asynchronous irregular spike. And also using this kind of the network to other models, they also show this kind of the collective oscillation and the irregular spike. So we want to know what's the reason about that. So we find a very good method. This method from the PRX 2015. They using this method to think about quadratic integral failure model, and they reduce high dimension model to the low dimension equations. Here show the two equations. One is the failure rate, another one is the member of potential. And they also compare the network results with the mean field result, and they found they can confirm each other. Here the colors show the mean field, and the yellow color show the mean field, and the black color curve shows the network, and they confirm each other. So we're using this method to analyze the model, and we also reduce the high dimension equation to the two dimension equation. One is the failure rate, another one is the mean member of tension. And in this case, analyze this two equation, and we find the fixed point. And also find this fixed point is a stable focus, because previously we're using the balancing network. So in the balancing network, we have the endogenous noise. So plus these two characters, so that's why we can find the oscillation in the network. So this detail Matteo will talk about it. So here we would like to extend the ideal model to the more realistic model. Here, so here we think about the exponential time decay synaptic, and also using this method to reduce high dimension equation to the long dimension equation. So here we got the 3 dimension equation. One is firing rate, another one is member of tension, last one is mean synaptic, and also compare the network with the mean field results, and we found they are confirmed each other very well. So here we're using the mean field equation to analyze the bifurcation. Bifurcation here in this figure. In this figure, we show the bifurcation diagram, and we also find the 3 regimes represent the 3 different kind of the dynamics. Region 1 represents the stable focus, and region 2 represents the stable oscillation, and region 3 represent the stable bistable states, which coexistence stable focus with a stable oscillation. And here we find for the different parameters we can also find these 3 dynamics. And here we give one example in figure A. If here we fix coupling strings G and plot the bifurcation in figure A, and we find first stable focus, stable oscillation, and bistable state. And here, and also we pick one state in the bistable region. And using different initial conditions, we plot the raster plot, and we find 2 different states, but both of them have the oscillations. And also we find for the in the probability of the CU coefficient or variation, and we find for the stable focus the average of the CU close to 1, which means the spike, every neural spike is irregular, and for the stable oscillation, we found the average of the value close to 0, which means the every neural spike regular. So we also, in that case, we also focus on the frequency in the 2 states, because here we find the two oscillations. We found in the stable bistable region for the stable focus, most of the states in the slow gamma oscillation, and for the in the stable oscillation, most of the states in the high gamma oscillation. So now we already know this model. In order to compare our model with the experimental results, so here in the left figure we show the experimental results, because we know usually in the experiment the forcing, the input usually is a theta forcing. So in that case, here the experimental using theta forcing and find the slow gamma oscillation and fast gamma oscillation in the theta forcing. So we want to mimic this kind of the input. So we also using theta forcing, and here we also plot the power spectrum in the theta forcing, and we also find the slow gamma oscillation and fast gamma oscillation. And according to the bifurcation diagram, and we realize for the slow gamma oscillation, they follow in the stable focus, so which means the fluctuation driving. So for the high gamma oscillation, they follow in the stable oscillation, so it means they are mean driving. So in that case, we explain it, the experimental result, and also in our model we also find the phase-phase coupling. So here in this figure, in these 2 figures, we using the chromotal order parameters, which means if the rho go to 1, which means the system high perfect synchronization. If the rho is go to 0, it means asynchronization. So in that case, we plotting it. We find the 2 peaks. These 2 peaks corresponding to the slow gamma oscillation and the fast gamma oscillation. And also we're using another parameter to entropy to also find these 2. and in that case, they are in the phase-phase coupling. So finally, we give the summary. So first, we're using the exponent time decay synaptic. We find the coexistence of the two states: one stable oscillation, one stable focus, and they are in the slow gamma oscillation and fast gamma oscillation. And also we find if we using the different amplitude of the theta forcing, we can find the phase-phase coupling. And if we changing the amplitude of theta forcing, we can also find the phase amplitude coupling. But here I didn't show it, but we also have that. Yeah. So last, I will thank to my private collaborations. One is Professor Alessandro Torcini. Another one is Matteo, yeah, in our meeting. And the last one is Marco, yeah. I think later, Matteo will talk about more details about this, yeah, also this model, yeah. Thank you.
Thank you, B. It was an interesting talk. Do we have any questions from the panelists maybe first and then the audience? Any of the panelists would like to ask some question?
Maybe I'd like to ask how you had these synaptic changes, dynamic equation controlling the synaptic weights, and how the time scale of this process affects the oscillation frequencies that you have shown us. So the tau d in this equation.
Yes, here. Let me show you. Yes, here.
मेरा mouse छोड़ दिया आपने.
Yeah, here the tau d is it's a time scale of the synaptic. Yeah, the tau d time scale of the synaptic, and also for the tau m is for the member potential time constant. Yeah.
And this tau d is much slower than the inhibitory oscillation, right?
Because here we can control the tau d. For the tau m, we set it the constant. Here we using the 15 millisecond. But here tau d, because the tau d is we set it this way. This one is a parameter. So in that case, we can change it. Or in this figure, you can see for the x-axis, we increase it. We can see the different dynamics behavior. And but here we fix the tau m is a member time constant. Yeah, 15 time related to the real light biology background. Yeah.
Thanks, B. Any other questions that we have? Someone from the audience would like to ask?
Yes, I can ask to Onji if there is a difference between the slow and the fast oscillations apart from the frequency. If there is other differences. Maybe I didn't.
Yes, for the slow gamma oscillation is between the 30 to the roughly 55 or between the 30 to the 55 roughly, and for the fast gamma oscillation is between the 55 to the 90 or 100 hertz. Yeah.
Okay.
Yeah.
But it seems that there is another difference because it seems mean driven. The slow seem to be mean driven. Yes. So the neurons are regular and not irregular.
Yes.
Okay, thanks.
Thank you, B, and thank you for all the questions. Thank you so much. We now move to our next panelist for the session, Matteo De Polo. He is a postdoctoral researcher and is working in the lab of Alessandro Torcini at CY University of Paris. Welcome, Matteo. Please continue.
Okay, let me. Okay, so thanks a lot, Amit, and thanks to let me thank all the organizers of this NeuroMatch conference. I think it's a fantastic idea to be able to share our researches, even if we are all very far apart. So I will talk to you about our research, which deals with understanding the dynamics of population of neurons, and in particular their collective dynamics as a whole, by using tools from dynamical system theory and mathematical modeling based on experimental observations. Yes. Okay. Okay. So if you can see here, it's again the same figures that you show by Onji. If you look at the experimental data in the cortex, you see that neurons are irregular in different states. Here is a state during awake, where there is asynchronous dynamics, and also during oscillations. Oscillations in the sense that if we look at the whole population of neurons, we have that periods of time where a lot of neurons seems to spike together. But if you look at the activity of each single neuron, you see that neurons emit spikes in a very irregular manner. So they are not like clocks. And this is true in different regions. And so we are, the question that we want to understand from here is how do these neurons, how are these neurons able to synchronize together, even if they, I'm sorry, I have a problem with my, okay. How are these neurons able to synchronize even if they are completely irregular? And also another question is, typically these collective oscillations that we see in the brain are associated to some time scales, just like the delay of the propagation of the axon potential or the synaptic time scale of the synaptic interaction. But these freezes, in a certain sense, the frequency of oscillations of population of neurons to these time scales, and doesn't explain the broad range of collective oscillations frequencies that we see in experimental data. And also the other question that we want to ask here is, what is the role of the irregularity of neurons for the coherence and the dynamics of a network of neurons as a whole? Why are neurons irregular? In order to answer this question, what we do here is we developed a very simple model of a network of inhibitory neurons with instantaneous synapses that are arranged over a sparse network of connections of connectivity K. You see here the dynamics of the voltage of the neuron I, where F is the intrinsic dynamics of the neuron. I consider two different cases, the quadratic intertemphire, but also the Morris-Lecker. And then this is the interaction between neurons, which is negative because the neurons are inhibitory. And then each neuron receives an external current I, equal for all the neurons. What we do here is that we consider a sparse network with connectivity K, and we make a network simulations. And what we see, here I show the raster plot. So I put a dot whenever a neuron emits a spike at a certain time. And you see that there are some periods where a lot of neurons emit spikes together. So if you want, there are some bursts of activity of the network that seems to be periodic in time. So these are, if you want, collective oscillations. But if we look at the dynamics of each neuron, so the voltage of each neuron, we see that the neuron emits spikes in an irregular manner. So not all these bursts are the same. Sometimes neuron participates, and sometimes neurons do not participate. So if you look at few neurons in this network, you don't see any collective oscillations. The collective oscillations emerge only if you look at a lot of neurons together. More importantly, what we have done is that we have defined a synchronization parameter, which is rho. Rho is 1 when neurons are synchronized, and rho is 0 when neurons are not synchronized. And what you see is that we have a transition from situations where neurons are asynchronous for low connectivity K, and the situations where neuron gets synchronized for large connectivity K, as I have just shown you. More importantly, in all these regimes, we have that neurons are irregular. You can see here the coefficient of variation of the neurons, which measures their irregularity. When CV is 0, it means that neurons are periodic. When CV is 1, neurons emit spikes in a Poissonian way. So there is this transition between two situations where neurons are irregular, and most importantly, what I would like to show you here is that if we change some parameter in the network, like the external current, we see that the synchronization of the network goes to 0 whenever the coefficient of variation of the neurons goes to 0. So in a certain sense, this is an indirect information that the network synchronizes only if neurons are irregular, which is a bit counterintuitive. And so in a certain sense, it is like that if the noise that circulates in the network generated by the irregularity of the spike of the neurons, so it is an endogenous noise that the network self-generates, is what matters to generate these synchronous oscillations at a scale of the whole population of neurons. So to understand these phenomena, we wanted to develop a theory. The problem is that if, as in our network, we have a network of one population of neurons with instantaneous synapses and no delays, if we used some kind of heuristic population model, like of this form, we would end up with a one differential equation that cannot give us any hint on the collective oscillations. So what we did is to develop a mean-field model for the quadratic interinterfere neurons that is able to take into account also the dynamics of the average voltage in the networks. And so we end up with a two-dimensional mean-field model for this network with two global variables. One is the firing rate of the population, and one is the population voltage. In this mean-field model, we only consider the mean activity of the neurons, and we do not take into account the fact that neurons are irregular and they generate an endogenous noise in the network. Anyway, what you see is that the mean-field model here in red is able to give a good prediction on the mean activity of the network in function of the connectivity K. The black circles are numerical simulation of a network of 10,000 neurons. And what you see is that, of course, in the limit of infinite K, the firing rate reaches the balance regime, which is when the external current and the recurrent inhibition balance each other. Then we make a stability analysis of this point, and we see that it never loses stability. So it is never oscillating, but this fixed point is a stable focus, meaning that there is a frequency of oscillation inside. And so the idea here is that the endogenous noise that we have neglected in our theory is exactly what is able to activate the frequency of this focus and gives rise to the collective oscillations that we see in the network. So coming back to the idea that the irregularity of the neurons and the noise that this generates is what matters for the network to synchronize and get these collective oscillations. But if this was true, it would mean that the frequency of the collective oscillations that we measure in the network would be the same of the frequency that we can estimate from the stability analysis of this focus, which is this very simple analytical formula. And this is what I show you here. So you see the red line is the mean field prediction from the frequency that can be analytically calculated. And these black circles is the frequency of oscillations that we can measure directly from network simulation of a network of 10,000 neurons. What you see first is that it works quite well, and also that this network covers a very broad range of frequencies from 1 Hz up to 100 Hz. Showing that here we have a different mechanism of oscillations that do not involve external time scale, but an intrinsic time scale, which is the focus that I've been talking about. What we did next what we did next was to take into account a network which is more realistic, a network with excitatory and inhibitory neurons. So in this case, we have two populations. For each population, we have a two-dimensional mean field model. So we end up with a four-dimensional mean field model. And from this, you know that if we make a stability analysis of the fixed point, we will end up not with one focus, but with two focuses, so two couples of eigenvalues. And so we end up with two frequencies of oscillations. So this theory would predict that if you look at the network, we will be able to see the two frequencies that can be predicted analytically from the mean field model. And indeed, this is what happens. If we make a simulation of the network, we can see here, in green are excitatory neurons and in red inhibitory neurons. We see that the dynamics is not periodic, but it is quasi-periodic. And if we look at the power spectra, we see that there are all the composition of two frequency, mu1 and mu2, that also can be very well predicted in the dashed line by our mean field model, suggesting that also in this case, these collective oscillations are due to the irregularity of neurons that triggers the coherence. So to conclude, I have shown you how the irregularity of the neurons, so the fact that they spike in a very irregular manner, is exactly what can generate a coherent and synchronous dynamics of a whole network of neurons, which is a bit counterintuitive, but explains their importance. And also this mechanism of collective oscillations is what permits to have a very broad range of frequencies from 1 to 100 Hz, just changing the external current. And also have shown how this is possible to be explained with a two-dimensional mean field model for sparse networks that is able to predict collective oscillations frequency. So this work has been done in collaboration with Alessandro Torcini, and so I would like to thank all of you for your attention, your time, and also Alessandro for the collaboration. So thank you.
Thank you, Matteo. Very good. Yeah, we do not have claps properly, so we can have it.
It's okay, it's okay.
Okay, we have a question from Aditi. Can the endogenous noise also have some structure that makes the network to have fixed frequency of the oscillation each time?
Yes, so let me see if I have correctly understood the question. So the noise in this case is a noise that is not generated by ourselves. So the noise is generated by the system, by the network itself. So we do not add external noise to the network. The noise is something that the network generates itself. And so in this case, we have seen that it doesn't have any color. It's a white noise. But in principle, it could be possible for a maybe different model with different parameters to have a system that generates, for example, a noise which has some frequencies inside. And in that case, I believe that it would be able to generate a even richer collective dynamics. But in this case, the noise is something that we do not choose. The network generates by itself the noise due to the randomness of connections. And it's a white noise in this case.
Thanks, Matteo. Thank you so much. Any other questions from the panelists or from the audience? Yes, Chala, please.
So thanks for the talk, Matthäus. I'd like to ask you, so in the 2D case, when you have two populations, you have usually the inhibitory loop that creates an oscillation. Is the second oscillation that you showed us the oscillation due to excitation inhibition?
Yes, so here there is no delay between the spike emission. So in principle, we do not have, and the time scale of the excitatory and inhibitory population is the same. So I believe that if we take this network and we make a theory which is, for example, an heuristic model like a Wilson and Cowan But with that, for example, imagine that you fit the transfer function and you will not get synchronous oscillations. You do not have a ping or a kind of oscillations. The oscillations are really emergent because of the noise that if you want, generates this kind of stochastic resonance that the network generates by itself. I don't know if I have answered, but please ask me more if I didn't.
No, thanks. Thank you.
Thanks, Matteo. It was really a very fascinating talk. Next, we move on to Chala Chun. He is PhD researcher at the lab of Klaus Obermeier in Technical University Berlin. Over to you, Chala, please.
Sorry, I was muted. So thanks for everyone joining. I hope you can hear me. And so my talk will be kind of like an extension of what you've seen before. And let me just start with it. So here's a short outline. First, I'll talk about the interaction between neurons and electrical fields, how they interact in the first place. Then we'll present shortly a mean field neural mass model that can capture effects that we're interested in. And at the end of the day, I will show you how electrical stimulation affects a population model that I've just shown you. So let's go for first a little bit of motivation. Why are we interested in electrical stimulation? Probably all of us know that there are multiple stimulation techniques popping up in the last couple of years that are being very successful in treating diseases, DBS, TMS, and TES, for example. And most prominently, TES is a technique that is very easily applicable by placing electrodes onto the scalp. And these also have been verified through cadaver studies, for example, where people put the electrode out to the scalp and measure spikes inside. And you can see what you also might expect is that external fields that's from the TES stimulation can entrain spiking of the neurons inside of a brain, right? So in my mind, if you would want to model something like this, you would have to probably simulate a whole brain for that in order to know how an electrical field affects the brain dynamics. Another way to research electrical fields is to look at what happens in a slice preparation. So local populations of neurons usually put the slice between two electrode plates. And then here you see one example where the population is spiking at 25 Hertz, and then an input is turned on and off again. So you can turn on and off an oscillation. And if the input is oscillating, you can even have new oscillation frequencies emerge. And this you might simulate using a model of cortical patch, let's say excitatory inhibitory neurons, and this is what I will talk about today. But let's go one step back first and see how do electrical fields interact with a single neuron. And for a pyramidal neuron, it's pretty clear that when you have an electrical field outside and you have ions flowing inside of this neuron, that the electrical field will affect this. So one way of modeling this would be a morphological model where you really place these tubes and cables and currents that interact with the electrical field. And the way this works is basically very similar to how an antenna works that we know and use every day. However, we like to use point neuron models, for example, ADEX neurons, and ADEX neurons don't have an extension, so you cannot couple an electrical field to an ADEX neuron because it doesn't have that spatial extension, so that won't work. And one way of solving this is from a colleague of mine was to fit a ball and stick neuron to the ADEX neuron. So a bit intricate. However, he calculated how the electrical field, Florian, affects the spiking of a ball and stick neuron and translated that into an equivalent input current to ADEX neurons. So it's kind of like getting an electrical field effect to point neurons, very shortly said. And so this is what I'll show you in the next couple of slides. And I've decided to not put any equations to how this mean field approach works, but just a image will suffice, I guess. So we have an ADEX network, delay coupled between E and I populations receiving inputs. And we do this mean field reduction that you can see in our paper, how it works. But at the end of the day, we get we do these typical mean field assumptions, and we get a population firing rate model that gives us the firing rate of the population depending on the mean inputs to both populations. So It's a linear, nonlinear cascade model that is extremely efficient, originally derived from a Fokker-Planck equation of these ADEX network neurons. So we end up with a ADEX mean field model of ADEX neurons. And now I want to draw bifurcation diagrams of this model to see what it can do, right? So similarly to as the other talks that we've seen before, now let's draw a bifurcation diagram in 2 dimensions. We have one input to the excitatory population and one input to the inhibitory population. These are the parameters that I'm changing. And you can see here the states that emerge. So in the inhibitory dominated regime, we have a down state where there's a low activity. In the excitatory dominated regime, there's an up state with high activity. These are fixed points. There is a bistable region where upstate and downstate can coexist, so you can jump between the two. And in the middle, here's a limit cycle in white contour where the activity oscillates between excitatory and inhibitory population. So this is the bifurcation diagram of the mean field model. And to verify this, we did also simulations, huge simulations with large networks of neurons to see if the bifurcation diagram is actually true. And it turned out to be quite true. So here you can see the analog bifurcation diagram of the ADEX network, now simulated with 50,000 neurons per point. So this is a very huge simulation that is going on. So just to, I mean, this guy takes about, let's say, 15 to 20 minutes to compute. This one probably a week or so on a live server. So we have adaptive neurons. This was without adaptation. Now adaptation, a single neuron for ADEX does usually this. So you have adaptation that makes the spiking slower as the input comes. So this is what it does for a single neuron. And we were wondering, what does it do for a population of neurons? So we turned on adaptation, and what happens was this. So the bifurcation diagram is transformed from the upper one to the lower one if you turn on adaptation. And most strikingly, what you see is that the bistable region now transforms into a new limit cycle. So you have now 2 limit cycles, one the fast one between E and I, and another one that is due to adaptation. So excitation and adaptation, basically. And let's look into these states. So basically, if you sit in one of these points, for example, you see a fast oscillation between E and I. And if you sit inside the adaptation limit cycle, you see slow oscillation that is due to adaptation, a lot slower than the EI oscillation. Okay, so this talk is about electrical stimulation. Let's talk about electrical stimulation. And one way, the reason why I also showed you these bifurcation diagrams is now we can try to understand what stimulation would do to these neurons, to this population. So imagine you're sitting somewhere in this bifurcation diagram, A1, for example, and you turn on electrical stimulation. It is equivalent to moving on the x-axis of this bifurcation diagram because we're changing the input to the excitatory population through stimulation. And why only excitatory population? Because, as I said before, you need extension for interaction with electrical field, and excitatory neurons have this antenna-like structure, pyramidal neurons, for example, but basket cells, for example, are much smaller and more symmetric, so you don't have much interaction with the electrical field. So this makes the electrical field input basically move on the x-axis here in these diagrams. So let's do now this. We put the bifurcation diagram to the side and then sit on this point A1 and just repeat what other people have done with the experiment. So for example, we start in the down state. Now we turn on the stimulus and we can see how we move from the down state into the limit cycle by a constant stimulus, right? So this turns on an oscillation through a direct current. The same is also true for the ADEX network. Of course, if you sit in an equivalent point in the bifurcation diagram. We can also turn off oscillations if you start in a limit cycle and then push it into the upstate. So you see the upstate here, for example. Same also for the ADEX network with a longer transient. We can also, this is how we detect the bistability in the ADEX network, for example, is by pushing it up, then you relax the stimulus. So you're in the upstate, and then you push it down and you relax the stimulus again. So the input here and here is the same, but the states are different. You see, here's an active state, here's an inactive state. This is how you can detect bistability, for example, in a spiking network. And you see the same also in the spiking neuron model. You can have phase locking. So if there's an oscillation going on and you input an oscillation, then you will have interaction of these oscillations. And you can also drive oscillations with an oscillatory stimulus. So I'll quickly talk a bit more about the oscillatory stimuli, what they can do. And now in this example, So the population is oscillating at 25 hertz. You can see the frequency spectrum of the oscillation, and this is in the EI limit cycle. And now I'm turning on a stimulus with a specific frequency, and the stimulus frequency will change. This is a movie now, and here the frequency spectrum of this thing. You can see here is the peak of the oscillation, and in red you see the stimulus frequency. And now I will change the stimulus frequency, and I want you to pay attention to what happens if the stimulus frequency approaches this peak. So something will happen, and you can see what. So I'm changing the stimulus frequency now. There's lots of frequency going on, and now something happened and it dropped back to the original shape. I hope you catch what it was. So I'll just replay again, and you can see that when the stimulus comes close to this peak, it picks up the peak and moves along with the peak. Yeah, so this is called frequency entrainment, and we can measure this. So this is now the same diagram, but looked at once. Basically, we're changing the stimulus frequency on x-axis, and we're drawing the spectrum on the y-axis, and the color is the height of the spectrum. And you can see here the frequency is going on of the oscillation until it reaches this oscillation frequency, the resonant frequency, and then entrainment happens. So it takes up the peak and moves it along until it's too high, and it drops back into its original frequency. Now, since we have a biophysical model, we actually can measure what the electrical field strength of this will be, and this is around 1.5 volts per meter. We also did the same for the ADEX network, which is a slightly higher frequency as well. So I'm a little bit out of time. We also did the same with higher frequencies, and you can see all sorts of interactions of frequencies going on here. And so we measured frequency entrainment and measured also the field strengths. We also measured phase locking, because this is important for stimulation experiments. And what I can tell you is that phase locking also works in this population model with much lower electrical amplitudes. So my conclusion very quick is mean field approximations work very well if you want to speed up your simulation time. Also, non-stationary interactions are well captured. DC input can, for example, cause attractor switching. AC can frequency and phase entrain. And most importantly, the field strengths that people use in experiments really seem to have an effect on population activity. So this was my talk. You can simulate everything also using our framework here, NeuroLib, and thank you for the attention.
Thank you so much, Chala. It was really a very fascinating talk. I think we have a question from Matteo. Please go ahead.
Okay, yes. So thank you. It was a very nice talk. So apart from, it seems that the mean field model works very well. I was wondering, of course, in different states of the brain, we have neuromodulation that changes. So for example, the strength of adaptation can change depending on the state. So my question is, how does the resonance frequency, or for example, the amplitude of stimulation that you need to change oscillation depend on the level of adaptation that can be its strength or the time scale, which can change, for example, in different states, as if your tool to switch could be state dependent in a certain sense.
Yes, so thanks for the question. This is indeed true. We also did lots of exploration on what changes in the bifurcation diagrams when you change certain parameters, for example, adaptation. So this was one slide that I didn't include, but you can see maybe, oops, I cannot show you the slides anymore, but I can tell you that changing adaptation also changes the bifurcation diagram. And the same is also captured in a mean field model. So that still works for changing parameters. And it is completely true that the state, it really depends on the state in which you are, how the reaction to the stimulus will be. I would even say it's even more important than the stimulus parameters in a sense. So the stimulus parameters might be 10 hertz or 15 hertz, but it really has an effect whether you're in a fixed point, for example, or in an oscillation already. So I can only tell you that there's a lot of dependency on the state, and it really depends on where you are in the state space.
It's very interesting. Thanks.
Mm-hmm.
Thank you very much. I guess we are running short of time because the next session is about to start. So any questions that you have for the Chala, please take it up with him on the Twitter. And thank you, everyone. Thank you, B, Matteo, Chala, and Ellie for the backend support. And all the attendees, thank you so much. The conference is successful because of you. See you in the next session. Okay, bye-bye.
Thank you.
Bye.
Different techniques for understanding different mental disorders. We have a very fascinating line of speakers in this particular session. We'll be starting up with Sergio Gro, I hope. Sergio is presently a master's student and is very soon to join his doctoral research. He's working under Dr. Raquel Bezo Sobera at Cognitive Neuro Lab from Open University of Catalina. Over to you, Sergio.
Okay. So thank you and welcome to my presentation. Neurocognitive disorders are more and more prevalent in our society as our lifespan increases. And Alzheimer's disease is the most common subtype of dementia. And here you can see the 4 principal characteristics that can be detectable in late stage Alzheimer's disease. But the problem is that it might be too late for the patient to prevent a cognitive decline when all these symptoms appear. And that is why it's important to predict the future outcome of Alzheimer's disease in patients with mild cognitive impairment. And our objective is to perform a systematic review of articles that use machine learning methods to predict a conversion from MCI to AD. The most common ways to visualize these cortical changes are these 2 neuroimaging techniques, and the studies we analyzed use this brain data, like cortical thickness, along with other variables, to train a machine learning classifier and try to predict a future outcome of MCI in patients with MCI. This is the Prisma workflow we follow for the sample selection, and here you have the inclusion criteria, and we can come back here later, but for now let's just jump to the results section. So almost everyone used ADNI database this is good because ADNI database has been validated for the study of MCI conversion or progression to AD. It also has several years of follow-up from hundreds of MCI patients, and the sample size of this database is increasing every year. Here you can see the neuroimaging techniques selected in each study, and as you can see, the majority of them used magnetic resonance. Also, 3 studies used positron emission tomography, 13 studies used the combination of these 2, and 2 studies used magnetic encephalography. So each study had a cohort of MCI or mild cognitive impairment, but 8 of them also had AD and healthy subjects along with the MCI. 32 of them separated between a stable and progressive MCI, and 4 of them had a healthy subject cohort along with the MCI. Here you can see the mean number of subjects per year, and as you can see, there is a trend of increasing every year, and that might be for the increment of sample size in the ADNI database. The most selected features are cortical thickness and intensity measurements, and that's something we expected, taking into consideration the 2 neuroimaging techniques that were most selected. Other selected features were biological measurements like APOE4 genotype, demographic data like age, and cognitive measurements. The classification method selected, SVM support vector machine, was the most selected classification method. And here you can see 3 types of the Gaussian kernel, which was the most selected kernel for this classification method. That's something we also expected because support vector machine has been proven to be a very good classifier of high-dimensional data. But the tendency of the last 2 years or so is to start using deep learning methods, and the most selected deep learning method was convolutional neural network, which actually was the classifier that correctly classified the most number of subjects. Here you can see a table of comparison of these 2. So the specific search of AD biomarkers is much more abundant than the MC conversion. And we think it's important not to forget that if we can predict an MCI conversion, we can start now a treatment that can prevent this cognitive decline, and we can allow the patient to live healthier and longer, and also save out of resources for the family and public health systems. Also, deep learning is the way it performs better, and it's easy to understand the model outcome, meaning that we can see which areas are the actually ones that help correctly classify subjects. And the most important regions of the brain for MCI classification are actually the ones that has been extensively validated by the literature, meaning that the information that the models provide is actually useful. Here you can see the brain areas that were the most important for this binary classification. And it still needs a lot of work because it's far from perfect, but it can be useful for helping clinicians, for assessing clinical professionals. And I think it's a really interesting line of research. So thank you very much for your attention. And before the questions, I just want to say that here you have extra discussion points like the risk of bias analysis I performed, and also that I have all the studies sorted by neuroimaging technique here. But for now, let's go back to the slide about the discussion points I think are more important of my research. Okay. I don't know if there are any questions.
This is an interactive session, so I would appreciate if someone has any questions, we can take up the questions in between as well. Please drop in your questions. I think we do have one from Eva. Could you describe the key brain areas a bit more? Did you expect these findings anything unusual? Thanks, Eva, for the question. Please, Sergio.
Oh, yes, the brain areas. Here. So not really. Basically, the brain areas are the classic brain areas we also always talk about when we talk about Alzheimer, like hippocampal regions or temporal regions or frontal regions. And here you can see the most important ones in this binary classification. For example, AD versus healthy controls, or MCI conversive versus stable. And yeah.
Thanks, Sergio. There is another question by Marta Russo. Can you describe a bit more the features that were used in the classifiers?
Yes. So the features, normally they were other cortical thickness or intensity measurements. And this cortical thickness, for example, was from 90 or more regions of interest. Something I didn't do in my investigation was perform an analysis about the feature selection because I didn't have time. But basically, the matrix of data was out of subjects and out of regions of interest, and they extract the cortical thickness or intensity measurements, and also biological features like APOE for genotype I said, or demographic data like age, gender, years of study, and also cognitive measurements like mini mental state exam or other kind of tests or neuropsychological tests. So those were basically the features.
Thanks, Sergio. Any other questions that we have from the audience? Anyone from the panelists would like to ask a question?
Yeah, I'll ask one. So I think you may have gone over this, but it's quite quick. How did you? So you had quite a few different MCI groups, and I'm wondering how you defined them initially.
Okay, so ADNI database has follow-up years, and MCI subjects were evaluated several times along these years, and then if the MCI subject converted to AD in, for example, 5 years or 3 years, depending on the follow-up, then it's considered a conversive MCI, and if not, it's a stable MCI, meaning that the cognitive decline didn't occur.
Okay, thank you.
Thanks, Divan. So that's very nice talk, Sergio. Now we can move on to our next talk for this particular session. The next speaker is Alex Michel. She is a postdoctoral researcher at University of Edinburgh, and she works with Professor Robert McIntosh. Over to you, Alex.
Sorry, I'm unmuted now. I'm going to talk about our work in about reaching in Alzheimer's disease. So when you typically think of Alzheimer's, you associate it with symptoms such as memory loss and degeneration in areas that we saw on the earlier slide, like the medial temporal cortices and hippocampus. But studies have shown that actually one of the first areas to show pathophysiological change that leads to Alzheimer's is actually the precuneus, which is in the parietal cortex. And these changes have been found to occur some 20 years before the onset of any kind of clinical symptoms such as memory loss. And the precuneus is part of a network of areas called the dorsal visual stream, which are critical for the online control of visually guided actions. And when the dorsal stream is damaged, it can cause conditions such as optic ataxia, which is a really specific disorder of online motor control where patients have difficulty reaching to things that they're not looking at, so in their peripheral vision. So this video shows a really good example of someone who has optic ataxic symptoms. They can't reach to the rod when they're looking straight ahead, but when they're looking at the rod, they can reach to it perfectly. So because of that feature, these symptoms often go quite unnoticed because, when you reach to something in your environment, you look at it before you pick it up. So given that optic ataxia tends to go quite unnoticed unless you're looking for it clinically, and the changes and the functional changes that we see in the dorsal visual stream in Alzheimer's, we thought that individuals with Alzheimer's NMCI might present with similar symptoms to what we see in optic ataxia, so an extreme peripheral reaching deficit. So this is what we tested. And to do this, we used 2 different reaching tasks. The first, where we presented our targets on a laptop screen in front of the participant as so, and we got them to perform 2 slightly different conditions. The first we called free reaching, and it's when you present a target, you simply get the participant to look directly at the target and then reach to it, so just standard reaching. And the second condition is peripheral reaching, and the only difference here is we got our participants to look at the fixation cross throughout the entire reach, so straight ahead of them and reach the targets without looking at them. And it's in this peripheral reaching condition that we expect to see an inflation of reaching errors in Alzheimer's disease and MCI. Because this reaching task was presented in the lateral plane, so the frontal parallel plane, we call this our lateral reaching task. And here targets are presented in the far periphery at 3 separate target eccentricities. Our second task, we presented our targets in depth. So this is the display just here. So participants were reaching out to touch targets in depth. And we called this our radial reaching task because our targets are represented in radial depth. And here they were presented at 4 separate target locations from near to far periphery. And we again got them to do free and peripheral reaching as well. So to get an idea of how well our patients performed in the peripheral task, we calculated what we call a peripheral misreaching index, or PMI, which is simply the absolute error for reaching to targets in free reaching condition subtracted from the absolute error in the peripheral reaching condition. And once we had this number, we ran a case control analysis to identify substantial reaching deficits at the individual patient level versus our controls. And then we also ran a standard group analysis where we compared mean differences across our 3 groups. I'd just like to highlight that a lot of this analysis was done by a wonderful PhD student at UEA called Annie Warman. I just wanted to acknowledge her contribution to this project. So what we found when we're looking at just the PMI analyses, you can see data from our 3 participant groups here. And just to note that the higher the PMI, the worse the individual is at reaching to peripheral targets. The filled diamonds that we see here show the cases where they had a significant reaching deficit compared to controls. So that was our case control analysis. And as you can see, there's only 1 in each group here. So there's 1 MCI and 1 Alzheimer's patient who show a significant peripheral reaching deficit. And these crosses show the group mean, and as you can see, there's very little difference in reaching deficit across groups in the lateral reaching task. So that's our frontal parallel task. For the radial reaching in depth, we found very similar results. So there are a couple more Alzheimer's patients who show a significant deficit and a slight overall inflation in peripheral reaching error, but again, very little difference across groups. So if we just look at accuracy, we can see there's actually patients with Alzheimer's cope quite well with peripheral reaching, and there's not much difference between their reaching errors and the control group's reaching errors. But there's usually a speed accuracy trade-off with these kind of things. So sometimes you slow down to compensate for any impairment that you might have in your reach. And if we look at movement time, which is the reach duration, so the time when they take their finger off the button and to when they touch the target, you can see that in both free and peripheral reaching conditions in the lateral reaching task, individuals with Alzheimer's are 100 to 200 milliseconds slower than healthy controls. And this is significant across groups. And our MCI patient sits somewhere nicely in the middle here, where they're significantly slower than our Alzheimer's patients, but significantly faster than Alzheimer's and significantly slower than our healthy controls. And this result is reproduced quite nicely in our radial reaching task, where we don't see as much difference between our patient groups, but there is about a 100 millisecond slowing in reach duration in our patients compared to our healthy controls. So what this suggests is that there is some subtle visuomotor impairment in Alzheimer's disease and mild cognitive impairment that's compensated for by slowing down the reach movement. So just to summarize a little bit, we don't find any evidence of any optic ataxic-like reaching deficit in Alzheimer's and MCI, but there is evidence for a slight underlying visuomotor impairment that's compensated for by slowing down the reach. And it'd be really interesting to look at further studies into peripheral reaching, more complex peripheral reaching, such as grasping or speeded response, to sort of piece apart the deficits that might be present in Alzheimer's disease. And finally, I just want to thank my team. So my PIs, Stephanie and Rob, the clinicians on the project, and the wonderful master students that were involved in data analysis and collection, as well as the teams at Rounding Clinic and the NHS, our funders, and also all the patients and carers that are involved in the project. And thanks for listening, and I'm happy to take questions. It's an interactive talk, so please, lots of questions.
Thanks, Alex. Do we have any questions from the panelists and the audience? Someone from the panelists may would like to go before? Yeah, we have a question. Marta is asking, would you consider another interpretation? For example, that MCI and AD have timing impaired instead of spatial accuracy? Interesting question. Yeah.
Yeah, no, that's a good question. So yes, I mean, we could. I mean, so to sort of really look into that would be interesting to basically limit the reach response the time that people have to reach. So, you know, sort of get them to reach within like 1.5 seconds or something like that, and make it quite a short response, and see if there's any spatial error impairment as well as a timing impairment there, and that will be able to piece apart that question. Yeah, so it's a good question. Don't know for sure just yet. So.
Any other question? Thank you, Alex. Yeah,
I
Giana.
Question as an answer for another question. Sorry.
Okay. So thank you, Alex, for the wonderful talk. And we next have Rana Corey I hope I'm speaking it correctly. She's a postdoctoral researcher at Holy Spirit University of Kasik, Lebanon. She works in the lab of Dr. Sandy Rihanna, and she will be talking to us about AR special text for AD diagnosis. Over to you, Rana.
Hello, everyone. Okay. So I wanted to ask Alex before, but I didn't have time, if the task maybe could be possibly done in AR. And this is the point of my my talk, is to present a pipeline to do augmented reality tasks for spatial cognitive tasks for Alzheimer's disease. So, for example, the spread of amyloid plaque and neurofibrillary tangles in Alzheimer, which are the two proteins that are thought to be correlated with the spread, with the progression of the disease. And the amyloid plaque first starts in the prefrontal cortex and then progresses and then spreads into the brain, and the neurofibrillary tangles start in the transinternal or internal cortex and then spread to the hippocampus formation. But the neurofibrillary tangles are thought to be much more specific to Alzheimer's disease, while the amyloid plaque spread is overlapped with normal aging in the early stages or with frontotemporal dementia. So it's good to focus on the neurofibrillary tangles, I think. And it's very important to be able to detect the disease in the early stages, because it doesn't have symptoms in the preliminary part of the disease. There are no symptoms, so it's hard to detect it without MRI or PET scans. And so there's a need to create new tests to detect the disease, new cognitive tests, because they're low cost and easy. So, for example, this is a memory test that showed to be much more specific and sensitive to Alzheimer's disease, where they collected 20 years prior to death for more than 6,000 healthy individuals, and they tested multiple cognitive functions like memory, processing speed, fluid intelligence, and crystallized intelligence. And this spatial test showed to be the most specific and sensitive to Alzheimer's. Lately, to make the tests more realistic, they start to do these tests in VR and AR, and so they can create an entirely controlled environment where the patient can navigate, and they can collect all sorts of metrics like the path he followed, the time he took to perform several tasks, and design any experiment they want. So it's much more flexible, and also they can translate a lot of the studies done on spatial tests for animals to these VR tests. So at first we thought of making an AR test, a specific AR test, but then we thought, why not make a pipeline so anyone can design any test they would like in AR. And to scale it up even more, why not do it on a smartphone device with a headset, so everyone can use it at home, and then they can remotely assess the test that the patient can do at home. So the features that can be implemented in an AR is first the tracking of the device, the smartphone, how the device is moving in space, and so they can collect how the patient is moving. They can also track hands, so it could be more interactive and much more intuitive to pick up objects and move objects and interact with the 3D environment with his hands. Object detection if needed, and spatial recognition, where they can make the test can be performed according to the spatial environment of the user. So it can be more specific to his environment. Okay, so to do this, we first did the video is not working, I think. I don't know why. We first did the AR tracking in WebXR. And to do that, we used the WebXR device API, which can collect information from the inertial measurement unit of the smartphone. It can take information about the acceleration from the accelerometers and information about the rotation from the gyroscopes. It can combine it with features coming from the camera feed to correct for the device position, and at last it can copy this position to the virtual environment so that the virtual camera can follow the movement of the space. But I don't know why the video is not working. Sorry. Okay, can you see it now? Okay, so it can be inline in the camera, but it's more useful to make it like the left video, the right video, sorry, where we use a headset, a cardboard headset, and split the screen so that the virtual environment can be seen in with stereoscopic vision, as if it's in the environment. To do the hand tracking, we use the media pipe library. So first, the camera feed takes detects the hand, and then once it's detected, it's cropped, and then the landmarks of the hand are detected using a neural network, an SSD architecture with a mobile net feature extractor model, which is very convenient for resource-constrained environments like the web and the mobile, because it's fast. And then we try to do marker detection and pose estimation, where when the camera detects a marker, it should try to estimate the pose of the object. So we should know how exactly the marker is away from the camera. And to do that, we need camera intrinsics, like the field of view of the camera and the model coordinates and image coordinates of the marker. So here's where we face the biggest challenge, is that each one worked with us on its own, but when combined, there were too many computations being done both on the browser and the phone. And so the application lagged a lot. And now what we will try to do before combining it with the spatial recognition is to try to move some of the computations to the server side with a backend and do parallel processing with Node.js. What we can also try to do is with WebAssembly, try to code some algorithm in C++, for example, which is much faster than JavaScript, compile them to bytecode and make them run on JavaScript. And we can also use a web worker, but I think this will be the least useful for us. Finally, if we were able to do this and speed up the application, we will have a flexible application where users can choose which features to include. Like, it will be easy to design. They can choose between a set of features, and it will have a bigger impact. They can make it work on a browser, so nobody will need to download anything, and they can make patients test it and before they have any symptoms of Alzheimer's disease, and see if they can get anything meaningful from the test that they have designed. Finally, I would like to thank my supervisor, Dr. Sandir Hanna, and I would love to have some input especially from neuroscience perspective, to see if there's anything meaningful that we can add to the application. Thank you.
Thank you so much, Rana. Any questions from the panelists or the audience?
Well, I can answer Rana's question. So I just wanted to say that absolutely we could do the kind of stuff that with augmented reality. I mean, it's kind of a dream to be able to do that kind of thing, like, because obviously we're looking at conditions that happen in the real world, and then you're giving people dots and on screens to look at. So doing something like that and assessing peripheral reaching and spatial ability would be incredibly cool. So yeah, that's just to answer your question. But I have no further questions about your talk. I thought it was really good though. Thanks.
Thank you. Yeah, I immediately thought that I didn't think of this kind of application before, and I immediately thought, okay, this would be even better than the things I thought of doing.
Yeah, it would be very cool.
Cool. Thank you so much, Rana. Any questions from the audience? It was very interesting to hear about the application of AR in AD. That is really very interesting. Any further questions do we have?
Yeah, I've just got an add-on question, I guess. It's just like, how do you think patients will respond to it? Like, have you been able to sort of tests, because, you know, they struggle with dealing with certain tasks, and an AR environment might not be that comfortable for them and stuff. Like, do you have an idea of how they can cope?
Mm-hmm. So first, AR there's no problems in AR like VR, so they won't feel any dizziness because they will still see the environment, and they can still focus on things that are really in the space and not on a closed screen. And yes, this is why I'm trying to make it as much intuitive as possible by using their hands, because I realize not all senior patients will be familiar with AR games in general, and and the controls for them.
Okay, great, really great. So we had a nice session, and I would like to thank our panelists, Rana, Alex, and Sergio, for the interesting talks that they had. And in the case our audience have any questions, we still have some time, or else we will see you all in the next talk.
Thank you, Amita.
Okay, thank you so much. Thank you, everyone.
Thank you. Bye.
Thank you.
Welcome to the NeuroMath session. This particular session is basically about different exciting talks about how the blind can see, about the non-stimulated regions in early visual cortex, and mistaking imagination for reality. A really wonderful session of all the talks that we have in this session. And the first talk will be by Atil. She is presently a postdoc researcher at UCL, and she is working with Professor Tim Behrens. And the work that she will be presenting is part of her PhD thesis done at the Weizmann Institute, Israel, with Professor Rafi Malish. Over to you, Atil.
Thank you. So let me share my screen with you. Whoop, not the right one. Can I go? Good. So hi, my name is Avital, and I'll be talking about how the blind see. Spontaneous brain activity underlies spontaneous perceptual behavior. So spontaneous brain activity is basically what happens in our brains when we do nothing. And we know quite a bit about it. We know it's ultra slow. We know it appears across the entire brain, but we don't yet know what its functional role is. One hypothesis brought forward was that spontaneous brain activity may underlie conscious cognitive behavior. So we usually think about our behavior as being evoked from some outside stimulus. For example, if you look at this purple pink thing here, this could be our stimulus. If we encounter it, then we would have some brain activity. And if it's sufficient, then it would cross some theoretical activation threshold. And then we would enter into an active mode. That is, we would show stimulus-related behavior. But it has been proposed that these very slow spontaneous fluctuations could occasionally cross this activation threshold. And by doing so, we would behave, but not because of some outside stimulus, but because of internal stimulation. This is what I will call unprompted behavior or spontaneous behavior. Now, it's very hard to really test whether spontaneous neural activity could underlie unprompted behavior for two reasons. The first is that you simply cannot ask participants to behave spontaneously, right? It loses all spontaneity. On the other hand, if you're looking at brain activity, then once participants behave, then their brain activity is not spontaneous anymore. It's task evoked. So to overcome these problems, we decided to study late blind individuals, because there is no external vision-evoked activity in their deprived visual cortex. So their visual cortex is activated spontaneously. But we chose those individuals that show very vivid visual hallucinations, as vivid as they used to see before. And because neither the appearance nor the content of these hallucinations is controlled by the participants, these are genuinely unprompted perceptual behaviors. Now, this condition is termed the Charles-Bonnet syndrome, CBS, and it's quite rare. but we managed to recruit 5 participants for our study. The first one hallucinates a face, a male face, that appears and disappears across her visual field. The second one sees vague faces that he describes as ghost-like or different patterns. And the third one sees still images of various objects and people. Now, these 3 participants can very accurately describe their hallucinations, both in the temporal and in the spatial domain. But we also recruited 2 more participants who couldn't give such an accurate report because their hallucinations actually spanned the entire visual field simultaneously and very rapidly. So one saw flashes of light and the other one saw patterns that looked like a kaleidoscope. We also recruited 11 late onset blind controls who have never hallucinated and 13 sighted controls. Now, what are the neural correlates of hallucinations in CBS? This has been previously studied, and previous work, for example, Fitch et al., have actually ascribed hallucinations in CBS to very focal activity in the visual system in an area near the fusiform gyrus. But if we think about the visual system, we know it's highly interconnected. And we know that at least when we see, then any activity that is sufficient to evoke vision doesn't really remain focal in one ROI in the brain, in one area in the brain. It spreads through the visual system. So unlike previous accounts of CBS, we first hypothesized that visual hallucinations, like vertical vision, would activate the entire visual hierarchy. Now, another controversy in the literature is that some studies have actually proposed that hallucinations in CBS are evoked from externally evoked stimulus. So they are evoked by the external environment. But this Fitch et al. Paper actually showed a slow buildup of activity before the onset of hallucination, which makes the possibility of this being triggered by the outside a bit tricky. So this actually aligns with our own hypothesis that spontaneous activity accumulates and brings about hallucinations. So we have another temporal hypothesis that hallucinations would differ from vertical vision in the spontaneous buildup of activity prior to perceptual events. Now, importantly, we actually hypothesized that this would happen across the entire visual system, not only in one part of the visual system. Now, to do this, we asked our CBS participants to give a verbal report of their hallucinations while their brains were being scanned in the MRI scanner. We know exactly when hallucinations occur, and we also recorded these reports because we played them back to the participants after being scanned, and we asked them to give as many details as they can about the content of these hallucinations. We then used these logs and descriptions to create simulated hallucinations, movies that represented the sighted controls in the MRI scanner, and we asked these controls to also describe what they see. Now, I'm going to give you some example of the hallucinatory streams that we created. This is the hallucinatory stream of the first participant who hallucinates a face. This one is of the second participant who sees patterns and ghost-like faces. And this belongs to the third participant who sees still images of various objects. Now, we have 2 experimental conditions. We have hallucinations, which are spontaneous vision, and we have veridical vision, where the vision is cued by stimuli. But these 2 conditions actually differ in another way, and that is that hallucinations are internally generated while veridical vision is externally generated. So to further isolate the spontaneous component of hallucinations, we introduced another condition, visual imagery. Because here the vision is cued. We tell participants when to visually imagine things, but the vision is internally generated. So again, across all these types of vision, we expect to find a very similar pattern of activity spanning the entire visual cortex. However, in the temporal domain, we expect that for the cued types of vision, first the stimulus or instruction would appear or be given, and only then the signal would rise. Whereas in the spontaneous type of vision in hallucinations, first the signal would rise and only then the hallucination would appear. So what do we see in the brain of CBS participants? Well, on the right, you can see an inflated brain, and on the left, just the flattened cortex. And you can see that these maps are not thresholded because I wanted to you to appreciate where we actually find activity. In red contours, you can see areas that are statistically significant and activated during hallucinations. They're also corrected for multiple comparisons. And you can see they nicely span the entire visual cortex. So hallucinations actually activate the entire visual cortex. Now, what happens during vertical vision in the simulated hallucinations? Well, we find more confined activation to the fovea, and this is probably because our stimulus had to be small enough to allow movement on the display screen, so we didn't really activate the periphery of the visual system. Nevertheless, if we superimpose these red contours of significant areas of hallucinations onto the controls activation map, we find some level of overlap. And if we actually correlate the patterns of activity between individual subjects, CBS or sighted controls when they see, we actually find a very significant level of overlap. So it seems that hallucination and vertical vision share some spatial components of activation. Now, this is again the hallucination map of CBS participants. And now let's compare it to visual imagery. This is visual imagery in the CBS participants. And again, you can see that we have a lot of activation in the visual system. And if we superimpose the hallucination contours on the imagery map, we find a very nice overlap. But this is a very small sample, so we can do a very good statistic on it. So because CBS comes from the blind population, then we can just look at the imagery map of the blind controls. And here again, you see a very similar map. And again, if we superimpose the hallucination contours onto this map, we find a very nice overlap that is also statistically significant. So it seems that hallucinations, like other types of vision, activate the entire visual hierarchy. Now, what about the temporal hypothesis? We thought that spontaneous activity would accumulate until hallucinations would appear. To test this, we chose 3 ROIs: early visual cortex, V1 to V4, the FFA, and the lip area. And the lip area is a control area because it is engaged in the task because of the report, but it's not part of the visual system. Now, here you see the onset of hallucination or stimulus. And the CBS participant in green, you can see that their signals actually rise before the hallucination appears, which is not the case for sighted controls in black, where first the stimulus appears and only then the signal rises. Now, importantly, this is unique to the hallucination condition because there is no group difference during imagery. We see a very similar effect for the FFA, although reduced in its amplitude. And importantly, there is no effect, no group difference for the lip area. So this effect is not only specific to hallucination in CBS, it's specific to the visual system of individuals with CBS. So hallucinations differ from other types of vision in the buildup of spontaneous activity prior to perceptual events. Now, as you can see, there is a difference in the level of effect between early visual cortex and FFA. So we wondered if this signal accumulation is uniform across the visual system. To understand this, we ranked visual areas from an atlas based on their position in the visual hierarchy. And we then correlated these ranks of ROIs with the time in which the signal rises relative to the onset of hallucinations in CBS participants. So the more negative you see a dot here, it means that the more preceding signal there is before hallucination. And as you can see, there is a very nice and significant correlation showing that the accumulation of signal is most pronounced in early visual cortex, and then it decays along the visual hierarchy. Now, you may wonder how we could measure such a thing using, given the sluggish nature of the bold signal. This is because, as I said before, spontaneous activity is ultra slow. So unlike visual evoked activity, we can actually see this using the bold signal. Importantly, this effect does not exist in the imagery condition in the CBS participant. So it's not some trait of the CBS brain. It is simply related to hallucinations. So anticipatory spontaneous activity decays along the visual hierarchy during hallucinations. Now let's sum up. Here we compared 3 types of vision. We had hallucinations in CBS, simulated hallucinations, vertical vision in sighted controls, and we had visual imagery in the blind. And we've shown that in the spatial domain, visual hallucinations, like other visual experiences, engage the entire visual system. However, in the temporal domain, only in the hallucination condition, there is a buildup of bold activity prior to hallucination onset. What we believe is happening here is that in the deprived visual cortex of CBS participants, and specifically in their early visual cortex, some spontaneous activity may occasionally cross some activation threshold. By doing so, it would activate the entire visual system by propagating through the entire hierarchy. And this, just like typical vision, would bring about the experience of vision. So in other words, spontaneous brain activity can evoke vision or perceptual behavior. And if so, it's tempting to think that perhaps spontaneous activity may drive other types of unprompted behavior. For example, when we close our eyes and go to sleep, our visual system is deprived, and therefore any spontaneous fluctuation in early visual cortex may propagate and ignite our visual system, thus bringing about the experience of visual dreams. I would like to thank my collaborators on this work, Meital Wilf, Boris Rossin, Marlene Berman, and Rafael Malach, the different funding agencies that support my work, and I want to thank you for listening.
Thank you very much, Avital. So, hi everyone, I'm your backup host, MC, for today. Nice to meet you all, and thank you very much for your talk. So we have many questions. I think we can take some online. So the first one is from Mohammad. What is the unit measure of signal accumulation? What exactly is accumulating in a given region?
So when I say accumulation, what I basically mean is the rise of the bold signal. So what we were measuring here is if a hallucinations appears in a certain point in time, whether we would see that the bold signal would rise prior to that hallucinatory event. So by hallucination, by accumulation, I basically mean the rise of the signal until its peak.
Perfect, thank you. Then we have another question from Haida. Did you see any differences between the people who experienced face hallucination versus lower level visual hallucinations, for example, in the FFA?
Yeah, so interestingly, across our CBS participants who had very different visual experiences, we still saw the entire visual system lighting up. We couldn't find any specificity of hallucination of activity to the content. So it's not as if faces, hallucinating faces activates the FFA more. That wasn't the case. So that seems to be something that is more general about hallucinations in CBS rather than stimulus or hallucination specific.
Thank you very much. Then we have a last question from Ariel. How similar, different are the reports of the Charles-Bonnet syndrome patients to other non-veridical hallucinations like dreams? Do you see the same neural activity patterns that you would for dreams?
So as far as I know, no one has actually managed to study dreams in the fMRI scanner. I can say that in comparison to other types of hallucinations, we have hallucinations in Parkinson's and in Alzheimer's disease. There are similarities and there are differences, but I think what we're looking at here is quite different because hallucinations in other conditions are evoked by some whole brain pathology, whereas here it's evoked by deprivation. So the visual system in these individuals is deprived and hence could act spontaneously. And I wouldn't expect to find a similar result or a similar type of activation in a sighted brain. As for dreams, that's a fascinating question. I'm afraid I don't know the answer for it.
Thank you very much. We have two more questions, but unfortunately we are run out of time. So I would kindly ask you, Avital, if you could type your answers in the Q&A and maybe the discussion can continue also offline. Thank you.
Thank you so much.
Very much. So we can stay in the visual field, but we will pass to our second speaker. She is Bianca Van K from the University of Glasgow. And so the floor is yours, Bianca.
Thank you. All right, let me share. Okay, yeah, so thanks everyone, welcome and thanks for joining my talk. So let me start by saying that as Helmut's already postulated more than a century ago, perception seems to be a process of inference, meaning that we're always trying to infer what was the most likely cause of our sensory input. So if I see something, I have some light hitting my retina and ultimately leading to some pattern of activation in my visual cortex. I'm trying to infer what was the cause of this sensation that I have. This is not always easy. First of all, we of course have a lot of noise in our signal transmission. So we have some noise in the sensory system, but also the sensory input itself might sometimes be noisy. or ambiguous. So for example, if I'm trying to talk to someone at a party with a lot of background noise, the auditory signal is not very clear. Or if I wake up in the middle of the night and I look in my dark bedroom, then this pile of clothes on my chair might suddenly look a lot like a person actually sitting there. So it's not always easy to infer what was the cause of what we are perceiving. So a special case of this is bistable perception. So here we have an ambiguous stimulus that has two possible interpretations and they can't be reconciled. And as a result, our perception fluctuates or alternates between the two possible interpretations. So there are some examples of these here. So on the left, for example, you see the Necker cube, which can be perceived as a cube with its front facing either towards the upper right or lower left, and you usually alternate between those two. Or in the middle, the phase-vase illusion, where you see two faces or a vase. And on the right, binocular rivalry, where each eye gets a different input and our perception alternates between the two different inputs. So it's thought that predictions play a large role in this. So we already know predictions really shape our perception, and it's thought that such predictions can actually help us decide which percept has to be chosen. So as already described here by having colleagues several years ago, there's this theory that we have predictive coding. So we have predictions shaping our perception, and that they play a certain role here in bistable perception. So in this example, we have binocular rivalry between a face and a house, and they both lead to some kind of bottom-up input. But we might have a prediction that the input must be caused by a face. And this prediction then has a strong influence on our perception. So it actually dominates our percept. So we actually perceive the face at this moment. And as a result, the prediction error of this input is very small because what we're seeing matches our prediction. But in contrast, then the prediction error elicited by this suppressed stimulus, or the stimulus that is currently suppressed, is getting larger and larger. So over time, this might tip the balance and favors the hypothesis that maybe the sensory input is actually instead caused by the house. Or if you want to put it in a more predictive coding or Bayesian perspective, if we have a bistable stimulus, like here the Necker cube, they both have an equal likelihood, but we might have a certain prior, so a certain belief that the input is likely caused by the second configuration. And these two combine then to create this posterior distribution that favors the second configuration, which is what we're currently perceiving. But predictions there keep on being fed back into our system and shaping our beliefs. They are used to update our beliefs in case we're wrong. So this increase in prediction error might then change our prior. So in other words, predictions really seem to play a huge role in this bistable perception. So how can we measure this? So we know already that there is a lot of feedback input going back to V1, and according to hierarchical predictive coding, such predictions arise from higher level areas, and they are fed back to lower level areas. And we know there's a lot of feedback connections that exist, and that would be the likely route where these predictions are being sent down. So how can we measure this with fMRI? One paradigm that has been used quite a lot now is the so-called occlusion paradigm, where you occlude a part of the scene, and as such you block bottom-up input from this particular region. So there is no bottom-up input in that region, in that area of the visual cortex that corresponds to that region. So if we see an activity here, this must be related to feedback activity, as there is no feed-forward information coming there. And as indeed has been shown here by Smith and Muckley, this particular region of cortex that's not directly stimulated actually contains a lot of information about the visual scene. So in this case, they could decode what visual scene was presented to the subject. Right, and as has later been shown as well, this was really suggestive of predictive signaling, because if we use high field fMRI, as in this case, 7 Tesla high field fMRI, we can actually see the different cortical layers. And as we know, feed forward arrives in middle layers, but feedback arrives in either the deeper or superficial layers. So as such, you can actually use fMRI to really figure out what information we're looking at. And as they could find here, these occluded regions or non-stimulated regions actually contain information in those feedback layers, supporting the idea that we're really looking at predictive information. So what we wanted to do in this study is use this method to address this idea of predictive signaling in bistable perception. So we were wondering, do such non-stimulated visual regions actually reflect the current contents of our conscious perception? So do we see predictive information in such non-stimulated regions that relate to our current perception? So in order to do that, we use these bistable plate stimuli that are contained of two gratings that are superimposed, and they were made bistable. So sometimes you would perceive the two gratings basically like sliding over each other in their respective directions. And sometimes you would see them integrated into one stable percept of a pattern moving towards one direction. So we had 4 different stimulus configurations. So overall pattern direction was either to the left or to the right, and the angle between the components was either 60 or 150 degrees. And crucially, we always occluded a part here of the scene. So participants were just watching this in the scanner, and they were reporting their perception during these stimuli. So then we ran some localizers. So we used standard retinal topic mapping to delineate the visual areas, and we used localizers for both the stimulated region, the non-stimulated region, and the border area to exclude any voxels that were in between stimulated and non-stimulated regions. We then ran linear classifiers to try and classify or decode the perception of these bistable stimuli. So here are just very briefly the results for the perception itself, just showing that these stimuli were indeed bistable and that we had fairly long phase durations, which is quite good for our fMRI analysis. And the fMRI results can actually be summarized in this just one figure. You can see here the decoding accuracy for each of the areas split up for stimulated and non-stimulated areas. And as you can see, we could decode perception here in all these regions. And it's important to stress here that the physical stimulus was always the same. It's really just your perception here that fluctuated or alternated between the two, and that is what we are decoding here. So we also had just here a control analysis where we exclude some runs with poor fixation performance as indicated by eye tracking. But as you can see, results don't really change much. We can still robustly decode these percepts. So this suggests that we have non-stimulated regions that actually contain here information about what we are currently perceiving. Question is, of course, where do these predictions come from? So a likely area in this case would be area V5, not just because it's motion sensitive, but also because it has been implicated in resolving such conflicts for bistable motion stimuli. So we did have some V5 localizer data for some of the participants. So we also decoded the percepts from this area. And as it might not be super surprising, you can actually decode this very well from V5 as well. Now, of course, I'm aware this does not prove that the predictions really originate in this area. It's just that if there's an area that generates such predictions, we should at least see a representation of those. And so this is just the first prerequisite that has to be met. So if I just want to summarize this all, what we see is that we have regions in early visual cortex that were not directly stimulated, so they did not receive any bottom-up input, but nonetheless, they contained information about the current percept during visual bistability, and we can decode this percept from fMRI signals. So this shows that they do not only contain information about the visual context, as has been shown by several previous studies, but also about the subjective interpretation of the stimulus, so what we decide to see in this stimulus. So this suggests the idea that we have predictive feedback signaling that is involved in our bistability, which is likely to arise from high areas such as V5. And with that, I would also just like to thank my collaborators and thank you for your attention.
Thank you very much, Bianca. Congratulations for your great talk and for your work. So let's see the questions from the audience. We have a first one from Thomas. What is the accuracy of the eye fixation versus the stimuli size? In other words, is it possible that the visible stimulus momentarily went into the non-stimulated retinal field?
Right, yeah, so that's the reason why we included eye tracking. It's indeed a good point, because of course we have to be very careful that we don't accidentally stimulate the region that we don't want to be stimulated. So that is why we had the eye tracking. So we located basically an area just around the fixation cross to identify if they were really fixating properly. And we had quite a large annulus around the fixation cross where you could still, where it was still allowed to fixate, so to say. And the accuracy was quite high. I don't have the exact number in my head, but I think it was something like 95% or something. So people were actually really very good at fixating. So we have good evidence that their non-stimulated region was indeed non-stimulated, but that's why we also had the control where we exclude some runs where people were not fixating enough. So there we have a criterion that if the fixation was outside this annulus for more than 5%, we exclude those runs. But we saw that the accuracy was still good. We could still decode from these regions. So I think in the end, we always have to be very careful. But yeah, we have the eye tracking to ensure this. And also the non-stimulated region was quite high up. So we also still had the border region in between. So even if you have a tiny shift, at least we exclude the voxels that are in between stimulated and non-stimulated regions.
Okay, I see. Thank you. Then we have a question from Minye. Do you have a negative control area where the decoding did not work?
Right. In this study, actually, we did not. But I would assume like that's something we could look at to have some area that's a completely different region. I would assume somewhere out of visual cortex where we could show that it's not possible. In the current study, we did not have this, no.
Thanks. Then we have a last question from Haida. If this is coming from V5, could you look to see if your decoder fails or not fails on the same trials for V5 and your main region of interest? If it is coming from V5, then this should be correlated.
Right. So if I understand correctly, this would suggest that if we decode from V5, we see how similar the pattern is from V5 compared to V1. That's how I understand the question. That's actually a good point. I haven't looked at this yet. This would actually be interesting because you would assume if the prediction comes from V5, that the pattern should be similar. So that's something we could do maybe to do a cross classification where we train on V5, for example, and test on V1 or vice versa. And I would assume that this works, but actually I haven't done that yet. So that might be an interesting point. Yeah, thanks.
Cool. It's always useful to have feedbacks and suggestions from the audience. Okay. Thank you very much again, Bianca, for your presentation. And I think it's time to move on with our last speaker for today. She is Nadina Dixa from the Wellcome Center for Human Neuroimaging. And please, Nadine, the floor is yours.
Thank you. Sorry, I don't have any cool fMRI data as my last two speakers do, so it's only behavioral, but I hope it's still going to be interesting. I'm going to talk to you today about a recent project that I did together with Matan Mazur, Peter Koch, and Steve Fleming about the influence of mental imagery on perceptual detection. Let me just get this done. Okay, so when we are walking down the street like this, we are bombarded with visual input. Our brain rapidly processes different shapes and textures and colors to create the visual experience that we perceive. But at the same time, we are often also caught up in thinking. We might, for example, remember the cool city trip that we went on way before COVID made international travel impossible, or the interesting lecture that we saw earlier that week during Neuromatch. And both of those processes are also accompanied by internally generated mental images. Now, various lines of research have shown that when we imagine a stimulus, similar neural representations in sensory areas become active as when we would actually see that stimulus in real life. And this neural overlap between imagery and perception has been shown using many different paradigms, stimuli, and techniques, so it's well established. But given that we often engage in mental imagery while actually also receiving external input, the question arises, does imagery actually influence our perception? Now, we tried to investigate this in this study using the following experimental design. So we asked participants to detect in a blockwise fashion left or right tilted gratings that gradually appeared in noise. So over time, the grating became more and more visible until about threshold. And every trial they had to indicate whether they did or did not see a stimulus there. So it was a simple detection task. And then we manipulated the imagery by just asking participants in some blocks to also imagine the stimulus that they were going to detect at the same time. So just to give you an idea of what this experiment looked like, I'm going to show you an example trial. So please form a mental image of this grating. So in the actual experiment, we didn't show the gratings, but I'm just going to show it to you so that it's easier to imagine. So form a mental image. Now keep imagining it as if the grating was still presented here in the square. Keep imagining the grating as vividly as you can. I think oh no, did you see the video? I don't think it worked, did it? There was a video. Anyway, so the grating was supposed to gradually ramp up, but I don't think it's working. Anyway, the idea would be that sometimes it's a bit difficult to then see whether there was actually a grating there or whether you just imagined it. So that's the idea. And then we analyzed these data using signal detection theory. I'm just going to give a quick recap of SDT for people who are not familiar with it. The idea is that we can categorize trials based on whether a stimulus was present or absent, and whether participants responded with, yes, there's a stimulus present, or no, there's no stimulus present. If people say yes when there also was a stimulus there, then that's a hit. If they say yes when there wasn't a stimulus there, that's a false alarm. If they say no when there was a stimulus there, it's a miss. And if they say no when there also wasn't a stimulus there, this is a correct rejection. And now based on the proportion of trials in each of these cells, we can calculate two main measures of perceptual detection. The first one is D prime, or perceptual detection sensitivity. And it's basically an unbiased measure of accuracy. So how well can someone separate signal from noise? And it's calculated based on the percentage of hits versus false alarms. The other measure is criterion C, and it's a measure of how likely someone is to say yes versus no, irrespective of whether a stimulus was present or not. So just the likelihood of saying yes, there's a stimulus there. And then we asked the question, how does mental imagery influence these different aspects of perceptual detection? So since it's a global pandemic, we collected our data online using Prolific, and we tried to ensure data quality using a few different measures. First of all, we staircase the perceptual threshold per participant. The idea would be that this would take into account some differences in lighting and viewing distance and screen resolution, etc. And then we remove participants if they had a detection accuracy below chance or above 95%, because that would indicate that the staircasing didn't really work. And then we also removed participants if they answered incorrectly the imagery check, because after every block we asked participants, hey, did you imagine a stimulus or not? And if they didn't answer these questions correctly, then that shows that they didn't really follow the instructions. So that was the idea. Now for the first experiment, we ended up with 96 good participants. So that's the good thing about online data collection. It's easy to get big samples. And I'm just going to show you first the D prime for both the no imagery and the imagery condition. Remember, the only difference between the imagery and the no imagery condition is whether or not people imagined the stimulus at the same time while they were detecting that stimulus. So we see that there's a slight decrease in D prime. It becomes clearer if I show you the pairwise subtraction here. So this is imagery minus no imagery blocks. And then you see that there's a significant decrease in D prime caused by imagery. So if people are imagining the stimulus, they are less good at externally detecting it. But we also saw an even clearer effect on criterion. So basically, when people are imagining the stimulus, they are more likely to say that an external stimulus is present than when they are not imagining it. We were thinking maybe that's an hallucination, yeah, but I'm going to come back to that later. So we see this increase in presence responses both for the false alarms. So they are more likely to say stimulus is there when there actually wasn't a stimulus there, but also for the hits. So they are also more likely to say stimulus is there when there also was a stimulus there when they are imagining. The effect on the false alarm is big. False alarms is bigger than the effect on hits, which is why we see an effect on D prime. Because theoretically, criterion and D prime are orthogonal. So you could have an increase in presence responses without actually changing your performance. But we see here that people are more likely to say a stimulus is there, especially when it's not there in real life. So we were thinking that maybe this was imagery being confused for perception. And then we were thinking that maybe we can also get the opposite. So maybe we can also get people to confuse their perception for imagery. So instead decreasing their presence responses. And we were thinking that maybe if people don't really expect that an external stimulus is going to be present, so maybe if they think it's very unlikely that there's going to be a stimulus present, then maybe in that case, they will attribute their sensory signals to imagination instead. So maybe if we manipulate the expectation of presence and absence, maybe then we can reverse this, this effect on criterion. So we did that in a second experiment, and we manipulated the expectation of presence and absence by changing the base rate of stimulus presentation. So in one condition, we only presented the stimulus in 20% of the trials, and in another condition in 80% of the trials. So in the 20% condition, people have a lower expectation of stimulus presence, right? Now, in this case, we didn't find any effect on D prime. So here I'm again showing you the difference between the imagery and no imagery blocks. But we again found a significant decrease in criterion in both the 20% and the 80% conditions. So this means that imagining a stimulus while at the same time detecting it just increases the probability of saying that the stimulus is present, irrespective of whether you expect stimulus presence or absence. But in both of these experiments, the imagined and the to be detected stimulus were always the same. So we always had asked people to imagine the same stimulus as the one that they had to detect, which means that we can't be sure whether this is a stimulus-specific effect. So if it's source confusion, then it should be stimulus-specific, right? Otherwise, it could just be that just general imagination increases people's likelihood to say something is there. So to check whether this is stimulus-specific, we ran a final experiment in which we also included an incongruent condition in which participants imagined a stimulus orthogonal to the one that they were detecting. So I'm just going to draw your attention first to the effect here on criterion. So we again see that for congruent imagery, we see a decrease in criterion, and this is now the third replication of this effect. But for incongruent imagery, we don't see such a decrease. So if people imagine a different stimulus, then they are not more likely to say that the stimulus is present. Now, if we look at D prime, we see the opposite effect. Now, similar to experiment 2, we don't find an effect on D prime for congruent imagery, but we find a decrease in D prime for incongruent imagery. And we think that that's probably due to the fact that imagining an orthogonal stimulus to the one that you're detecting is just more cognitively demanding. So that makes the detection task more difficult to do because it's just more effort. Now, we also looked at individual differences because there are large individual differences both in imagery ability and vividness, as well as in perceptual detection criterion and sensitivity. So we thought maybe these two things are related somehow. Maybe external detection and internal imagery do share. I mean, we know they share some neural mechanisms, and maybe they also share some behavioral effects. So we measured imagery ability using the VVIQ, the Vividness of Visual Imagery questionnaire, and we also measured hallucination proneness with an LHS questionnaire, and we correlated with everything and nothing. We didn't find anything, so everything was flat. All the correlations were 0, but we did find a very interesting correlation still. Thankfully. So we also asked participants to practice their imagery during this dynamic stimulus, because that's a bit weird, right? To imagine something while you're also looking at a dynamically changing stimulus. So we had a practice session before the main task started, and people were asked to rate their imagery vividness after each trial using a Likert scale. So we just had a very simple rating of vividness as well. And we found that this vividness rating correlated negatively with general perceptual detection criterion. So people with highly vivid imagery also have a lower detection criterion. So they are more likely to say a stimulus is present, and they are also more likely to say they have high imagery vividness. And importantly, this correlated in both conditions. So it wasn't that it was about the effect of imagery on detection, but it was really the general detection threshold correlated with imagery vividness. And we replicated this over all 3 experiments. So it seems to be a very robust correlation. All right, now to conclude, we found that imagining a stimulus while externally detecting that same stimulus, but not when you're detecting a different stimulus, increases the probability of reporting stimulus presence, irrespective of whether you expect stimulus presence or absence. And we can explain this by either a response effect or a sensory effect. So we cannot be sure which one it is based on these data. It's possible that just imagining the same stimulus increased people's probability of responding yes without actually changing their perception, right? We can't know that, whether it's just a response or a sensory effect. But given that we do know that imagery recruits low-level sensory areas and that it does change our visual experience, we think that it's unlikely to just be a response effect, but we need future research to fully dissociate these 2 explanations. Now, we also found that people with more vivid imagery have an increased tendency to report also the presence of external stimuli. This can also be explained as either a response effect or a sensory effect. So it could be that, for example, there's some common internal and external presence thresholds that varies between people. So it's just the kind of likelihood of saying something is there, whether it's imagined or real. Just, some people are more likely to say something is there than others. And this suggests that that would be shared for imagery and perception, which is interesting, I think. It could also be some kind of sensory effect, for example, that both detection threshold as well as imagery vividness relate to some sensory processing property like visual cortex excitability. So people with more excitable visual cortex maybe have more vivid imagery and also a lower detection criterion. That's also possible. So future research for that as well. But anyways, I think these results do show that imagery and perception are highly related, like more than we maybe even thought before, and that they can really influence each other. And it also shows that sometimes when we imagine something, the sensory activation generated internally can cross some kind of external threshold and can lead to imagery being confused for perception or hallucinations. Now, I'd like to thank you, and I'd like to thank my collaborators also. And yeah, that's it. Thanks.
Thank you very much, Nadine. Congratulations, very interesting work. And we have already 5 questions, so go directly to them. So Marcos said, thank you for the very interesting presentation, Nadine. Do you think the increase in bias and or in D will change with more biologically relevant stimuli, for example, faces?
I think that's a super interesting question, and I think future research is necessary, but my intuition would be that the increase would be lower because imagining more biologically relevant stimuli is more difficult. So I would just think that then the overlap between imagery and perception is lower so that you get just less strong effects. That's why we also picked ratings, because it's very easy to imagine them. So that's my intuition. I
see. Then a question from Ilya. Have you found anything beyond VVIQ which can be used to find people who are better at imagery? We used it at our lab and it's also didn't correlate with anything during 2 experiments.
No. Sorry, my answer is no. No, I mean, apparently Likert skill ratings work a bit better. I think if you have an imagery rating for the specific task that you're doing, then that usually works better, at least in my experience, because you have different kinds of imagery, right? And the VVIQ measures one kind, but then maybe measuring the specific imagery for your specific task is better. And you could also think about more objective methods like the Pearson binocular rivalry method, which aims to measure imagery ability more objectively.
And I think we have a follow-up question about this topic. So Heida asked, why do you think that your simple Likert scale works while the VVIQ is not correlated with anything? And were the Likert and the VVIQ not themselves correlated with each other?
So to answer your last question first, yes, they were correlated slightly, but not very convincingly. So I think it's maybe related to what Heida recently gave a talk, and she said maybe the VVIQ is just not very good to use different colorful language, but I think that's probably maybe something. But also what I just mentioned is that maybe you need to measure the specific kind of imagery that you're doing in that specific task. And maybe the VVIQ is just too general in that sense. Yeah.
Thank you. And then a brief detail for Rebecca. Did the participant get feedback?
Oh, no, they didn't. No,
okay,
which
okay.
I was thinking that maybe is a bit mean, because then maybe they think they are constantly hallucinating or something, but we didn't give them feedback. So. Yeah.
Perfect. Then we have a question from Jacob. Would the measure of suggestibility be useful to determine whether your findings are due to a response bias or sensory effect?
Yeah, I think that's a very good question, and I think it relates to the recent discussion on the rubber hand illusion. So we are thinking about that now, about how to dissociate these different explanations. Yeah, thanks.
Perfect. So I think we can wrap up this this session. We have seen 3 wonderful talks about our visual system, our imagination, and so I would like to thank our speakers, Avital, Bianca, and Nadine, for being with us, and also to all the attendees who asked very nice and interesting questions. And I've seen that there have been also some kind of discussions in the Q&A, so that was very cool. And So I just want to thank you again for being here and enjoy the rest of the Neuromatch Conference 3.0. Bye.
I was just curious, are these YouTube streams, will they be recorded and available later, or are they only streaming?
We're going to, at the moment, the YouTube streams are available later, but not broken into individual sessions. We are also recording the Zoom streams, which are going to be better quality and blah, blah. And that's what we're going to make available as like the definitive.
Okay, beautiful.
But we'll do that probably next week. Cool, all right. So it's 12 o'clock. All right, so we're fully live and broadcasting, right?
Right.
Excellent. All right, so welcome everyone to this session. I'm covering for the MC who was supposed to be hosting this session, who lost internet, who lost electricity actually, even more extremely than using internet. So actually, I'm mostly doing hearing research, but this session is not about that. It's all about vision. It's specifically seems to be all about eye movements. And so we've got 3 cool talks coming up. We've got one on virtual reality. We have one on eye movements in the blind, and another one on eye movements while driving. So it's a pretty cool session on eye movements, if that's your thing. All right, so let's kick off with I think it's Ashima Kashava, who's going to talk about some eye movements and virtual reality stuff. Brilliant. All right. Ashima, do you want to unmute yourself and go for it?
Perfect, thank you. So I'll share my screen now.
Yes, that would be great, yeah.
Do you see the panel underneath?
We don't see we just see at the moment, we're just seeing your like web browser.
Oh, perfect, okay.
We don't see, it's not full screen yet.
Yeah?
Okay, now it's full screen, yeah. And we can see the panel, yes.
I'd like to get rid of, okay, perfect. Okay, welcome everyone. Thank you for attending my talk. I'll be talking about preparatory eye movements that reveal prior knowledge and intended interaction in virtual reality. This is a project that I started this year with Nina Gochevsky, Fabert Nizami, and my lab supervisor, Peter Koenig at the University of Osnabrück. Okay, so what is the motivation of my study? So in everyday tasks, eye movements have been found to be primarily driven by top-down factors such as task relevance and less by saliency. For example, in the Land and Hayhoe paper in 2001, they did a sandwich making task with subjects, and subjects fixated on only task relevant objects such as the bread, the jar, the knife that was used to spread the jelly. So they concluded that only task relevant objects are fixated on during a task. Furthermore, eye movements are also used to extract visual information in a goal-oriented way. For example, in the Bellardinelli study from 2015, they studied how subjects would fixate differently when asked to lift an object versus when asked to open the lid of the object. So when the subjects were asked to lift the object, their fixations were more centered towards the center of gravity of the object, so like so. And when asked to open the lid, subjects fixated more towards the location where the action was supposed to happen. So they concluded that fixations are goal-oriented, and these anticipatory fixations also reveal the intended interaction of the subject. And so here we ask how eye movements extract information from unfamiliar objects when prior knowledge is not available to the subject. So this is my experiment design. The experiment takes place in virtual reality. We have a 2x2x2 within subject design with factors task, familiarity, and orientation. In each trial, the subject has to interact with a virtual tool, either by lifting it or using it. Use would be pantomiming the use. I'll show you an example of how this interaction looks like. We have 12 tools in total, 6 of which were familiar and 6 were unfamiliar to the subjects.
The handle of the tool was oriented either to the left or the right-hand side, which corresponded to the factor orientation. In total, we measured, we had 144 trials per subject over 6 blocks. The task orientation and the tools were counterbalanced so that we had equal number across participants. We measured 18 participants. I wanted to measure more, but because of Corona, it was not really possible. And we measured these participants in a simulated environment using HTC Vive Pro I. And we tried to assess the naturalistic gaze behavior using these 3 factors. This is how the VR environment looked like. So this is the HTC Vive setup, where the head-mounted display is set up before the experiment. The interpupillary distance is calibrated to the participant. This is the calibration phase, where subjects are shown 4 dots. And after the calibration is successful, the simulated environment starts. This blue dot is used for validation to check that the calibration error is less than 1 degree. If the calibration error was more, we had to do the calibration again. And now the experiment starts. So this is a virtual hand that was used that was shown to the subjects. This corresponded to the real hand. So this is a use condition where a tool is presented, a beep is given to the subjects, which corresponds to the go cue, and subjects can press the button to get on to the next trial. Here, a spatula is shown, the subject can lift it, go on to the next trial, the same tool in a different orientation. And so on. So these are the 12 different tools that we use. The familiar ones would be, should ideally be familiar to you. These are everyday objects that you might use. And in the unfamiliar tools, for example, this is a lemon zester, which subjects don't really know, are not really familiar with. This is a spoke wrench, which is used for bicycle repair. So if you are a repairman, you would know this tool, but our subjects did not. And this is a daisy cutter, which is used for gardening. All of these tools had predefined regions of interest. So here we had a collider on the effector part of the tool, which was pre-made before the experiment. And here on the right side, we have the handle, the collider over the handle, which is our region of interest for the handle. And a questionnaire was also administered to the subjects after the experiment to assess the familiarity ratings, subject-specific familiarity ratings for each tool. Our hypothesis was in the use condition, more fixations would be on the effector of the tool, while in the lift condition, more fixations would be on the handle of the tool. For the unfamiliar tools, more fixations on the effector, and these would be, and fewer fixations on the familiar tools. And in the use condition with unfamiliar tools, there'll be more fixations on the effector compared to familiar tools. And the orientation of tools would elicit more fixations on the handle for both tasks due to the incongruence of the grasping direction. So this is how we analyzed the data. We studied the fixations made before the go cue, before the beep, and we modeled these fixations as log odds of fixations on the effector compared to the fixations on the handle using a linear mixed effects model. So this is how our model looks like. We have the probability of fixation on the effector divided by probability of fixation on the handle and the log of this. And this was dependent on the task familiarity orientation with a random slope and intercept over subject and a random intercept over our items, which is the tool. All our categorical variables were effect coded, so they were not dummy coded as in 0, 1, they were effect coded to minus 0.5 and 0.5. And here we ask, how do familiarity, task, and orientation affect the fixations on the effector? This is the data that we have. So on the y-axis, you have the log odds on the effector. Values above 0 would indicate the odds of fixations on the effector, the odds of fixations of being on the effector, whereas values under 0 would be the odds of more odds of fixations on the handle. In the familiar condition, we see that in the lift task, the fixations are mostly on the handle for both the left and the right orientation. And in the use task, there are more fixations on the effector, but slightly, so the odds are slightly towards the effector, but not as much for when the tool is presented with the handle on the left side. In the unfamiliar condition, there were the fixations were more towards the effector in general. And in the use condition of unfamiliar tools, there were higher odds of fixations on the effector part of the tool for both the left and the right orientation of the tools. This is what our linear mixed effects model revealed. So in the use condition, the odds of fixation on the effector is higher, and this is significant. For unfamiliar tools, the odds of fixations were very much on the effector, and there was no significant effect of orientation when the handle was presented on the left side. In the use condition and the unfamiliar, in the use condition for unfamiliar tools, there are a higher number of fixations on the effector part of the tool, and this was significant as well. For the use condition, when the handle was presented on the left side, there was a marginal effect of the fixations being more towards the handle. For unfamiliar tools presented with the handle on the left side, as well as for use unfamiliar on the left side, the coefficients were not significant. So in conclusion, we can say that preparatory gaze strategies differ for a given task, in this case, use or lift. Unfamiliar tools elicit more fixations as a way of extracting the mechanical properties of the object, because the affordance of the object is not directly known, so it has to be inferred. This strategy is exaggerated when using an unfamiliar tool. And the orientation of unfamiliar tools marginally affects these preparatory gaze, but not significantly. And in conclusion, we can say that eye movements reveal prior knowledge and intended interaction with an object in VR. And with that, thank you for your attention.
All right, thank you, Ashima. Okay, we have a couple of questions just coming in right now, actually, which is cool. So the first question is just a quick one, I think. Were your subjects right-handed?
Yes, we made sure that all our subjects were right-handed, because it wouldn't make sense if the handle orientation was incongruent.
Right. Yeah, that makes sense. So Lewis is asking, so more a suggestion, unless it's a question. Why did you code for left-right relative to the user's orientation and not in terms of handedness congruence?
So it's easier to get right-handed participants for one, so we just had congruent to the handedness basically. So the handle on the right side would be congruent to a right-handed person, and a handle on the left side would be incongruent.
Okay, yeah.
Mm-hmm.
I have a couple of sort of more general questions, but do any of the other panelists want to knock in and ask a question actually at this point? If so, just go ahead and unmute yourself. No, not particularly. Okay, so I'll ask some of my more general, naive questions in that case.
Yes, please.
So what I was wondering actually is, could it, so in your virtual environment, it's quite a relatively simple, right? Sort of flat shaded, not many objects. Could it be that the way people handle sort of more realistic environments, which is much sort of busier visually, could be different from what they would be in such a simple environment?
So I am running a follow-up experiment with more textured environment where it's more natural. It looks like you are on a workbench, you're working with a workbench, you have more wooden textures, the tools are much more real looking, and we have the interactions that are used not with the controller of the HTC Vive, but with leap motion. So leap motion would be that you do not have a controller in your hand is rendered naturally in the environment. So even very small finger movements could be rendered in VR. And we want to see now if this heightened immersion can cause either a breakdown of this effect, or how does it affect the results for us. Okay. But it's in progress, and hopefully if we don't have another lockdown, we should be able to have some participants.
Yeah. Well, actually, I have a follow-up on that, but since we've got another question from the audience coming in, I think I'll ask that one instead. So, so Lewis asks, could you expand on your experience with eye tracking in VR and how that restricted your potential inferences with regards to this topic of preparatory responses to objects?
So eye tracking in VR is messy, of course. As you saw in the example, there are head movements, so you have to account for differentiated velocities in the eye. We found that using median absolute deviation based fixation detection to be quite useful for us, because the eye movement data is quite noisy to begin with. And that helps us in a data-driven approach to fixation detection. But I'm not sure if it restricted our potential inferences. We do check all of the fixations per trial by hand and see if it makes sense. There is some amount of pre-processing, more than in a particular lab experiment that we have to do for VR eye tracking. But yeah, I hope that answers your question, Lewis.
Okay, that's great. All right, so I think we'll have to call it a day there for this session. Thank you again very much.
Thank you.
That was a great talk and really interesting to see VR being used like this. All right, so next up we have Paul Zer, who's going to tell us about eye movements in the blind, I think. So yeah, Paul, take it away. Oh, you're muted, by the way, Paul. So.
Okay, here we go.
Yeah, there we go.
Okay. Hi, everyone. I will present a study that we did in collaboration with the University of Hamburg and the LV Prasad Eye Institute in Hyderabad, India, where we essentially investigated the eye movements inside recovered total cataract patients. So I'd like to say a quick word about this institute. So it's a really fantastic place. It's very progressive. So one thing that's really nice is that if you're if you're poor and you come to this institute and you say, well, I'm poor, I cannot pay for my eye care. So it's a hospital and research institute, and if you cannot pay for your eye care, you will be given it for free. So all the way up to cataract operations, lens implants, corneal implants. So and I had the honor of being there for about 8 months to collect data on congenital dense total bilateral cataract patients. So these people had total cataracts from birth. And the longest time they had these cataracts prior to cataract operation was 36 years. So they range from 1 to 36 years, during which these people had total absence of pattern vision. So this population is very interesting because we know that there's sensitive periods in the visual system for things like face processing, global motion perception, multisensory speech perception, visual acuity. So these functions never fully recover if you haven't had vision for the first year of the first months of your life. But surprisingly little is known about oculomotor control, which arguably is underlying a lot of visual system functions. What is known is that in the congenitally blind and no voluntary eye movements exist. But in some cases, people who are blind can recover sight, for instance, during a cataract operation. And so there's also some mixed evidence from monkey and cat studies, where some studies saying, well, some oculomotor control recovers, some studies saying it doesn't. One thing that is quite well established that, well, if you cannot see, or even if you have bad vision during the first months of your life, you'll have nystagmus, which is these oscillatory eye movements in your fixations. So we did this very simple study after arranging all the logistics and setting up an eye tracking lab. So we showed people as targets on a screen. The targets would move around at unpredictable intervals, and we investigated these basic visually guided saccades. Here we have a normally sighted control. At the top, we see a eye movement profile and velocity profile, and at the bottom, we see the eye movement trace. So this is what we would expect. These are normal saccade and corrective saccade. At the right, we have a congenital cataract patient after the operation, so at least 1 year after the operation. And what we see is, okay, they do actually sort of go from fixation to the target, but not really in the way that we would expect. And so this already shows you why maybe there's not so much research in humans in this regard, because it's very difficult to analyze these eye movements. So here, 3 other examples of eye movements of single trials, essentially, and you can already see. All right, this is tricky. How do we even analyze that? So after trying many different very complicated analyses, I realized that okay, we can actually just measure the distance of gaze from fixation from the target. So the distance from the target we have here in black. At some point it sort of goes up, and the distance to the target goes down. Now, what we see is that for basically all of these eye movements, there is this point somewhere where these where this black and red line crosses. And this is essentially the point where the gaze is closer to the saccade target than it is to the fixation. And this is already a very straightforward way of saying, okay, this eye movement was successful. I mean, you moved closer to the target from fixation. Now we can split the eye movement in 2 axes. So the targets were presented randomly, and what we can see is, okay, at some point this line that indicates the middle between the target and fixation, this is crossed at some point. And if I plot essentially eye movements orthogonal to the fixation target axis and parallel to the target axis, we see over about 100 trials this kind of pattern emerge. So if we take the median for each time point, 0 being aligned to the crossing of the midpoint, we see that overall, on average, eye movements are successful. So this is for a single subject. We can now take the median line for each of our 9 subjects, and we see that overall, yeah, this group is doing fairly well. We had a nystagmus control group, so people who also had this severe nystagmus, and you can already see, well, it looks fairly similar to this nystagmus control group. So they never had cataracts, they just have nystagmus. And then we have a developmental cataract control group, which, yeah, so they had cataracts, but later in life, so not from birth. They had vision during the first year of life. And we see, okay, they're doing a lot better, and they're fairly close to our sighted controls. And so what we can see here already is that, well, our congenital cataract subjects, well, they're not doing as well as your sighted control subjects, but they're not really doing worse than on the nystagmus controls. So this is pretty nice to see, meaning that even if you have been essentially blind for 36 years and you get to see patterns, targets, for the first time, your eye movements will still recover. So we can basically quantify the number, the proportion of eye movements that contained a midpoint, so where they were crossing this midline, and we see that, okay, so it's worse in the congenital cataract and nystagmus groups, but not that bad overall. At least half of these visually guided eye movements were successful. Of these successful eye movements in the congenital cataract group, about a bit more than 75% on average contained saccades that could actually be classified as saccades. Now we wanted to go a step further and say, okay, so now if I take the difference between the black and the red line here, I get a singular measure, which is essentially the difference between distances from the fixation and saccade target. And I can provide, okay, so this is sort of a model what this would look like. So we have a color grading here. We see that this ratio between the distances is first sort of further away from the target and moves towards the target, and then you have here sort of these nystagmus curves going on. So but what you see also in the color in this graph down here is that in this trial they sort of moved towards the target. Now I can provide some cutoffs, let's say 5% from the total value, and that allows me to define a saccade or eye movement start and end point. So a big problem in all nystagmus eye movements is if you want to classify those, well, if you go by the classical definition, which works in most other cases, fixations and saccades, you're missing a lot of trials. Like in this trial, for instance, you would just, you have to exclude this trial, but clearly this person moved from fixation to the target. So here's a different way of defining a eye movement start and end point. And if we do that, if you have a start and end point, we can define things like latency. We can analyze latency. So with some Bayesian estimation here, and what we see is that latency, so latency to start the eye movement, not just simply saccade latency, which is typically a lot lower. So in nystagmus patients, you usually see a much lower latency if you just go by saccade latency. But here we see that there's, well, not really much of a difference to the nystagmus control group, and really not much of a difference to even the sighted controls. So the developmental cataract group is a bit of an oddball here, but the important message here is that, well, the latency to actually begin eye movement is not that bad. Total durations are longer than in the normally sighted controls, but not longer than in the nystagmus controls. So, and this is sort of a pattern that repeats. Well, of course, these eye movements are going to be longer, but that's because of the nystagmus. Endpoint error, similar pattern, so somewhat worse, but not that bad at all. So about one degree on average in the congenital cataract group. If you look at the total fixation area, again pretty high. So in the nystagmus, your eye movements are going to be all over the place, but not higher than in the nystagmus control group. Saccade velocity, saccade peak velocity is lower than in all other groups, which so far is somewhat unexplained. So it's not a function of saccade amplitude, because some saccade amplitudes are not that much lower. But yeah, so overall, we see a really remarkable recovery of eye movements. As a take-home message, I would say that especially in atypical populations, we should be very careful how we define eye movements, because the classical definition of fixations and saccades does not always work so well, or it's not really an adequate description. Generally, for most parameters, eye movements in congenital cataract patients are indistinguishable from other nystagmus patients, and this is consistent with other studies indicating robustness of low-level functions. Yeah, so this paper's out. You can just have a look, and here's my email if you have any questions, or you can ask them now if we still have time.
Great, thank you, Paul. Yeah, we have a couple of questions already come in from Lewis, who is asking all of the questions today. So come on, everyone else, ask some questions. Don't just leave it to Lewis. So Lewis is saying, maybe I wasn't paying attention. Did Paul already explain the calibration validation procedures across participant groups, and if this was comparable, if at all?
Yeah, sorry, I didn't really go into detail here so much. So what we did was essentially do sort of an iterative process. This is explained in detail in the paper. So if you're interested in calibration for any kind of nystagmus eye movements, have a look at the paper. But briefly, we're looking at the sort of start and endpoints. We're using this a default calibration. So this is what's usually done in nystagmus eye movement research. You just put somebody else on the screen. You have like very, very, very rough calibration. And then we were looking at the endpoints of each of our trials. And we're then refining the calibration, reanalyzing everything, finding new endpoints, and doing sort of this iterative process where we sort of were optimizing for endpoints. Now we're doing this in a cross-validation, so that there was no sort of circularity in that argument, and that worked fairly well. But again, this it's a bit of a longer procedure to explain. So if you are interested in that, send me an email or have a look at the paper.
Cool. All right. Oh, we've got just one more just come in quickly from someone else, so I'll prioritize that one. So, Paul, have you ever measured their visual acuity before measuring the eye movement? Do they actually see the target in the visual periphery before making the saccade or not?
I would have loved to, but I mean, it's quite delicate, the situation in this institute. So it's very difficult to get these subjects after their operation at all, because they often come from very far away villages, kind of thing. So we do want to do that as well. We want to do sort of longitudinal studies essentially, but this will just take a lot longer, I think. So what is known is that some have some fixation to on light. So if you shine a very bright light, they have some basic let's say you could call it rudimentary eye movement control. These are sort of clinical observations of these patients. But what's important to keep in mind is that the vision is like you would be looking through like a bread paper kind of thing. So it's milky, and there's no way to actually fixate a particular target unless you shine a very bright light. So some eye movement control exists, but it's very rudimentary. But it will take time to establish that more formally. But it's a very important question. I agree.
Great, thank you, Paul. We have some more questions, and if you want, you can go into the Q&A and give your answers during the next talk. It would be great, or in the chat. But we better move on to the next talk now, because I think we're already running a little bit behind. So okay, thank you again, Paul. Right, so our last talk is from Laura Mikula, and she's going to talk to us about eye movements while driving. So yeah, take it away, Laura.
Okay, forgot to unmute myself. So today I'm going to talk to you about some work that I've been doing for the past year at the University of Montreal. And I'm going to talk about how we can use dynamic analysis of eye and head movement to estimate visual and cognitive demands while driving. So when we're driving, there's a complex interaction between vision and cognition. So for example, imagine yourself driving while you have your vision blurred, and you also have to multitask when you're in your car. Because our mental resources are limited, the inability to meet visual and cognitive needs can actually affect your driving behavior. It can have detrimental effects on road safety. Furthermore, it has been shown that eye and head movement contribute to attention allocation, and they can be modulated by the quality of vision and the cognitive load. So that's why in the study, our question was to see if eye and head movements were modulated and therefore be markers of increased visual and cognitive demands. So in order to do that, we had 21 young participants coming into our lab, and they were in a driving simulator, and they were doing quite a simple driving task where they were on a highway, and we asked them to maintain a speed of 90 km/h as accurately as possible. And I will refer to this as our single task because on some occasion on the GPS screen, some picture will appear with road signs, and we asked participants to report the number associated with the city of Montreal while still doing their driving task. So it's their double task that they have to do. So we used within subject design. So each of our 21 participants did 2 driving sessions. One session with optimal vision. So it means that we made sure that their vision was at least 20/20. And they also completed a second session where they had to wear contact lenses that are going to be perturbing their vision. And we measure that as a reduction in visual acuity. So we have half of the participants with a lower visual degradation, where the visual acuity is estimated to be 20/50. Whereas for the other half of the participants, they had a much higher degradation, where their visual acuity is estimated to be around there. In our participants, we also measured eye and head movement in 2 axes. So the yaw axis will be left to right rotations, and the pitch axis will be up and down rotations. So first off, I'm gonna present you the driving behavior of our participants to see how the driving was affected by the cognitive load and the visual degradation. So I'm presenting 2 driving parameters, which are the variability in the driving speed here and the variability in the car lateral position. So basically these 2 measures are going to tell us how the participants are stable in their speed and in their position relative to the middle of the road. So we ran a three-way ANOVA, and we found that for both driving parameters, there was an effect of the cognitive load. So it means that in general, participants were more variable when they were doing the double task, as shown as triangles here, compared to when they were doing the single task, so when they had to just maintain their speed. Then for the driving speed, we found a main effect of the visual degradation, which means that participants were overall more variable in their speed when vision was degraded as compared to when vision was optimal. And then we didn't find any main effect of the experimental group, so no significant difference between the lower and the higher degradation groups in any of the driving parameters. So then we move on to look at some visual exploration parameters that are classically used in the literature. And here I'm showing you the gaze distribution in the vertical and in the horizontal axis. This is for all participants in the optimal vision condition and in the degraded vision condition. And as you can see here, there's not much of a difference between these two conditions. And this was further confirmed when we looked at the variability of the gaze position in the horizontal and in the vertical axis. There was no significant difference between the degraded condition compared to the optimal condition. And again, we didn't find any differences between the lower and the higher degradation groups. It was also similar for fixation duration, which is another parameter that is commonly used in previous studies. So it was quite surprising to us that we didn't find any differences. So we move on to some more dynamic analysis of eye and head movement. And to do that, you can use the entropy. So it's a measure that has been used in previous studies about driving, but also aviation. I won't go into the details of how it is calculated, but the thing to remember to know is that the entropy is going to estimate the randomness or the predictability in your eye movement scanning pattern. And generally with a higher entropy, you have more of an exploratory behavior. And when the entropy is low, it's generally associated with more stereotyped movements. So we calculated the eye entropy for every participant in both optimal and degraded vision condition. And we found an effect of the visual degradation. So the eye entropy was reduced when vision was degraded compared to when vision was optimal. But again, here we didn't find any differences between the two experimental groups. And finally, the last measure that I'm going to talk about is the eye-head coordination. And here I'm just presenting the results for the yaw rotation, so the movements in the horizontal axis. And here what you can see in these subplots is that we have the head in space rotation plotted as a function of the eye in head rotation. And we did that for both experimental groups and both optimal and degraded vision condition. So basically, when you're doing the regression between the head rotation and the eye rotation, it's going to tell you how much the head is contributing to gaze shifts. So if the slope of the linear regression is close to 0, it means that the head is not contributing much and only the eyes are contributing to your gaze shifts. However, if the slope is very close to -1, it means that your eye rotation is counteracted by your head rotation. So it means that if your eyes are 50 degrees towards the right, your head is going to be 50 degrees in the opposite direction. And as a result, your gaze will remain somewhere around 0, 0, so around the center. So we did the linear regression for each participants, and we compared the slopes. And the red line that you see here is the average slope of the linear regression. So we did in ANOVA, and we found that there was a significant main effect of the visual degradation, but no significant main effect, the main difference between the two groups. So basically, when the vision is degraded, the slopes are steeper and closer to -1. So it suggests that when vision is degraded, the head is contributing more to gaze shifts. So in conclusion, what we have shown is that the driving behavior and some of the most commonly used visual exploration parameters were rather insensitive to our particular visual degradation. But in contrast, the dynamic visual exploration and the eye-head coordination were somewhat impacted by the visual degradation in this condition where the cognitive load is high. So it suggests that the dynamic analysis of eye and head movement could be used as indicator to estimate visual cognitive demands during more naturalistic tasks, just like driving. And with that, I would like to thank you all for your attention, and I'm happy to take some questions.
That's great. Thank you, Laura. I feel like this throws up a ton of questions. The first one that occurs to me, is this something that could be used by like policymakers to set what the rules should be for what devices you're allowed in cars, or is it not quite well enough developed yet to be at that stage?
It's difficult to do right now, but yeah, the idea with this study was also to see if we can see when, like to see the visual scanning pattern of the participants and kind of try to extract when maybe it could be dangerous.
Yeah.
Yeah. But it's not at the point where it can be used right now.
Right. Yeah, as I was watching, I was thinking there's a load of like things that you could start testing with this, like certain types of devices or certain positions that you put devices more distracting or not than others, and all sorts of things. If you had a good measure that correlated with, I guess, how safe people's driving were and things like that.
Yeah, because the thing is, when you're using in-vehicle displays, it can actually have an impact on your cognitive resources. So you have less cognitive resources to process the visual scene and the roads. So yeah, that was the idea here.
Okay, actually, loads of questions have come in, so I'm going to stop asking my questions and start asking some from the audience. Okay, so we have so Laura, great talk and excellent visualizations. I'm curious, which gaze tracker did you use to obtain both eye and head movements?
So the eye tracker that we used was a portable one. So you have kind of some glasses without the lenses that the participants are putting. So it's going to record your eye movements. And we also have kind of a headset that participants are wearing, and they have some reflective markers. So it's going to track the markers just like you will do when you're doing motion capture with hand movements, for example. So we kind of combine these two techniques, and we were doing some calibration for the head movement, the eye movement, so that we can have a recording for the eye, for the head, and then we can reconstruct also the gaze rotation in the space.
Cool. There was a follow-up second question to that, which was, did you perform any temporal analyses close to when the stimulus appeared on the GPS?
We didn't do that. Actually, a thing that I didn't mention is that generally the entropy that I presented, it's more spatial based. So basically you will divide your visual scene into some region of interest, and you will look at the visual scanning pattern. But here we didn't want to be dependent on the visual scene because it's going to change a lot with just when you're driving. So with the entropy that I presented here, we looked at the entropy over time.
Cool. Okay. I think we have to finish there because I think we're going to get cut off in like 1 minute. So I better quickly wrap up and say thank you again, Laura, and thank you to all the speakers in the sessions. I certainly learned a ton about eye movements today. I hope everyone found that equally exciting as I did. So yeah, thank you again. For all of you, I think that there were unanswered questions left in the chat. To other participants, please go ahead and email the speakers or ask them your questions on Twitter or wherever is appropriate to follow up on those. Right, well, thank you very much. Thank you, everyone.
Thank you.
Thank you.
Okay, all right. Hello, everyone, and welcome to this session, which is going to be all about decisions, perception, evidence accumulation, and lots of cool stuff like that. We've got 3 very cool talks coming up for you, and I think we should just jump straight into them, actually. Our first talk is from Zara Aizi, who's going to talk to us about perceptual decisions in discrete and continuous environments. So yeah, Zara, can you unmute yourself and take it away?
Yeah, and thank you, Dan. And I will share my presentation. Here it is, and sorry, let me see all the screens. So I will talk about accuracy, confidence, and reaction time on perceptual decision in discrete versus continuous environment. I am Zara Aizi, a PhD student in cognitive modeling at Institute of Cognitive Studies, Iran. As I was introducing myself, maybe some of you noticed this video showing multiple short RDM, random dot motion cues. And if you have noticed that, your brain might integrate the information from all the cues to at least decision about the direction of the RDM. And maybe also you feel more confident as the time passed. Previous studies has shown that gaps in sensory information do not affect performance, and participants are able to accumulate evidence from discrete cues to improve their performance even better than the prediction. Besides, in perceptual decision making, it's known that there is a positive relation between accuracy and confidence. And here we want to see that our participants how accumulate the evidence to report their confidence when they receive separate cues of informations. We use signal detection theory as a methodology to study observers' ability to report decision and confidence too. And in addition to implicit confidence reporting, explicit confidence reporting, we might use some implicit indicator or measures to see how confidence works in our task. For example, it's known that there is a reverse relationship between the reaction time and confidence, and some neural indicator like EEG can provide these indicators. For example, the centroparietal positivity component, CPP, can known to be related to both evidence accumulation and evidence. Here, we want to study the decision parameters and see how they alter when participants receive discrete queues of information. The way we do that is to implement an RDM, a discrete type of RDM. We have we want our participants to decide about the direction of dots based on just one pulse of motion, random dot motion, or two pulse of random dot motion. The gap between the two pulse in double pulse trials is selected from these values, and the coherence selected from these values. And in single pulse trials, we have these values to values of coherence. It's notable that our targets are gradient rectangle, which we ask the subjects to indicate their response by directing their gaze toward one of the targets, and if they choose upper extreme of the target, it means that they are confident, and if they are choose the extreme lower part, it means that they are just guessing. We have 16 subjects, 4 of them just perform behavioral tasks extensively, and we have recorded EEG from 12 subjects. As you can see here, in single pulse trials, coherence, accuracy, and confidence improve based off motion strengths. Although the pulse was very short and the information was very limited. In the double pulse trial, we can see something like that too, that accuracy and confidence improve when the accuracy, when the coherence of pulses increase. And from these two figures, you can see that in the accuracy and confidence were invariant to inter-pulse intervals. So to address to address the accuracy variation in double pulse comparing to single pulse trials, we take the accuracy of each single pulse coherence as baseline and measure the variation of accuracy compared to each corresponding single pulse. And as you can see, in all sequence of our double pulse, the accuracy improved meaningfully. But we, when we did the same process for confidence, we can see that just in some of the sequence, we can see this improvement. As I mentioned before, confidence and accuracy has a strong positive relation with each other. So we separate correct trials and incorrect trials and do the same analysis for both of the groups. Considering just correct trials, you can see that the improvements in confidence reporting can be more meaningful. But interestingly, in incorrect trials, in all sequences, you can see that the confidence decrease, even as participants receive an extra pulse of information. And this is in line with the concept of metacognition sensitivity, which predict that incorrect response are with lower confidence and correct response are with higher confidence. So to study metacognition sensitivity, we use signal detection theory. As you know, D prime is evidence sensitivity and is related to performance, task performance. And we have meta D prime, which is related to metacognition sensitivity. We compare these two output D prime and meta D prime in single pulse versus double pulse trial. And as you can see here, D prime in both of them, there is significant difference. In short, it seems that a participant used the extra pulse of information to adjust their confidence rather than just increase their confidence, report confidence. So next, we study about decision time, and as we expected that we see lower accuracy with a slower decision, here we see it in both our single pulse trial and double pulse trials. And we expected that faster decision accompanied with higher confidence. And we can see such things in double pulse and single pulse of our data. But interestingly, we can see that when comparing single and double pulse with each other, we see that in double pulse trials, the decision time differs significantly, and it's the decisions are more faster. So to explore the internal or explicit state of participant, we record EEG. It was known that there is a peak stimulus when we use a stimulus onset data. There was a peak around 300 to 500 after a stimulus onset. And we can see such things in both single pulse trials and double pulse trials in all gap duration here in our test. And it was known too that this centroparietal signal was related to confidence. To be sure that our results are irrelevant to participants' performance and the coherence of the motion strengths, we separate, we just consider correct responses and separate the coherence in double pulse and single pulse trial and consider them separately. And as you can see here, the high and low profile of confidence can be seen more meaningfully in our double pulse trials rather than single pulse trials. So altogether, it seems that accuracy and confidence were invariant to the gap interval. And in line with continuous studies, accuracy and confidence could be tracked from decision time and ERP component. And more interestingly, I think that comparing double pulse to single pulse trials, we can see that decision accuracy and metacognition improve, but not confidence. And implicit confidence measure like decision time and ERP-CPP signals can be observed more meaningfully, while explicit measure like confidence rating remains almost the same. And at the end, I would like to thank my supervisor, Dr. Ibrahimpour, and all my colleagues in decision-making lab in Iran, and thank you all. I think that I go very fast, so we may have time for questions.
All right, thank you very much, Zara. And indeed, yeah, very excellent timekeeping, in fact. Okay, so let's ask the first question here from the audience. So Lawrence says, I may have missed it, but was it possible to compare meta D prime on the double pulse trials for an equivalent level of difficulty on the single pulse trials? i.e. where the accuracy of the subject is roughly equivalent because the single pulse trial has more coherence.
But was it possible to compare meta and double pulse trial? Good point. Why couldn't we compare D prime for double pulse trials and single pulse trials? Because the evidence the sub participants received during the task was different in each of the task conditions. So I think that why not?
Okay.
No, sorry. I should add something because we just compared the coherence which are corresponding to the double pulse trial. For example, if we have just 3 coherence in double pulse trial, we separate the trial which have those kind of trial coherence and then compare those. And because in signal detection theory, the number of the trials are important and can influence over the results, we do a kind of sampling and select the trial randomly and then do our testing.
Okay. Would any of the panelists like to ask a question, actually? Because I can ask some questions, but it might be interesting to get the more expert opinions of some of our other panelists, if anyone has a question. No? Okay, so I'll ask my question then. So I thought you made very reasonable and measured conclusions, but if you were invited to speculate wildly about what the significance of this might be, what it means for decision making more generally, do you have any thoughts about that?
If I want to say it more, if I want to consider it more generally, it seems that if there is a very short, I can say that short information, you might decide because of the pressure, for example, but your decision might not be that much supportive. You might change your decision because of the confidence you report is not, it's irrelevant to your performance.
Okay, cool. One question came in while I was asking that. So if you can very quickly answer this one, I think, which from Lillian asks, have you looked at metacognitive efficiency, the ratio of metacognitive sensitivity in D prime, therefore adjusting the estimate of metacognitive sensitivity for changes in performance?
Yes, we have done that. And like metacognition sensitivity, we see that metacognition efficiency improved in double pulse trials too. Cool. But I don't include the result here.
Great. Brilliant. Okay, so maybe Lillian can follow up with you by email on that.
Thank you.
Brilliant. All right, well, thank you very much, Zara. And I think we should probably move on to the next speaker at this point, who is Maria Rusella, who's going to talk to us about evidence accumulation in a new dot motion task. Zara, I think I need you to stop sharing your screen so that Maria can start sharing hers. Brilliant. Thank you very much.
Okay.
Yeah, so take it away, Maria.
Yes. Yeah, thank you, Dan, for the introduction. Hi, everyone. Thank you for your interest in my talk. I am Maria, and I work with Lawrence Hunt, and I will be talking about a project that I did during my PhD. And this is about how humans adapt the integration kernel to different timescales of evidence integration. So to give you like an example, if you think about everyday life and you might be using your bike, going to work, you will have to make decisions that are probably based on maybe a few minutes or even seconds of evidence, for example, to switch lanes. So this is a very short time scale. In contrast, if you maybe want to sell stocks, you probably want to think about that and consider evidence of several days or maybe even weeks. So how are we measuring this in the brain? Like Sarah, my task paradigm is a random dot motion paradigm. And as you know, in the past, these paradigms have been consisted of discrete trials in which mostly the motion coherence stays constant. However, in my task, the motion, the dots change their motion direction continuously for 5 minutes straight. And this is a small video. I hope it works because sometimes Zoom will probably drop frames, but this is basically what participants will see. They will see these continuously moving dots, and then they will have to detect these stable phases in which the dots will more often move to one direction than to another. These stable phases are indicated by the fixation dot in the center turning white. So obviously, this is just for you guys so that you get a feel for the task. In the real experiment, participants won't get any cues about this. But importantly, participants have to pay attention to past motion directions to solve this task. This is a schematic of the task, and this black line, this is the signal, and this can be either in a baseline period or in a trial period every time the signal deviates from the baseline. So for example, here it goes down. That would be a response to the left, because here on average, we look at those and those, the motion goes on average more to the left than to the right. So now this is not everything. We thought that if we manipulate the trial period, meaning that we ask how does the integration kernel of participants change if the trials are either long or short, or based on how often they are. Are they frequent or are they rare? This is shown here in this schematic, and it's a 2x2 design. And then we would expect that the integration kernel shown on the right would change accordingly, and it would be how far back in time would you consider evidence, and how much evidence in total do you need to make a decision. So now we need to think about how do we analyze this data, and how do we get these integration kernels from the behavior, but also from EEG out of this data. And for this, the noise is very, very important. So the noise is this gray line here that wiggles around the signal, and that's the actual coherence that participants see on each frame. And very importantly, I have complete control over this noise, and I know exactly what happens on each frame. And this variability in the noise is, in the end, that what allows me to analyze the integration kernel in the behavior, but also look at the EEG signal. So I will first look at the behavior. So what we do here with the noise is this, might be a snippet of what the participant does, and the participant will make some responses, and then I will go in and cut out the noise here in the yellow square leading up to that response, and I will do that for each response, average this, and voila, what I get out is this integration kernel of the average coherence from these snippets. And if we do this for each condition, rare versus frequent, short versus long, we indeed see that the integration kernels vary between conditions. And indeed, if you are in a rare trial condition, you consider evidence further back in time than what you do for frequent trial conditions. So what about the EEG? Sarah already mentioned this. We also obviously know about the central parietal positivity signal from O'Connell, and that's based also the reason why we looked at certain electrodes in this case. And again, the noise plays an important role, because if you think about your typical EEG experiment, you might have your 30 to 50 events that you can time lock to. But in my event, I basically have thousands of events, because I can look what the brain does at each time point the noise changes. And yeah, I don't use a typical time lock analysis. It's more regression-based analysis described in the Unfold toolbox by Enger and Dijmingen. They will give a talk tomorrow at Neuromed, so check that out. It's really interesting. And what I did is I first wanted to know what happens in the brain every time there is a change in the noise. What's the main effect? And this is shown here on the left. So from the topography, you can see this is sort of the central parietal partitive signal that we know from O'Connell and his studies on evidence integration. And you can also see it has a peak at 300 milliseconds after a change in the noise. And this is consistent across all conditions. And I think this is really cool because we really see, okay, the brain updates or does something every time there is a change in the stimulus. But even more interesting is that if we now look on top, put on top of that requester looking at how much does the noise change, meaning how big is the difference of the previous coherence of the previous jump and the current coherence of the current jump, you can see that we find the difference that we only for rare versus frequent trials, but this is significant and indicates that if participants are in rare trial conditions, the brain updates the information differently than if you are in a frequent trial condition. We also have some additional results that I think make the previous results even more interesting. So what I also did is I did a control experiment. In this experiment, participants not only see this horizontal motion, but they will also see vertical motion going up and down. This vertical motion follows the same statistics as the horizontal motion, but will give you no indication whether you're in a trial period or not, because the participants should still focus on the horizontal motion. And that's really cool because now we can see that the brain actually, we're looking at the same regressors, really only cares about the motion relevant, here the dark gray line information in the horizontal motion, but it doesn't really care about the vertical motion. So the signal we are measuring is really directly related to decision making and doesn't have to do with any other processes, such as a visual update or something like that. And another really interesting result, I think, is this one here. So now we are back with behavioral integration kernels, and this is my final result. What we actually found is that the cross-subject variance is a lot higher than the within-subject variance. So what this means is, so these are integration kernels for 3 subjects in the row, and the conditions are here in the columns. So if you look at subject 1, the integration kernel is actually quite consistent across all conditions, but it varies quite a bit across subjects. What I mean by that is here the integration kernel decays very fast back to the baseline, which means the subject actually only considers the very recent motion directions the subject has seen. And this is true for all conditions. In contrast, if you look at subject 3, here the decay is a lot slower, meaning this subject actually considers evidence that goes way further back in time. And then I guess subject 2 is somewhere in the middle. This means that actually we can get here a robust signal of the integration kernel for each subject. And we are obviously continuing analyzing this now because we think that we might also find such a signal in the brain that might be consistent within a subject, but vary across subjects. So in conclusion, I talked about a new continuous evidence integration task that allows us to measure evidence integration robustly. Furthermore, by manipulating this task, we can influence the behavioral integration kernels participants use and also the EEG signal. The measured EEG signal is purely related to this decision-making process, but not to another process, as I've shown with the control study. And these behavioral integration kernels can be robustly measured and are consistent within the subject and are further investigated now. Thank you for listening.
That's great. Thank you very much, Maria. Right, and actually quite on time, quite early in fact. So we've got plenty of time for questions, and they're beginning to stream in now. So I'll just leap in here with the first one. So we have a quick question from Benedict. The effective jump is a constant and prediction error is the slope. Is that right?
Yes. So the effect of the jump is a constant. So it's a binary regressor for a 1 every time there's a jump. So it's really the main effect size. And the prediction error is really actually the difference. So let's say if the jump at time point t is at 30% coherence and the next one is at 20% coherence, and the difference is 10%, and that would be the regressor. And I've plotted the betas for each of the regressors. Does this answer this question?
Okay, yeah. And the other part of the question was the effect sizes in microvolts.
Well, I plotted the betas, and I think for the jumps, that's obviously true because it's just the main effect. But for the prediction error, I wouldn't be quite sure now. That's true.
All right, so maybe Benedict can follow up by email on that one. Okay, so we have one from Tim Hanks. Very interesting experiment and results. If I understood correctly, your hypothesis was that kernels would be longer for long duration than short duration trials, and bound would change based on the rarity of trials.
Yes.
But it
So
seemed that, yeah, sorry, go ahead.
Sorry to interrupt you. Yeah, no, yeah. So like just nothing. Yeah. So yeah, that's true. You've seen that correctly. I didn't really go into that because so definitely. So the first thing I can say, we so far haven't found any changes in the evidence threshold for which we had hypothesis for rare versus frequent trials, but indeed we found that we have a very strong effect of the trial frequency with rare trials having longer integration kernels. It seems like the participants just need more evidence in these paradigms to make a decision. Sorry, I need to read that. And that they just need, you know, in total higher evidence to be sure that they are in a trial. I should also mention that this also holds for false alarms. So if participants press during the baseline period because they thought they are in a trial, we also find a result that still shows that the integration kernels are still slightly increased for the rare trial conditions.
Okay, yeah. So I think that the next part of the question was, do you have ideas for why that occurs?
So yeah, so I think, like I said, so for the rare versus frequent, it's really just a matter of how much evidence do I get, and that I really believe that participants need more evidence, because I guess if you're in a rare trial, you need to be convinced a lot more, because trials occur, you're a lot more cautious to press the button, right? So you think that you need more evidence, you need to be more convinced to press the button, versus in frequent trials, they happen so often, like every 2 seconds, that you basically press constantly because you're a lot less cautious about it. And then you obviously would consider probably less evidence back in time. I hope that explains this a bit.
Yep, I think so. Cool. So we have a question from G1. Interesting talk. What is the reason that you looked only into certain time before the button press, not the entire period of a trial?
Okay, yeah. So the thing is that, you know, we have these 5 minutes. That's one block of one condition. That's condition in that block. And we always have trials dispersed in there every so many seconds, depending on the frequency. And these trials are either 5 seconds long or 3 seconds long. So that's why we look 5 seconds back in time.
Okay, great. All right, from Maxine, who says a lovely talk, thank you. And in a recent paper from the Shadlin lab by Gabriel Stein, the authors pointed out that evidence integration over time is an assumption that we need to test against alternatives such as extremer detection. Have you tested whether people are indeed integrating continuous evidence?
So I would argue, given that well, yeah. So the thing is that we only work with an Andrein Wednesday Oct process so far to model this task. So, and you know, it sort of to some degree overlaps with the results I found. But I think we are now also looking into more of like a Bayesian model, which will Lillian Weber, a postdoc with Lawrence, do now, where I guess we will also look further on how each jump directly influences the evidence integration signal, and how much the variance of the noise influences how you integrate that evidence.
Okay, great. All right, so there was some remaining questions, but I think we're going to have to move on to the next talk now. So if any of the remaining questions, you could maybe have a look in the chat and answer them, and also maybe people can follow up with you by email as well.
Sure, and my email address is down there. So. Thank you.
Right, and now the final talk of the session is Michael Pereira, who's going to talk about evidence accumulation and conscious access. So please, yeah, take it away, Michael.
So hi, everybody. I'm Michael Pereira, and I'm going to happily continue with evidence accumulation and attempt to link it to conscious access using single neurons and computational modeling. So imagine that you're bitten by a mosquito. So there is a conscious experience that is associated to this event, and our goal is to find the brain processes that support this conscious experience. And so for this, we're going to use a contrastive approach, meaning that we take stimuli that for the same physical properties sometimes do not lead to a conscious experience. So for example, you could not notice that you've been bitten by a mosquito. And so that allows us to contrast the brain activity between the two conditions, and the difference will correlate with the conscious experience, and that's why they're called the neural correlates of consciousness. And so how do we probe what's the content of the conscious experience? Well, the good thing with working with humans is that you can ask them. And so if they answer that they felt the stimulus, then it's a hit. Otherwise, it's a miss. And this is a first order report because it's directly related to the stimulus. And we're also interested in second order representations, so representations of oneself in a first order state. And as a proxy to this kind of processes, we will use confidence ratings. We will ask the participants how confident they are about their first order reports. And so there have been many studies of the neural correlates of consciousness. And here we're trying to tackle a hypothesis that tries to explain how this brain activity relates to conscious experience, and it's based on mechanisms that a mechanism that's borrowed from the field of decision making. And so the idea that some neurons in your brain accumulate noisy perceptual evidence over time, and when it reaches a bound, you take decision. And so since this process is stochastic, this could happen at different timings, or it could not happen at all. And in this case, it's a miss. And so this has been extensively studied in non-human primates, also in humans using EEG and linked to consciousness. And so in this study, we're going to link it to consciousness using single neurons and attempt to link evidence accumulation to confidence and to a computational model. And so we were lucky to be able to work with a patient with epilepsy that was implanted with a microarray in the posterior parietal cortex here. And just, so here you see the microelectrode array, and it was just next to the somatosensory area. So that's why we're going to look at tactile perception. And so with these participants, we did 3 experiments. And the first one, so we apply weak vibrotactile stimuli on the wrist of the patient. And we titrate the intensity so that in 50% of the cases, the participant will not report feeling the stimulus. And in 50% of the cases, he will feel it and immediately press a button. So we get the response time. And so this would be a hit. And so for the analysis, we time lock on the stimulus onset, and we're going to count the number of times that the neuron fires in this in a window between 500 milliseconds and 5 seconds. And we're also going to look at the firing rate. So here's the firing rate for these neurons that we believe accumulate evidence. So you see this rather typical buildup of the firing rate prior to the response. So here you have 3 bins of response times. And you see that the slope is steeper for faster responses. And so the way we select these evidence accumulation neurons from the other neurons, so first we look at detection neurons, so neurons that have a different firing rate for hits and misses. And then from these detection neurons, we look at the ones that have this gradual build up to the response time. And so we found 12 of them, and these numbers, they're statistically significant, meaning that we checked that we couldn't have obtained them by chance. Now, the problem with this experiment, of course, is that the neural correlates of consciousness are contaminated by the fact that there was a motor response in one case and not for misses. And so in the second experiment, we used a start cue, and that was followed by a 2 seconds window where the stimulus onset could occur at any moment. And importantly, then we added a 1 second delay before the participant was cued to report whether he felt the stimulus or not, and his confidence about his response. And so here we have two factors. We have the detection, hits versus misses, and we have the confidence. And so we looked at these two factors in a factorial analysis, and we actually found that most of the neurons that were responsive, they were responsive to both factors, meaning that there was 17 neurons that showed detection times confidence effect. So showing that it's probable that the information that is used for detection could also be used for the confidence in hits. And here you see the average firing rate of these neurons with this ramp up of the activity that you can see only for high confidence hits. So now the thing is that these two experiments, they were always accompanied with this decision making. So we were asking the participants to report whether they felt the stimulus or not. So it's somehow hard to disentangle whether this is related to decision making or to conscious perception by itself. And so in the third experiment, we stimulated the patient with stimuli with different intensities, and we didn't ask him to report anything. And although we didn't ask him to report anything, we still found some neurons that had that coded for the intensity. So with higher intensity leading to higher firing rates. And so now we characterized these neurons in the parietal cortex, and we were interested in seeing whether we can model this neural and behavioral responses using a computational model of evidence accumulation. So for this, we recorded 18 healthy participants with EEG, and we found this famous CPP here that is actually quite like the neural responses that we got, meaning that there's an increase for hits and not so much for misses. And you see here the behavior with the detection rate and false alarm rate. Now, the problem with fitting these evidence accumulation models is that usually you fit them to discrimination task and you have response times for all conditions. Here we can't get response times for misses. And so we decided to not collect any response time. So we're not contaminating this NCC, but we fit the shape of the evidence accumulation to the neural response for hits and for misses, while keeping the simulated behavior identical to the observed behavior. So here you see the results of the fit for all the subjects and the behavior, and you see that even for single subjects, it does a decent job at capturing the individual differences. And so now that we have this first order model, we're going to fix the parameters and try to simulate confidence. And so for this, we're going to simulate traces of evidence accumulation, and we're going to define confidence as the maximum of the accumulated evidence over time with respect to the boundary. And that allows us to also define confidence for misses as this distance or for correct rejection. And so using this mechanism of maximal evidence for confidence, we were able to reproduce the confidence, so meaning here you see the average confidence for these three conditions: hits, misses, and correct rejections over all subjects. And here you see the distributions of the confidence with with the model predictions, or model fits rather. And so we did a bunch of other tests to verify the predictions of the model, which are in the preprint if you're interested. But the last thing I wanted to present is that when we use this maximal evidence method to compute confidence while looking at our neuronal data from the patient, we were able to decode confidence for both hits and misses, while when we would apply the, let's say, more standard procedure of looking at time locking to the stimulus onset, we could not decode confidence for misses. So altogether, we present an evidence accumulation account of perceptual consciousness that's based on neuronal activity in the PPC and the computational model. And we think that this evidence accumulation account could also underlie perception in the absence of decision making. And we also propose a way to explain metacognition also in the absence of awareness. And finally, this evidence accumulation account is integrated in the global workspace theory, because it has already been hypothesized that the ignition in the global workspace theory is triggered by accumulated evidence reaching a boundary. And so with this, I'd like to thank all the co-authors and the funding agencies and the audience for their attention, assuming I'm not alone. Thank you.
Thank you, Michael. And I can confirm you're not alone. There's quite a lot of people in the session, actually. Yeah. Okay. So we have a question from Nadine, which is actually pretty similar to what I was going to ask. So let's go ahead and ask that one. So Nadine says, "Thank you for the interesting talk. Great stuff and very clear effects. The one thing I was unsure about was why did you frame this as a consciousness study? To me, it seems like traditional perceptual decision-making study with a metacognitive component. You find effects of detection, response, stimulus intensity, and confidence rating. What makes it specific to consciousness?"
Yeah, sure. So, well, the thing that so we're interested in linking it to consciousness. So, of course, there are a lot of questions that come into play that are, I guess, well, typical to works in consciousness, but we think that the fact that we titrate the intensity to get 50% hits and misses, and the fact that we just ask the subject whether they perceive the stimulus or not. I mean, unlike animal studies where you're never really sure what is the corresponding perception, we think that this allows us to, let's say, at least tentatively link it to consciousness. But I understand your concern.
Yeah, I mean, I guess it's always, consciousness is always a tricky issue in that sense.
That's also why we talk about conscious access and not directly consciousness in the title.
Right, yeah, try and be a bit safer. I mean, so it's actually my question was a bit like that. So is the bigger picture question here, like, sorry, the bigger view of consciousness here is that somehow we're always accumulating evidence about the world, and it's only when that evidence reaches some threshold that we become conscious of it. Is that more? I'm quite naive about consciousness stuff, so I'm just trying to get a feel for it. Is that the sort of the idea behind what you're doing here, or?
Yes, so that would be very much linked to this global workspace theories. Of course, there are many other theories, and there's no consensus on whether this is actually the theory.
Okay. Right.
But let's say in our view and in our model, let's say that's what we would propose.
Cool. All right, we have time just about for one more quick question, I think. So we have Derby has asked a very interesting talk. I couldn't quite follow this, but was it true that there were many neurons in experiment 1 that showed difference between hits and misses, but did not show an evidence accumulation profile?
Yes, that's true. They were actually, so one thing we have to say is that so the conditions to say that neurons were accumulating evidence were pretty strict, because we really wanted to see this gradual buildup. And so that's why we found actually quite few of them. But actually, when you look at all the neurons that respond to hits versus misses, it's very, very heterogeneous. So you see some that respond after the response, some that respond before, and with various shapes. So it's yeah, it's true that for the rest of the neurons, let's say we wouldn't have, let's say, any mechanistic explanation about what they're doing and what is their role.
Cool. All right. Well, in that case, I think we're pretty much out of time. We've got 1 minute before we get brutally cut off. So I'd just like to say thank you again to Michael, and thank you to all of our speakers in this session. That was really interesting. I hope everyone enjoyed that as much as I did. And yeah, if you want to follow up with further questions, unfortunately the chat's not going to stay open for this session as soon as we shut. So could you maybe email or tweet or whatever to the speakers to follow up on this? All right, thank you again, everyone.
Thank you.
Well, even if people will hear us, then we can say, how are you?
Very good. And you? You're still, how is going? Did you attend many of the seminar? It's nice.
Well, some, yes, but there are so many seminars ongoing that
exactly, so many in parallel, right? So it's quite full and quite dense.
It's quite demanding, but it's like quite nice as well. So that's yeah. And on top of that, there are also other conferences. So I think that's
yeah.
Yeah.
And people are getting so many of these seminars that is, I mean, it's great. But somehow it's becoming really dense, huh?
Mm. And so I'm also wondering whether at one point we should redistribute in a different way and not to have that pack, because anyway, we're going to spend probably another year like this, right? So then we can also make it a bit less dense and distribute, because at one point, I think it's a nice format, especially for a student and PhDs and postdocs, but
especially because also at the institute we don't have seminars anymore, so there is basically nothing anymore. So in the end, is also a way to keep the people a little bit, you know, inside of the science. But it's a lot now. I think after the summer was one after the other one.
Yes, indeed, and but again, I mean, I think that's we are reaching people that usually we were not reaching in the normal world and then the normal type of conferences, right? And I think this is really the nice part, and also have people communicating with each other, and so I think this is quite lovely. But yeah, let's see for we have really to see whether we will go back then to how it was before or not, right?
Yeah, it is possible to watch them later, these seminars, or also just only live?
So this is actually now they are recording it, but I don't know. In fact, I am not sure where and when they are gonna put them. But it's being recorded. In fact, yeah. So I think now a few more people are joining. Let's
wait a bit.
Yeah, we wait some minutes.
2 minutes.
Right? Yeah. Let's wait maybe a couple more minutes just to be sure that everyone does the transition. Maybe, I mean, there was some difference in time from other talks, but just to be sure that people are here. Okay, maybe I start with the introduction. Well, it's actually my great pleasure to introduce the speaker of this keynote talk, Silvia Capello. And so just very briefly, Silvia is originally Italian, and she obtained a PhD she studied biotechnology, and then obtained a PhD in pharmacology and toxicology. There are so many things that one learns when introducing people, actually, because I didn't know that I had a PhD in toxicology as well. And so her PhD was obtained at the University of Bologna in Italy. But at the same time, while she was still a PhD student, she was visiting already the laboratory of Magdalena Goetz in the Max Planck at that time in Munich, in Germany. So then once done with the PhD, she moved to the US. So she went in Columbia University to work in the lab of Richard Wally, and so on a laboratory of cell biology. And then finally, not finally, but after the postdoc, she moved then back to Europe, back to Germany. I think she really fell in love with the research that Magdalena Gotz was doing and is doing, and working on the neural stem cells. And in 2015, she became independent group leader at the Max Planck Institute of Psychiatry, so in Munich, Germany. So overall, Sylvia is very much interested in understanding the basic biology of neural stem cells and brain development. But she has also a very, she kept and always an eye actually, a big focus on understanding also human disorders. In particular, what she's studying are defects of brain development, which are interfering. Sorry, this was unexpected. Which are eventually leading to brain malformation, so structural malformation, going from lissencephaly and other type of cortical malformation. So Sylvia, thank you very much for accepting to give this talk. So I think today we are also, something that I didn't mention is that Sylvia, since some years, she's using brain organoids to study those pathologies. So I guess we are also going to see some of that. So again, thank you very much for accepting to give this talk, and very much looking forward to it.
So thank you very much, Gaia, for the invitation. Actually, I have a PhD also in toxicology, but I don't think I have done anything in toxicology, but you know how it is. But I'm very happy to be here today. I think this is a great opportunity, again, exactly to share our finding and to discuss science in a different format. And so I will share the screen and tell you what the project that we are working about now. Let me just make sure that everything is running properly. Okay, I hope you can see it, but I'm sure you will tell me if you don't see anything. So what I want to talk today about is something that we slowly care more and more inside of the lab, because we have many projects that lead to the same key point, and is that extrinsic factors are also very important for human neurogenesis. And yeah, I'll give you a brief introduction about why we're all here. So we are all interested in understanding the human brain, but I strongly believe that if we want to understand the function of the brain, we have to go back to development and really tackle all the processes that govern the development of the human brain. And specifically, if we want to understand the disorders that are associated with the brain, like, for example, neurological disorders. I will talk about that today, which are, for example, cortical malformation. These are very obvious diseases because you can easily spot them with an MRI picture. And they are sometimes, you know, kids have smaller brain or larger brain or smooth brain instead of folded brain, or neurons that don't migrate to the right place. And of course, since are coming very early in development, this also have very strong consequences like intellectual disability or seizure. And but luckily, at least they are rare disorders. But if we go to more prevalent disorder, like psychiatric disorder, neurodegenerative disorder, still we can slowly see that it's very important to understand cell development, because psychiatric disorders, even if they are not so easy to see and to associate with development of the brain, we now know very well, and Gaia can confirm that, for example, autism or schizophrenia, but also more complex disorders that come later in life, they have a developmental origin. And also for neurodegenerative disorders, also very prevalent, we actually need to know everything about how neurons develop to be at some point able to maybe replace the neurons that they are dying in these cases. So from my perspective, the brain is this beautiful composition of cells which are generated during development. Then they have to be generated in the right number, go to the right place, and mature in perfectly to then connect. and give rise to a functional brain. And so what are the cells and trajectory that they are populating, that they are important for population of the brain? So we have generation of cells, which include neurons and glia, and different type of neurons and different type of glia. Cells need to migrate tangentially, the excitatory neurons, tangentially the inhibitory neurons, radially the excitatory neurons. Then they have to become mature, make dendrites, define what is the axon and make synapses, and then function, meaning integrate into the circuits. So when something in this process is not going correctly, you can imagine how much this process needs to be regulated. And so in these very early developmental disorders, like neurological or psychiatric disorders, we have to find actually the vulnerable hubs to understand where exactly in which cell biological processes we have some defects, so that it could be very early, like during the generation of neurons, or maybe more during the migration of the neurons or the maturation. And of course, for that we need model system, and so we have a lot of model system available now, animal model system. A lot of work has been done in the mouse, but I think we need also to have more complex models, like even animal models, like more non-human primates or ferret, which is more as a folded brain, for example. But also the advent of this induced pluripotent stem cells give us really these very important opportunities to study human cells in a dish. So human cells, mainly, we can generate neurons, put them in a dish and study them, and not only in 2 dimension, but also now in 3 dimension with organoids or assembloids. So I just wanted to mention that, because in the lab, and you will see in this project, we mostly use as an in vivo model, we use the mouse, and as an in vitro model, use both 2D and 3D model system like organoids and assembloids. And of course, we know that these in vivo models are important, but despite the big difference that you can see with this very simplified cartoon, in which the mouse brain is so much smaller, so much more simple, and has so many less cells and synapses, despite that, when you look at the processes that they govern brain development, so many similarities and so many processes are conserved. So we have radial glial cells, especially the apical, which are very similar in mouse and human, for example, then intermediate progenitor, which are also very similar in mouse and human, with some changes in localization. Only then we start having something that start having some differences. So the basal-radial glia, which are also present in mouse, but in human, they are very strongly enriched. So it's something that become a little bit more specific for human compared to mouse. We have then migrating neurons that we now know that they have some different composition of receptors on the surface molecule, let's say, to migrate in a human-specific way. Excitatory neurons, now we also know that interneurons, that they come from the ventral side, they are some population which are unique in human, or at least they are different compared to mouse. Then we have a lot of glial cells, which are also very heterogeneous in human. And finally, what I will talk about today is that we have also a very big differences in the secreted factors, namely both the extracellular metrics that compose the human brain has been shown, especially by the lab of Willem Hutne, that is quite different, but also I will show you that secreted vesicle can be quite relevant. What is important is to then also have a human model system, but of course you can see from also this very simple picture that obviously the human model is much more simple also because it's just in a petri dish and not attached to a living human being. So the developmental disorder that we are mostly focusing in the lab are neuronal migration disorders. So I work on neuronal migration disorders since quite some time, and in particular today I want to tell you about one that we study extensively since quite some years, which is called periventricular heterotopia, in which neurons actually accumulate at the ventricles, some of the neurons, not all of them, instead of migrating far away to their correct layers. And they form either nodules or band. But this is not the only neuronal migration disorder. So we have also different type of neuronal heterotopia, like subcortical band heterotopia, and also the lysencephaly, so smooth brain or brain with over-migrating neurons. So today, in particular, I want to discuss how mechanisms underlying both neuronal migration disorder and at the same time also brain foldings. So a few years ago, in collaboration with Stephen Robertson, a clinician in New Zealand, we found some patients which had cortical abnormalities and mutation in one specific gene that is called galectin binding protein 3, and simplified here as L-GALES3BP. So all 3 patients had mutation in exon 5 of this gene, and actually they had the first one as neuronal heterotopia, the second one as also some abnormality of the central nervous system and a little bit of microcephaly, and the third one some also abnormality of the CNS. And in particular, we managed to have all the data, MRI data and clinical data from the first 2. And interestingly, apart from cortical abnormalities, one of them had also autism spectrum disorder. So we decided to study this specific patient in order to understand if we could link actually something that is a neuronal migration disorder, also so a neurological disorder, also with something like a psychiatric disorder. In particular, we want to focus on 2 processes. One is the neuronal migration, namely the balance between excitatory and inhibitory neurons, and the other one is the process of folding. So the one of migration and balance between excitatory and inhibitory interneurons is really ongoing, and so it's a bit too early to say, but we are basically using assembloids to look at interneurons migrating from the ventral side and to the dorsal side to actually look if the balance between excitatory and inhibitory neurons is actually altered in this model system. But today I want to focus more on the folding process. And so with Renzo Guerrini, that is a radiologist in Italy, he did some morphometric analysis of the brain of these 2 patients that we managed to have all the data. And what he could see is actually that we have changes, local changes in this patient's brain, which leads to changes in the cortical thickness and in the gyrification index, in local gyrification index. That was the first patient, and the second one actually had many more defects, but both on the same direction, so change in the thickness and in the gyrification. So Cristina Chirusi, a postdoc in my lab, decided to study this gene, and in particular, since there were changes in the folding and in the thickness, we thought that it could be a gene that is important for evolution of the brain and expansion of the brain. So we look at the expression of this galectin binding protein, and by looking at different single cell data or even bulk-seq data in different species, we could basically see that in human is expressed in a specific population of cells, which is mostly radioglia, and also this basal radioglia. In mouse, it's completely absent, and in ferret, actually is highly expressed in the ventricular progenitors that will generate gyrus versus the one that will generate a sulcus. And if you look in organoids from different species, all primates, we can also see that it's strongly enriched in human compared to other non-human primates. So suggesting that could have an evolutionary important role, this galectin binding protein. So we look at this expression also in human fetal tissue with the help of the lab of Alex Buffet. And basically what we can see that this staining here that you will see later, that is really good staining and not just dirty dots, is actually accumulating in the outer subventricular zone where the majority of the basal radioglia are residing, but is also spread a little bit in the whole cortex. And especially what is interesting is that it's really co-localizing with its expression, is co-localizing with OPEX, which is also a marker for basal radioglia. So we look a bit more carefully, and indeed in this outer subventricular zone, where is exactly expressed, and we co-localize with markers for progenitors and for neurons. And if you look at these little dots, and indeed is expressed in vesicles, as you will see later, is actually co-localizing very much with SOX2 positive cells and not really with neuron positive cells, so really suggesting that is in progenitors rather than neurons. When we look in the organoids, we can see that is expressed first in progenitors, then a bit more in salt and pepper fashion when you grow the organoids, so suggesting that it's really going to more basal position. It is again pretty much in vesicles, and also suggesting data from single cell sequencing suggests really that is high in radioglia and is going down in intermediate progenitors and neurons. So what we did was to then generate iPS cells with the mutation of our first patient. But in addition, we also generate a knockout for the whole exon 5 to actually mimic a little bit more the 3 patients, so all 3, because they all had different exon 5. And so these are the 2 official names of these 2 mutations that we inserted by CRISPR-Cas. So when we look at the organoids, we just did some basic staining, and what we could see, we also did FACS sorting to quantify all the cells that are present there. So what we could see is that we don't see major differences in progenitors, apical progenitor, PAX6 positive, or basal progenitors that are PAX positive, or neurons double coding positive. So in numbers, they seem quite normal. But if we look at the distribution of the cells, and especially these basal radioglial cells, or cells that they are a bit more in basal location, we can clearly see that while in control, the majority of these OPEX positive cells, they sit here. In the mutant, both mutant, actually, we had a lot of cells. Some cells actually delaminate quite nicely, but some of the cells actually were also accumulating at this apical ventricle, at the ventricle, so suggesting that they didn't manage to delaminate. So they are the same number, but when you look at a position, we have many more of these cells that stay at the apical side. So suggesting actually that we retain somehow, when we have this mutation, the cells at the apical side. And interestingly, when we look at the neurons, since these patients are also neuronal migration defect, we can see that exactly in the same position where we have this basal, progenitor should be in basal side. When we have them in the apical side, we also accumulate some neurons at the same position in this progenitor zone. So suggesting, or maybe indicating, that these neurons that they are generated in the wrong place, because these cells, they are not actually here, but actually located here, may also be confused in terms of where they are supposed to go. So we therefore decide to overexpress this gene very quickly to see if we could generate actually more of these basal radioglia. And indeed, we had immediately a change in the morphology of the cells, as you can see here, but also with shorter processes. But also when we did OPEX staining, we could see that the OPEX positive, GFP positive cells were increased. So suggesting that from apical radioglia, when we overexpress these genes, we have the delamination of the cells and the generation of more basally located progenitors. So we also confirmed that, again, with the help of Alex Parfait, in human fetal tissue. So these were few experiments performed, so they focus only on this area, and they could actually recapitulate the same phenotype, namely that we have more basal radioglia when we overexpressed L-Gallium-3p. So, but I didn't tell you very much about this protein, what it's doing, and what it's clear is that this protein is secreted in vesicles, and is actually in vesicle and not, and can bind a lot of protein which are present in extracellular matrix like collagen, fibronectin, integrins, and also tetraspanins. And very interestingly, both integrins and tetraspanin, which are binding partner of L-Gallium-3p, lead to changes in cell adhesion and cytoskeleton remodeling. So we thought that maybe this could be one of the reasons why the cells, once they have L-Gallium-3p, they delaminate. And so we look at the apical adhesive molecule at the apical side here with beta-catenin or F-actin, and we can clearly see that overexpression lead to delamination, but also lead to loss of this apical membrane, loosening of this apical membrane, suggesting that that's the way these cells delaminate. And when we look in the patient's ventricle, we can actually see that this belt is super thick, and probably the reason why these cells fail in delaminating. So we decided to have a look at this protein a bit more to do proteomic analysis actually in this organoids to see what was dysregulated, and this was done in collaboration with the lab of Stefan Sieber. And so what we could see, first of all, that what is at the level of biological processes, what is dysregulated are many processes related to neurogenesis, neuron development, generation of neurons, so definitely something related to the brain and to its development. But when you look a little bit more on the cellular components, could see that there were a lot related to extracellular stuff. So extracellular space, vesicle, organ, eggs, vesicle again. So we started to think that it was really something related to its secretion. And so we decided to do also what we call secretome, so the proteomic analysis of the medium in which these organoids grow. And again, we could see that a lot of geotherm, they are referring to exocytosis, vesicle-mediated transport, extracellular matrix organization, and so on. So everything related to the outside, both vesicles and matrix. So at this point, we also wanted to understand which population of cells lead and is mainly relevant for these changes, and if there is a main population, so progenitors, neurons, since we saw that expression was mainly in progenitors. So we decided to do, with the help of Barbara Treutlein, single-cell sequencing of these cells, and so we look at a variety of markers to confirm that we had the right regions and to see if these organoids were comparable. But then when we look at the proportion of cells which were actually generated in the mutant organoids, what we could see very clearly that they are a strong decrease again in ORG or basal-radial glial cells. And as we suspected already, not only the basal-radial glia versus apical radial glia markers were disbalanced, but also again collagen and matrix protein were dysregulated in the mutant organoids. But what we were really hoping to find was to find something that was related to also extracellular vesicles, because in the meantime, it's now known that this protein is secreted in vesicles. So we found actually something very interesting. So the family of the tetraspanin, which are transmembrane receptor of extracellular vesicle, and in particular exosome, were quite dysregulated. And so we decided to do to have a look at this vesicle, and also by simply look at the radial glia geotherm analysis, only radial glia, but not intermediate progenitors and neurons, we again could find that the main dysregulated processes were related to extracellular vesicle and extracellular secreted stuff. So we were quite convinced by all this data, proteomic and secretomic and single cell sequencing, that radial glia have something to do with the secretion of stuff in these cells. So, and indeed, when we look back to this immunostain that we're performing the human developing fetal tissues, you can clearly see that we have a lot of vesicles and a lot of dots. And these dots actually, in some position, they look a bit more like macrovesicle or maybe aggregate of vesicle, but you can also clearly see that in many of these positions, you have clearly single vesicles. So what we did was to then, with the help of Rossella Di Giammo and Giuseppina Maccheroni at the Institute, we actually did a proteomic analysis of the exosome of the organoid. So we extracted exosome from the medium, and we generated, we ultracentrifuge this medium or these cells to then get only the vesicles at different time during development. And very interesting, we found quite of genes or protein that they are associated with malformation. Some of them that we also are studying, like FAT4 endoxus or plaque 6 or cystatin B. But definitely, I don't want to focus on that. I want to focus on the fact that at all developmental stages, we found in exosomes L-Galus 3BP, so suggesting that it's really there. So it's packed in vesicle and it's secreted. So we thought, okay, if everything that it does is function is mediated by vesicles, we should just try to switch the medium in the organoid. So it was a very tedious experiment performed by Paola actually in the lab. So it simply switch the medium every day between control and mutant organoids, and we could completely rescue the phenotype, both the thickness of the apical belt, the number of apically dividing cells, and even the ectopic neurons. So really suggesting that all the phenotype that we observed in the organoid was mediated by extracellular secreted factors. So at this point, we wanted to understand, we wanted to study the role of this protein in vivo. So all this has been done in vitro. Sure, is a human model system, but we also wanted to see if in vivo this is happening. But of course, the mouse does not express this protein, which on one side is a disadvantage because we cannot downregulate it and study it. But on the other side, we have basically an in vivo model system in which we can artificially express the human form, so the wild type form that humans have, but also the one of the patient, the patient variant. So we decided to use the mouse model and electroporate and overexpress this gene, So this is how it looked like, an electroporated brain after 3 days. And what we could see when we electroporated L-Gal-3BP, with that we generated actually a region here with progenitors, which actually detach or delaminate, as we have seen in previously in the organoids, and form a region here that resemble, let's say, the outer subventricular zone. But obviously, to be sure that these are kind of basal radioglia, which will function as a basal radioglia, we had to look at later stages if this lead to something that is functionally relevant. So, and in addition, what we also spotted is that many of the cells were actually red but not green, so suggesting again this non-cell autonomous function. So the protein we know now that is secreted in vesicles, so we were not surprised to see that many of the cells were actually only with a phenotype were not GFP positive. So, and indeed, when we look a couple of days later, we could see that this base radioglia actually function as a base radioglia because we had generation of fold. And these folds were also having a laminin, so a basement membrane on top. And when we look again, we found many of the cells that they were in these folds, which are not GFP positive. So suggesting that really is form a niche of, with an addition of this L-Gal-3BP, and the niche change the environment, and this leads to the folding. And not only upper layer neurons are present there, but also deep layer neurons. And here's the quantification. So we got many times the folding, sometimes major, sometimes minor, depending on the size of the electroporation. What was interesting is that actually exactly the same mechanism that we found for a mouse was actually for the organoids, for human cells, we found also in the mouse model. So suggesting that every time that we electroporated this L-Gal-3BP, we could see that the apical belt here was becoming more loose and the cells could delaminate. So what then we decided to do was also to overexpress, Alex actually generated the construct with the patient mutation, so the variant of the patient. And what we could see by overexpressing this form of L-Gal-3BP, the two mutant forms that they were present in the patient, was that the number of times that we got folds was very limited, suggesting still that this mutant form of the protein is still functional. But much less functional, let's say. So it's not, and indeed what we could also see is that is secreted, so we could find vesicles when we overexpress this protein, so suggesting that is going to vesicle, is secreted, but its function is not the same as the control protein. So that's why we decided to do a final experiment, which is was quite complex. So we decided to overexpress in a cell line, neuroblastoma cell line, different form of L-Gal-3BP, so the control one and the two variants of the patient, plus a control plasmid only having the HA, so it's the vector that in which we inserted the L-Gal-3BP. And then we transfected neuroblastoma cells. We took the medium, we isolated the exosomes, and what we also did was to confirm and validate that these exosomes were containing L-Gal-3BP, and indeed you can see that they were containing both the controlled version and the two mutant form. So with that exosome, we put them on the side, and then we took a mouse brain, we sliced the mouse brain, we prepared cortical slices. And then we decided to treat these slices with exosomes. So we actually did the control without exosome, one with control exosome, so exosome, but only with the vector with HA. And then we treat them with the L-Gal-3BP exosome and the two variants. And then we analyze the position of the OPEX positive cells and also the neuronal position to see if we could recapitulate something that was happening in the patient brain. And what we could find, long story short, is that we have, when we overexpress the wild type form of L-Gal-3BP, we have again this generation of OPEX positive cells, and for the two variants a little bit, but much less. And we could also recapitulate with the patient that has the ectopic neurons, we could also recapitulate the ectopic neurons. So with that, I would like to come to the conclusion. So we actually found that L-Gal-3BP is secreted in exosomes. and then is modulating the extracellular space, then promote the generation of basal radioglia, so the switch from apical to basal radioglia. This basal radioglia leads to the formation of folds, and also this generation of the fact that these basal radioglia are not actually delaminating properly lead also to changes in the migrating neurons, in the position of the migrating neurons. So, and this I think could explain at least some of the, or maybe all, or we can try to, you know, summarize and try to figure out how we can connect all these cellular changes with the phenotype that this patient has. So we have seen ectopic neurons, which we could definitely recapitulate, and we assume that they are not migrating properly because they are generated in the wrong place. We see that this patient has microcephaly, and we can imagine that if we have less generation of basal radioglia, it could also be that there is less cortical expansion. We have seen gyrification changes, which also is very much in line with the fact that we have different basal radioglia. We have seen seizure in this patient, which could definitely be linked to the fact that some of the neurons don't migrate to the right place, but is also probably linked to another part of the project that I told you is still ongoing. So we don't have enough data to show now, but the fact that it seems to also be relevant for the regulation of the interneuron migration. So finally, it could be nice to speculate that some of these mechanisms could be linked to any of the possible mechanisms related to also autism spectrum disorder, which of course will be a variety and are a variety, and we can just add some small little pieces to this to understand these diseases, much more complex diseases. So, and I also would like to conclude saying that, you know, this is not the only, I started with that sentence, so I also want to conclude that. So this is not the only cell non-autonomous mechanism that we have found. So indeed, I didn't have the time to tell you all these stories, but we have also studied this year, showed this year, that another mutation in a protein called ECE2, so endothelin converting enzyme 2, which lead in patient to neuronal heterotopia, is actually very strongly having an impact. So this mutation have a strong impact on the formation of proper extracellular matrix. So we have changes in the matrix, and we could recapitulate some, neuronal nodules with this model. So really suggesting that the extracellular matrix changes and secreted factors are not just one case of the L-Galles TDP patient. On the other side, another mechanism that we have studied recently is that we have also modeled the mutation in cystatin B, which in patient leads, mutation in cystatin B leads to epilepsy. And what we have found also that cystatin B is actually a secreted protein and is secreted also very much in vesicles of the size of exosome, and we have found that in exosomes, and this also lead to changes in the developing mouse brain, but also we have seen that in organoids from patients. So having the mutant form of cystatin B leads to changes in the number of progenitors, but also changes in the recruitment of interneurons, which could lead to the imbalance between excitatory and inhibitory interneurons. So I don't have the time to tell you all this story, but I just wanted to come back to the idea that it's not just one component, one gene, one protein that leads to changes in the extracellular space and lead to something that is different in the niche. But many other genes seems to have this impact and that they are related to developmental brain disorders. With that, I come to the most important slide. So this is my lab, not the current teams, but since I have a lab just since 5 years, I thought I keep everyone in, so all the people that they came to my lab for a simple reason, because also many of the members that left, so this last part here, they were taking place in this project, but this is mainly the project of Fabrizia, of Cristina Chirusi, but also many other people in the lab have been strongly contributed to that. And in addition, I would also like to thank all my collaborators. This is also something I find very important because this is very, as you have noticed, this is a very it's a project that required a lot of expertise from many people, including clinicians, including experts in single-cell sequencing, in proteomics, in human tissues, and also in the institute, I have quite some collaboration. And the funding, and thank you very much for your attention, and I'm happy to take your questions.
Thank you very much, Silvia. It's a fantastic talk. You know that I'm very much in love with this story, in fact. So I'm always happy to see this over and over, and I always have new questions. So while I'm waiting, and maybe some of the attendees write a question in the chat. So I maybe start asking a couple of questions. So first of all, I was actually struck by the homogeneity of the exosome proteome. So I was wondering whether, because so we are doing also some experiment in that direction, I mean, a little bit, but I thought that the heterogeneity would be much larger. So are you biased? So did you design the protocol in a specific way to obtain a specific type of vesicles? Maybe I lost it, or what do you think? So
you mean the protein that they were in the exosome? Okay, this is just a completely fraction. So this is just examples. So we have many more protein inside of the exosome. And so they are different in different developmental stages, but definitely these are not all. I just found very interesting that many of the disease molecules that we were studying were actually in, and also many of the collagens that we also found secreted in the medium. So this is a bias selection. So definitely we did not enrich for that.
But so did I read it right that so there are certain proteins that are always coming together in the same vesicle, or you don't know exactly if they are together, or how I don't know even how many proteins eventually there are in those exosomes. And
so the exosome is super full of protein. So there are many. And so at the beginning, we thought maybe it's just the trash of the cells that we are analyzing. So everything that is not useful anymore goes there and is spit out. But actually, we are seeing that this is not the case. So we have different composition, depending on developmental stages. And we have also different composition depending on patients versus controls. And we also differences in what we find in ratio that we find inside and outside. So this is what for me was the most important part, to understand that this is not a trash, because independently on how much we express, how much protein we have in total, the one that you will find in the exosome is not correlated to that. So meaning that it's not, okay, I have 100 and I have 10 always in the exosome, and if I have 10 in the lysate, I have 1, but it's very different. So suggesting that there is a regulation in the secretion. But it's a bit early days because we are still analyzing all this data. But it seems that there is something that is regulating the secretion, and not just, and yes, so some protein, they are always there, but some of them, they are actually changing. So there are some, also is full of cytoskeletal proteins. So the tubulins and the actin are always there. So we don't have, so we have in mind, I think, this idea that vesicles contain 5 proteins, but it's definitely not the case.
So there's one question from Simona Lodato, and she says, wonderful talk, of course, and she's asking, and I think you answered to that at the very beginning, but do you know if ALGAL has 3 variants mutations have been identified in GVAS or de novo ASD or any other neuromental disorder? And yeah.
So this is if they have to identify. So they are actually, we have checked that. So there are very few mutation. And also if you look in the general variants that they are in human in controls, there are very few variants in this exon. So there are some variants, but very few in exon 5. So it seems that exon 5 is the most important one. We don't know exactly what it does because it's not very clear what this protein does. But definitely is not something that has been found in many other studies. yes, I would say that is, so there are some correlation with neurodegenerative diseases, but the most important role that has been found for this protein is huge accumulation in patients with cancer. So they find in the blood and a lot of accumulation of vesicles, or in the CSF even, with accumulation of L-galactose-3BP when there is in case of cancer.
I was wondering on the mutations that you showed. So they're both affecting the glutamate residue, and they are both from 300 amino acids on. And I don't know how big it is, the protein itself. But I was wondering, so first, whether you would know anything about the structure, why those residue exactly, and second, whether you think that maybe earlier mutations maybe leads to a complete loss of function or loss of proteins, and so maybe they are lethal, or whether you can speculate anything about that.
So we have tried to do some conformational analysis. So first of all, keep in mind that this is a very highly glycosylated protein. So maybe changes could really, in some specific spot, could change a glycosylation. What else can I tell you about this? So the deletion, so we have done the full deletion of exon 5. So instead of doing all the patient mutations, so the organoids that we have done is one with the one patient mutation, and the other one is the all exon 5 to basically recapitulate all the structure, and they're very, very similar. The other thing that I found very fascinating, but is still speculative, is that they are between, if I remember correctly, macaque and human, there are something like 5 single changes, very, very few. And this is one of the one that is different in macaque. So there are a few residues which are seem to be very important and for human, and this of patients, one, for example, is one of them. But of course, since we have so few patients, it's so difficult to speculate that. So I think it's a combination, and the other thing, we could even have a dominant negative effect, because one of the patients is heterozygous. So it could also be that either the one that is producing is not sufficient, or maybe the one that is producing that is defective is actually somehow catching something wrong. So we have tried to do some interactome studies, but with neuroblastoma, and of course they are not as good as if you do it with your right cells. And what we see is that the mutant L-galactose-3BP, actually they bind many more stuff compared to the control. So we are trying to go in that direction, but it's quite difficult.
I was also wondering, so I mean, one of the issue that there is with the organoids is that there is a continuous developmental process, right? They are continuously developing, and it's not that it's really regulated in time. And so it is difficult maybe to test a sort of a treatment approach. But I was wondering whether you could speculate if you would add those exosomes at one point in development, once you imagine that already sort of those foldings are not appearing in those brains, whether you could imagine to induce them later on, or so. I am just wondering, because of the patients, obviously, right? So are we able to do anything at all, and or what do you think about that?
I mean, it's the first time actually studying rare diseases. I mean, I don't study prevalent diseases, but rare diseases. So always when they ask me, do you imagine any treatment? I always say, well, it's going to be difficult that anyone will, with a single mutation in the planet, will, imagine a therapy. Also because you have a kid, and then he's already a kid when you discover that. For this was the first time in which I actually thought, with this exome, we can actually do something. They can go in, right? So if you know that there is this mutation, you could actually imagine to deliver this exosome, to deliver this protein. More and more, it seems that you can actually, I mean, we were not very successful in that. So you can pack whatever you want in an exosome in theory. I think actually you can enrich in whatever you want and not just pack whatever you want. But that's debatable, and then at some point could be even possible to have really exosome containing the exact composition of stuff that you want, but this you can deliver. So imagine that you can do that. You could indeed do that if we find that many factors are extracellular, not just one, but maybe many diseases are, you know, relevant for that. I think that could be doable, and depending on the type of obviously your phenotype that you expect, you can imagine to deliver them at different time, right? So obviously, if you want to help the basal radioglia to delaminate, you have to go at very early developmental stages, but with exosome interior, you could. So I find it a very fascinating option.
So I have been told that we will be kicked out of this Zoom room in basically now probably 1.5 minutes. So I would use that to thank you again. This was really, it's a fascinating, wonderful story going from disorders to basic biology, basically, and basic human biology. So thank you very much for sharing this unpublished work with us. So that was very much appreciated. And I hope for everyone else that you will enjoy the rest of the meeting. So
thank you very much, Gaia, for the invitation. It was very nice.
All right. Hello, everyone. From the Neuromatch 3.0 headquarters here. Welcome to this session. I'm your moderator. My name is Dobi Rahnev, and I work on perceptual decision-making and metacognition. The back-end support for this session is provided by Gauri Somashekhar. So thank you, Gauri, for making this possible behind the scenes. In this session, we'll hear 3 amazing talks. They're going to be focused on attention and measuring attention with high temporal resolution using MEG and EEG. I want to encourage everybody to ask questions. These are going to be short talks, just 5 or 6 minutes, so a ton of time for questions. There's no stupid questions. Please ask them in the Q&A, upvote the ones that you like the most. We want this to be as inclusive as possible, and we rely on your participation to make this happen. All right, so without further ado, let's get to the first speaker. This is Rachel Dennison, who is an assistant professor in Boston University, and she will tell us about voluntary temporal attention and how it affects the visual cortical responses. Rachel, take it away.
Hi, thanks, Dobi. See the screen? Okay, great. So hello, thank you. Sometimes matter more than others. When returning a tennis serve, for example, it's helpful to see the ball as well as possible at the moment it hits the racket. Voluntary temporal attention is the prioritization of visual information at specific points in time. Temporal attention improves perceptual sensitivity at attended times, but the underlying neural mechanisms are unclear. One potential mechanism is modulating the timing reliability of visual cortical responses, which can be measured using EEG or MEG as the intertrial phase coherence, or ITPC. ITPC quantifies the phase consistency of a periodic signal across trials. And we illustrate this here with time series from 5 example trials. For these well-aligned trials on the top, the ITPC is high, and for these poorly aligned trials on the bottom, the ITPC is low. We know that spatial attention increases the ITPC of visual cortical steady-state evoked responses to flickered stimuli. So here we asked, does voluntary temporal attention affect the timing reliability of human visual cortical responses. To answer this question, we did an MEG experiment. Observers performed an orientation discrimination task, deciding whether a grading target was tilted clockwise or counterclockwise from either the vertical or horizontal axis. On each trial, two targets, T1 and T2, appeared sequentially at the fovea for 100 milliseconds, separated by a 300 millisecond stimulus onset asynchrony. A pre-cue tone with 75% validity instructed observers to attend to either T1 or T2. A response cue tone after the targets instructed observers to report the orientation of either T1 or T2. To tag visual cortical responses throughout the trial, the targets were embedded in a 20 Hertz counterphase flickering noise. This stimulus flicker generated a 20 Hertz response in visual cortex called the steady state visual evoked field, or SSVEF. We tested 10 observers with 2 sessions per observer. Behaviorally, we found that temporal pre-cueing improved performance. Both perceptual sensitivity, D prime, and reaction time were better for valid than invalid trials. And this behavior confirmed that our temporal attention manipulation worked. In the MEG data, we first confirmed that the 20 Hertz flicker elicited a clear SSVEF signal. So here's a group average time frequency plot for visually responsive channels, which shows a clear 20 Hertz ITPC response. Next, we analyze ITPC across time, which I'll illustrate with 2 example observers. For both observers, as expected, the SSVEF amplitude is strongest at the back of the head, and there is a clear 20 Hertz oscillation in the average time series from visually responsive channels, as well as clear evoked responses after each target, T1 and T2. In the 20 Hertz ITPC time series here, we found that the target evoked ITPC response increased for some observers, but decreased for others. And this directionality appears to be mediated by either constructive or destructive interference of the target evoked response with the ongoing 20 Hertz oscillation. So we normalize the ITPC by subtracting a baseline period value and flipping all the peaks to the upward direction. So in this group average normalized ITPC time series, the T1 evoked ITPC response appeared larger for pre-QT1 trials than for pre-QT2 trials. And to quantify this, we conducted a peak analysis of the target evoked ITPC responses, which confirmed that pre-queuing T1 increased the magnitude of the T1 evoked ITPC response. And there was no significant effect of the pre-queue on the magnitude of the T2 evoked ITPC response. To conclude, we found first that temporal attention improved orientation discrimination performance, and more so for T1 than T2. And second, temporal attention increased the magnitude of the target evoked 20 Hertz ITPC response, specifically for T1. In sum, we found that voluntary temporal attention can change the timing reliability of visually driven occipital cortical responses. Thank you.
All right, thank you, Rachel. Here's some applause from the whole audience, just delivered by me. All right, so with these short talks, I know it's very hard to write questions on time, but if you do have them and you are not able to write them, just raise your hand and I will give you the microphone and you can just ask the question verbally. No need to write it. All right, so we do have a question right here from Jason Samaha. I will also give him the microphone so that he can also clarify, but The question is, great talk. Why do you think some subjects show constructive versus destructive interference? And Jason, if you want to follow up, feel free.
Yeah, thanks for the question, Jason. So I just want to keep everyone on the same page, say that what Jason's referring to is here, we see that, for example, for this subject, in the evoked time series, when the target appears, the evoked response seems to just add to the 20 hertz oscillation that's already ongoing, resulting in an increased ITPC response. Whereas for other subjects, the target seems to evoke a response that kind of interferes destructively with the ongoing oscillation, leading to a decrease in the ITPC. This is something that other researchers that we've talked to have observed in when you embed targets in an ongoing SSVEP or SSVF stimulus. And we've tested a number of possibilities for why some observers might show one of these patterns or others. I will say that pattern is very consistent across multiple sessions for the same observers. So it seems to be very observer specific and consistent. For example, we've tested, this is just a short list of like the many variables that we've tried to correlate with this phenomenon. And so we found, for example, that behavior doesn't correlate, the channel topography doesn't, the baseline ITPC, the timing of the peak, the phase angle of the time series at T1 onset, none of these seem to correlate with the directionality. But so for our purposes, we're interested primarily in the effect of attention on the ITPC response. So whether we have someone who increases or decreases, what we're interested in here is then the magnitude of the ITPC response and how attention affects that magnitude. But we'd be happy for any further suggestions of things to look at here.
All right, great. So we have a bunch more questions. So let's get to the next one. This is from Aparna. How were T1 and T2 selected or decided?
Is there, can Aparna maybe clarify the question?
Yeah, Aparna, I just allowed you to talk, so you can unmute and maybe clarify a little bit.
Hello.
Hi, we can hear you.
Hi, great talk. It was very nice, very interesting to hear your talk. I was wondering how you decided your T1 and T2. I mean, what made you decide that T1 will be around at 1000 millisecond and same for the T2?
So the question about the timing of the two targets?
Yes.
Yeah,
yes.
Great question. Great question. So for the timing of the first target, so first of all, the timing was always regular, so it was completely predictable. So the observers knew when these targets were appearing. For the first target, we wanted to make it far enough from the pre-Q so that people would have plenty of time to prepare their attention to really attend precisely at that upcoming moment. And for the interval between T1 and T2, we have found behaviorally that 300 milliseconds results in the strongest effects of attention on performance. So there seems to be some sort of limited time period where there are real trade-offs in processing between T1 and T2, where we can voluntarily control those trade-offs with attention, and 300 milliseconds is the peak of that time course.
All right, so that's great, and that's related to the next question. How do you interpret the temporal tension has a bigger effect on T1 than T2?
Right, great question. So I'm just going to go to that slide. So right, again, so we found that temporal tension seems to affect T1 more than T2. There are a couple of possible explanations. One simply is that we had a stronger effect of temporal attention on the behavior for T1 than T2. So we may have more sensitivity to see that larger behavioral effect coming out in the MEG data for T1 than T2. So it may be a kind of a sensitivity or a power issue. But another possibility is that the signal is actually cleaner leading up to T1. The MEG signal is cleaner leading up to T1 because there's nothing coming before T1. Whereas it's a bit noisier at T2 because T1 has already occurred and that varies across observers, et cetera. Or it could simply be that there is a smaller effect really for T2 and that the behavioral trade-offs we see for T2 are coming really from another source.
All right, thank you. And another question from Katherine Duker. Did you expect no difference in ITPC after T2 presentation, and how do you explain it?
I think this might be the same. Is this a similar question to the previous one about why there's no
I guess that's
pre-tuning effect for the
I didn't appreciate that.
second target? But if there's a follow-up to that, feel free to.
Katherine, I'm going to unmute you in case you want to follow up.
Oh yeah, thank you. No, you basically answered that question already. But my question would be, is the normalized ITPC after the presentation of the two stimuli, does that relate to the event-related field? Because the dotted lines, or the lines.
Yeah,
T1,
let me,
T2 lines that shows the onset of
more
the stimuli,
helpful
right?
slide here. So here I'm showing both the event-related field. This is the evoked time series, and the ITPC next to each other, and you can see the correspondences between these two time series. So the strong 20 Hertz oscillation here corresponds to this strong ITPC measurement, strong phase alignment across trials. And the ITPC peaks here correspond to how T1 and T2 affect that ongoing oscillation. So again, some subjects have an increase in this oscillation after the targets. Some subjects have a decrease, and that's that's reflected in the direction of these peaks. Does that answer the question? Or?
Yes, definitely. Thank you.
Okay, great.
All right, so very quickly, we have one last question from a partner again. And I think you may have addressed it a little bit so far, but do you think destructive response may be due to inhibitory process?
Yeah, so the mechanism of the destructive interference is something that we're interested in. We assume that it must be some kind of nonlinear interaction between the ongoing oscillation and the incoming stimulus evoked response. In terms of inhibitory processes, I think kind of the way to think about this this destructive interference is what it means is that that there's two things that might contribute to this. One is the just a decrease in the amplitude of the 20 Hertz signal across trials, and we do see that kind of in the single trial amplitude decreases when the target comes on, suggesting that the ongoing oscillation is disrupted for some people. And another possibility is that the incoming target evoked response causes some changes in the timing reliability across trials, so jitters somehow the timing. But we think it's more likely that it's simply disrupting the ongoing 20 Hertz signal based on our data so far.
All right, great. Thank you, Rachel.
Thanks everyone. Thanks for all your questions.
Okay, so moving on, our second speaker is Sarah Sheldon from University of Alberta. Sarah is a grad student there, and she tries to convince us that decoding covert attention is not only super cool, but it's also helpful in understanding the role of alpha activity in visual perception and attention. Sarah, take it away.
Alrighty, can you see my screen? Yes. Okay, and you can hear me? Okay, so this is very early work that I've been doing, applying very new techniques, at least for me. So I'm going to be talking about decoding covert attention on orientation perception task from EEG alpha activity. So, just to start off with, in the very beginning, Hans Berger showed that brain was never entirely at rest. It's constantly constantly functioning at different levels of activity. One of those levels, which he was the first to identify, is considered alpha activity, which is this 8 to 14 hertz. You can see in the bottom right, the arrow is pointing to such activity. This activity has been implicated in a wide range of functions, including perception and attention. However, despite almost a century of research, it's still not clear exactly how alpha oscillatory activity is related to, or how exactly mediates perception and attention. So there have been many ideas over the years. One of the ideas that has recently been proposed is this baseline sensory excitability model, which the important thing to take away from here is that the model proposes that a baseline or change in the baseline firing rate of sensory neurons is how alpha mediates sensory response. And it's important to note that this means that both signal and noise will change, leading to no change in visual discrimination, but participants seem more likely to respond that they saw a stimulus. This is in relation to this, so that is when there is no attention that is present. On the other hand, when attention is present, rather than changing just the overall baseline firing rate, alpha selectively enhances relevant or suppresses irrelevant sensory areas, which does lead to a net improvement in visual performance. A similar idea, not necessarily mutually exclusive, but another model is proposed by this group called the oscillation-based probability response model. What to take away from here is that they propose that rather than just alpha power being responsible for visual perception and attention, is really alpha power that's modulating gamma that then is what modulates the neural response. And they propose that this can either be done by alpha modulating gamma amplitude or alpha modulating gamma phase. Now, to try to get at which of these two models might be correct, first I took data from this task called the Q orientation detection task. Starts with a fixation, and then there's one of three cues that can show up. A cue either pointing to the left or right that would tell the participant that the target will show up on the right or left, and it's always informative. So if it's pointing to the left, it will always show up on the left. On the other hand, you can have this non-informative cue, which is at the bottom, which is doesn't give any information about which side the target is going to show up on. And you can see this cue is present for a variable amount of time, and then target flashes very briefly. I haven't really come up with a good name for this target except pointy thing. So the pointy thing will be pointing And when the directions, it will flash very briefly. There'll be a blank, a backwards mask, another blank period, and then response will come up where our response screen where the participant can use the mouse, and this response pointy thing will spin around, and the task is for the participant to try to match the response pointing thing to the target pointing thing. So I have data from 34 participants, all right-handed. So the task is already pretty hard, but to try to get it to be about equally difficult for everyone, I used a staircasing procedure. Before the task, so there's a separate initial task that looks just like that task, except persons should just say whether they saw it or not, and that was just meant to staircase the target visibility. So it's about equal for everyone. Equal number of trials for right queue, left queue, and no info queue. And the pointy thing, the target could have one of 24 orientations. So feature extraction. So what I was really interested in when trying to get at the differences in these models in which the data supports. So I focus on this this queue period, which is before the target, and to try to not have it be too influenced by the queue onset and the fact that this queue is only for a variable amount of time. All the epochs were aligned to the queue onset, and then the time period that I looked at was only the 200 to 1200 millisecond time period following the queue. So the features that I extracted from that time period was the alpha power and the cross-frequency coupling, which is the interaction between frequency bands. So there's two types, one that was alpha amplitude that modulates gamma amplitude, or amplitude coupling, which was measured using Spearman's correlation, and phase amplitude coupling, which I used the phase locking value from first proposed by Cohen, or first described by Cohen 2008. So the gray is going to be later analysis, so you can kind of ignore that unless you're really curious. And I can talk about that later. But right now, what I've really only looked at is to try to see if I can classify the trials that had no info queue, so the ones with the queue that didn't tell them whether they're left or right, versus the trials that had the queued, so trials where participants were told which side was going to be on so they could allocate attention to that side. So the idea is that if this baseline, or if the evidence supports this baseline sensory excitability model, then the trials can be, no attention trials can be classified just with alpha power. But if this oscillation-based probability of response model is more likely, then trials will be classified by either the amplitude coupling or the phase amplitude coupling. So I did the classification on each participant and ran a tenfold cross-validation. I used 4 classifiers, hopefully correctly, but like I said, this is all very new, so I'm still learning how they work. So it was 2 linear classifiers. One was linear discriminant analysis, and one was SVM, and then 2 quadratic classifiers, the quadratic discriminant analysis and quadratic SVM. And so, like I said, these are very preliminary results, and you can see there isn't really anything significant that comes out, but it looks like it's sort of working. But like I said, I didn't actually find anything that any evidence that strongly supports one way or another. But like I said, this is very preliminary results, and I'm again need to make sure that I'm doing this all right. But I am very excited because it actually got something that doesn't look like a total nonsense. So like I said, there's still a lot more to do. Like I said, I use the Cohen's, the phase locking value for the phase amplitude coupling, but there's a number of other ways to measure it that I was going to look into. Also, like I said, it's like a 1,000 millisecond time period that the measures are taken over. So it might make more sense to look at it in smaller time window chunks. Also, this is done by participant. I don't think doing it across participants will really improve classification, but it would be interesting to see if there is something that, some pattern that might be more easily picked up with more signal using cross participants. And like I said, I'm still learning how classification works, so I'm need to look into the hyperparameter optimization, and this was using all features, so like all electrodes, and so I didn't do any sort of like extraction of relevant features. I didn't do any PCA, so be interesting to take a look at that and other kinds of classification algorithms. So still a lot to do, and I'm very excited to see how this works. But if people have ideas or comments, suggestions, or I guess if you just think this is stupid, maybe don't tell me that. But if you have any comments or suggestions or questions, very happy to hear it. So thank you for your time.
Thank you, Sarah. Here's some applause from everybody in the audience. We have first question from Marisa Carrasco. And Marisa, I'll bring you up on stage. Actually, I think I can do that if you want to ask the question. So, how did estimation vary as a function of the Q? Is the question. And Marisa.
So I mean, I'm not sure. I might need clarification on that question. So what do you mean estimation vary as a function of the Q, as in?
I understood correctly, you had a queue and then you had a response queue, and for the response queue you said it's the thing that they have to adjust and then tell perceive. So that's an estimation task. So it seems that the first thing to do is just to make sure that your attention manipulation worked. So I was wondering how it changes the estimation.
Oh, so it does work. So at I did actually present those results at a different conference recently. So looking at the effects of Q, you do see less response error when there is a Q, indicating that at least people attention does seem to be used, and it does correlate with alpha. So
how does it correlate with alpha?
So there's, in addition to measuring the response error, there's also the response error gets fit to a model from Luck, Zhang and Luck, which is what that project, or at least that analysis, was focused on initially. So it was shown that alpha was, like I said, it's a different project, so I can send you those slides if you're interested. But
that to interpret the neural response that you're seeing, is important to know what the behavior was.
Yes. So the behavior. So there is a behavioral change due to the Q. I can tell you that there's definitely a behavioral change.
Did you see differential effect of alpha, whether it was contralateral or ipsilateral to the Q?
Yes. So I did see those effects as well.
Okay. Thank you.
Yes.
All right. So we actually are out of time. So let's move to our third speaker, who is Audrey Morrow from UC Santa Cruz. Audrey is a graduate student there, and she will tell us about how attention modulates alpha oscillations and activity in V1. Audrey, take it away.
Great, thanks, Dobie. All right, so I'll begin by talking about alpha and the C1 ERP, or event-related potential. The C1 ERP is the earliest visual evoked response, and it's considered to be an index of initial afferent activity into V1, or the primary visual cortex. So one interesting thing to note about the C1 ERP is that it results in polarity reversal based on how the activity projects out from the calcarine fissure, such that the upper visual field will actually result in a negative peak, as you see in yellow in the figure, and stimulus in the lower visual field will result in a positive peak, as you see in the blue line in the figure. So a study showed that when participants were passively viewing stimuli in the upper or lower visual field, C1 amplitude was able to be predicted by spontaneous or natural ongoing alpha oscillations. More specifically, strong pre-stimulus alpha power resulted in suppression of the C1 component, as you see in the thinner lines in the plot, whereas weaker pre-stimulus alpha power resulted in an enhanced C1 response, as you see in bold. So this shows us that your natural ongoing alpha oscillations have some modulation over this initial afferent activity in the primary visual cortex. So now we'll switch to talking about attentional modulations. There has been evidence that attention can modulate the topography of alpha power and also the C1 ERP. So there have been a lot of studies that have shown that pre-stimulus alpha power is modulated by where you are attending, specifically where you're expecting the stimulus to appear, as you can see in the figure below. And this change in alpha power topography is usually seen in the parieto-occipital area. So that is a pretty well-established finding. There is one study that has also looked at attentional modulation of the C1 ERP, or rather I should say many studies have looked at it. One study found a really clear attention effect on the C1 amplitude. So if you look at the solid lines, these are for attended trials where the stimulus appeared in the visual field that was anticipated. And so the C1 response is a lot stronger when you are attending to the appropriate visual field as compared to the dashed lines where you are not attending the appropriate visual field. But there is a lot of debate actually about whether attention can modulate the C1 ERP. Another group replicated this study, this Kelly study, pretty closely as far as the methods were concerned, and they did not find an attentional modulation of C1. So our question is, given the role of attention on alpha activity, and then also alpha activity on C1, we're wondering why it's so hard to find this attention effect on C1. So our goal was to use kind of these big, bold checkerboard stimuli to elicit a large C1 response to see if we can get at this maybe nuanced effect of attention on C1. We had participants engage in a contrast discrimination task where they were presented a cue that indicated whether they should shift their attention to the upper or lower visual field with 80% validity. So on 20% of the trials, the stimulus appeared in the opposite visual field. And if you look at the bottom right figure, this is just an example of what an upper visual field stimuli would look like. And participants would respond to which wedge had a greater level of contrast. In this example, they would respond with a left arrow button press, suggesting that the left wedge had greater contrast. And as has been established in lots of the previous literature, looking at attention, participants generally responded faster and more accurately to valid trials in our study as compared to invalid trials. But I will preface everything by saying that we have a very small sample size. We got interrupted by some social distancing guidelines. So as for preliminary results on alpha, we do see a really clear attention effect from the cue. So we can see that alpha topography changes based on whether participants are preparing to attend to the upper or lower visual field shown in blue and red respectively, following the cue, which is the dashed line in the plot. And then the topo plot on the right shows the difference in upper and lower visual field alpha power, and specifically also the electrodes that we examined for the left graph in the parieto-occipital area. And this is showing from a 200 millisecond interval following the cue and prior to the stimulus. So we can see that attention is clearly modulating alpha here. As for the C1 results, we looked at them by subject. The C1 can vary really widely across participants. So we selected a different electrode for each participant, depending on what showed the greatest upper and lower visual field peak. So here are the electrodes listed and then circled in red, all from generally the same area in the parieto-occipital lobes. So these are our C1 responses across subjects. Just a reminder that the C1 is the first peak that you see in red or blue. And the two things I kind of want to draw your attention to here are that the C1 does vary greatly across participants, as you can see from the differences in amplitude. But more importantly, the dashed and solid lines, which indicate invalid and valid cues respectively, are pretty much overlapped. So we're not really seeing much of an attentional modulation depending on whether participants are shifting their attention to the appropriate visual field or not. So even though we're seeing this attentional modulation of alpha, we're not necessarily seeing an attentional modulation of the C1. So just to kind of wrap things up, we definitely see that, as I just mentioned, pre-stimulus changes in alpha topography are seen when participants are preparing for upper or lower visual field attention. And while our stimuli did do a great job at evoking a really large C1 response across participants, no clear attention effect was seen. So some considerations might be that we have a lot fewer invalid trials, they're only 20% of the data. And we already have a small sample size, so there could just be some noise that could be mitigating some attention effect. Additionally, because we tried to use these stimuli to evoke a large C1 response, they're kind of bold and take up all of the screen. They do leave some of this after image effect on the screen. So we might consider masking them moving forward. The after image might be playing a role in allocating attention or how the C1 is evoked. But generally, even if we don't find an attention effect of C1, it could suggest some interesting things about the properties of alpha. So we did see that spontaneous ongoing alpha oscillations were modulating the C1. So maybe there's a difference in this attentional versus spontaneous alpha and what kind of effect it has on visual evoked responses. And specifically maybe depending on where it's originating from or what the motivation is. So we're hoping to, of course, collect more data in the future and be able to parse this apart. So I just want to thank everyone for your attention, specifically everyone I've worked with and the NeuroMatch organizers and all of you for listening.
Thank you, Audrey. That's an applause from everybody. So we have first question from Katherine Duker. And let me promote you to a panelist if you want to ask the question, Karina. In the meantime, I'll just read it. As alpha doesn't seem to have an effect on C1 here, what's your take on the role of alpha oscillations in attention? For example, with regards to the idea that gain modulation by alpha or gating by inhibition?
Yeah, so we've actually looked at a lot of studies looking at alpha and how it might modulate other ERPs or even like gamma lateralization and things like that. There's not really a clear answer. I guess right now we're trying to understand whether alpha might modulate this very earliest visual evoked response. It seems that alpha might be able to modulate some later responses like P1, N1, or even some like decision-making ERPs possibly. It seems like it has some sort of suppression modulation of distractors, but there's a lot of inconsistencies with the research. So we're actually kind of diving into that a little more. I hope that answered your question.
Okay.
Yes, thank you.
Great. So Marisa Casco has a question as well. Could the lack of an effect be related to the fact that the attendant area is so large?
Yeah, that's kind of what we were thinking as far as why we might want to mask the stimulant after presentation. Yeah, they're kind of large, and that could be driving, I think that's definitely driving this big C1 response, because we're seeing almost double or triple the amplitude compared to previous C1 attention studies. So yeah, I guess our hope was that by using larger stimuli, we would be able to kind of look at these possibly minute attentional changes on C1. But yeah, it could be kind of interfering with like both upper and lower visual field for valid and invalid trials are getting activated, regardless of attention. So we definitely want to consider masking it when moving forward.
It could be, if I may say so, just that also, rather than just considering masking, you want a task that is more spatially localized.
Okay.
This is a comparative task, so in reality, people have to attend all the upper or all the lower visual field, right? So another possibility would be to do the task to be dependent more locally. So it is
Okay.
more what you would see.
Like maybe farther from the fixation or something?
For example, yes. I mean, there are different ways, but yeah, or not to have necessarily a comparative judgment, but more of a local judgment. That's another possibility.
I see. Thank you.
Very nice presentation, by the way.
Thank you.
All right.
I have a question, but I don't think I can ask it in the Q&A. Is it? Can I jump
ahead.
in?
You
Okay. Yeah, really nice talk. I wonder how the stimulus that you use in this study relates to the stimulus that was used in the study that found an association between the spontaneous alpha, and the C1. Yeah.
We actually used the same stimuli that they used. We adapted the code to introduce variations in contrast, but actually this top figure was taken from, well, not quite that paper, but it was the same stimuli that were used, and this was cited in a review paper.
I see, interesting. Yeah. So yeah, part of why I asked, and maybe this relates to the contrast manipulation, is that if you think of like a contrast response function as if the contrast of the stimulus is very high, you might be in a regime where the neural response is saturated and the effective attention won't be very large. But if the contrast was a bit lower, you might be more in the dynamic range of the system where the attention could actually have a larger effect on the neural response. So I just wondered if you have been thinking about contrast or playing with contrast and how it related to those previous studies.
Yeah, so we had the right wedge was a standard at 80% contrast, and then the left wedge would vary plus or minus up to 20% contrast difference, but most of them were pretty close in like to the 80% contrast. But yeah, the stimuli that we used were taken from the passive viewing study. I'm not actually sure what level of contrast that they had it set to, but I know it was pretty high, and we did see that the spontaneous alpha modulated C1, but perhaps, yeah, during attention, it could be modulated differently. So maybe reducing it would also help reduce maybe some of that after image effect as well, and maybe we could kind of parse that out a little bit better.
Yeah, great.
Like having it just a lower, both of them set to maybe lower contrast levels overall. Yeah.
All right.
The feedback.
I actually have a quick question as well, and this may be sort of quite different, but there's a sort of a debate in the field on whether or not expectation, but also attention changes the bottom-up signal, or is just a later top-down modulation. And I'm wondering whether you think this kind of paradigm can address this kind of question at all, because C1 is actually pretty early, so whether or not you see modulation may actually have a implication for that debate.
Yeah, I guess that's kind of what we're trying to get at here. I don't know that I have a good stance per se, but I do think we're trying to assess how far back maybe this top-down modulation of attention can go. But I wouldn't be able to speak on what that would say about bottom-up modulations.
Okay.
Great.
So I see no further questions. There's a comment from Marissa that she was agreeing with our reasoning earlier on. So let me just thank all of the speakers and people in the audience for your participation and for wonderful talks. Thank you, everybody.
Thanks, everyone.
And yeah, please enjoy.
All right, welcome back to the NeuroMatch conference for this panel session on science communication. We're really excited that you're here joining us today, and I just have a fantastic panel of neuroscientists, of working scientists with scientific training who have decided to make science communication a part of their career in various forms. And as you'll see, it ranges from people who have gone full-time vocationally into science journalism, through people that are podcasting and writing articles and children's books kind of in their spare time, right? So I'm just really excited with what the panel is going to share to us today. I'm going to kind of go down a little bit so you know who's here, and then we'll go person by person and have a chance for everyone to give us kind of their perspectives for a few minutes, and hope that you'll chime in by posting your questions and such in the Q&A and in the chat. So if you can just give a quick wave, everyone, so people know who you are. We have Ali Caldwell, senior science writer at the University of Chicago School of Medicine, and the co-creator, writer, and host of the YouTube channel Neurotransmissions. We have Grace Lindsay, who's a postdoctoral research fellow at the University College of London and is the co-host of the podcast Unsupervised Thinking, and also the author of the upcoming book Models of the Mind, which I've taken a quick peek at and looks fantastic. We have Mark Humphreys, professor of computational neuroscience at the University of Nottingham. He's an author at The Spike and author of the forthcoming book, The Spike, A Journey Through the Brain in 2.1 Seconds. We have Tim Rickwarth, a lecturer in science writing at New York University and a freelance science journalist. And Thean Griffith, assistant professor of biology at the University of California, Davis, and author of the STEM-themed children's chapter book series, The Magnificent Makers. So thank you all so much for joining us here today. This would be the place where the audience would clap for you all, but you're stuck with me solo clapping for you. So I would love to just kind of go around the room here and have everyone give us a few minutes to describe how you engage with science communication, what your experience has been. And I'd especially love to hear some details about how you practiced, how you prepared, and also how you found the opportunities or maybe created the opportunities that you've been working with now. So Ali Caldwell, let's start with you. You may know her better as Ali Astrocyte from her Neurotransmissions channel. But Ali, why don't you tell us a little bit about your experience?
Sure, thanks for that introduction. Yeah, I'm Ali Caldwell. I was a graduate student at UC San Diego studying neuroscience, which is when I first got involved in doing science communication and science writing. And after graduate school, when I finished in 2019, I transitioned into institutional science writing full-time. So I kind of got into science communication almost through a back door in that when I was a first-year graduate student at UCSD, I learned about an annual tradition in my graduate program where we would create a music video to promote a party that we hosted. Normally would be happening this week. It would be during SFN, whenever SFN was happening in San Diego. And my partner actually had already been making videos for quite a long time, just for fun. And so we got roped into helping with that project and found that we really enjoyed, sort of making this video together. And then friends pointed us to the Society for Neuroscience annual video contest. And we entered the following year with a video about how brain lesions have taught us about the brain. And from there, we decided we really enjoyed doing this project together. And so we decided to launch Neurotransmissions. This was in 2014, 2015. And at the time, there weren't really a lot of educational videos on neuroscience on YouTube, especially not about basic neuroscience, like things that people could use to support their studying about how does a neuron send a signal, how does our sense of vision work, that kind of stuff. So we launched the channel in 2015 and we've been putting out videos ever since then. And kind of along with that opportunity, I started to gain access to a lot of other opportunities. So through Neurotransmissions, entered in a couple of other video contests that led to some other sort of network connections. I got involved in science Twitter, which led to a lot of really great opportunities to attend science communication and science writing conferences and experiences, including the International Wildlife Film Festival, the Science Media Awards, an organization called ComSciCon. And from there, kind of was able to build this portfolio, both of science writing for video, but also science writing for digital news outlets. And eventually that led me to the Bigelow Science Communication Fellowship when I graduated with my PhD. I worked with UC San Diego Medicine, but also with Scripps Institution of Oceanography and the Jacobs School of Engineering to do this sort of interdisciplinary science writing for UC San Diego. And then that led me to my current position here at UChicago. So sort of this winding path that started with one opportunity that wasn't even really science communication in and of itself, but really just got lucky to have someone in my life who could work with me on this project and let us launch this great experience and opportunity.
Fantastic. Yeah, I'm always amazed, even just in my science life, how one little serendipitous turn can open up a whole another direction that you weren't expecting to go down. So great. Thanks for sharing that story, Allie. Let's move on next to Grace Lindsay. And Grace, would love to hear more about your experiences in science communication.
Yeah, sure, thanks. Yes, so I guess I got started with science writing just in my first year of graduate school. I went to Columbia, and I just decided I'd start a blog when I was a first-year PhD student. And that was mostly, and this is kind of the thread through a lot of my science communication, it was a place where I could work through ideas. As a first-year PhD student, you're getting a lot, on you, a lot of new information, and you're also kind of expected to decide what you want to do long term. And so having an outlet to explore ideas that wasn't, the pressure of a classroom or anything like that, because, sometimes people are afraid of sounding stupid in a proper setting. But on a blog, it's whatever. So yeah, I blogged a little bit regularly through that first year about papers I wanted to read or ideas that were kind of turning in my head. And then having done that, kind of like what Allie was saying, other opportunities come up once you've done something. So I was able to write for the Dana Foundation because they were looking for guest bloggers, and I could show, well, I'm interested in blogging. And similarly, I started writing for the Simons Foundation because someone at Columbia knew that I was interested in writing and they needed someone to write things for them. And so, yeah, you just kind of bootstrap from there. I then, kind of halfway through my PhD, I started a podcast because, I don't know. No, it was basically, there's a podcast that I was a fan of about philosophy called Partially Examined Life, where it's just a bunch of people talking about a topic. They do some reading and they have an open-ended conversation, kind of like a journal club. And I thought, wouldn't it be cool if this existed for neuroscience? And so me and some of the other grad students at Columbia started this podcast. And again, it was like a way for us to read things that we wanted to read, but didn't perfectly align with our research, and to have conversations that, weren't so structured and strict and could be a little bit more open-ended and philosophical. So yeah, so I did a lot of episodes of that. And yeah, now I have a book coming out in the spring called Models of the Mind. It's kind of a book about the history and the current state of computational neuroscience. And so that was a really fun undertaking, and I can talk to people about that if they have questions. I know getting into book writing is kind of a scary unknown thing for a lot of people. But I should say, and I think Tim will probably talk about this as well, because he was the leader of this group when I joined. There's a group called New Right that I joined as a a first-year PhD student at Columbia, and that was probably, in some ways, one of the most impactful decisions that I made, because being able to see people workshop, it's a group of scientists and science writers where we workshop each other's pieces. So being able to see that process over and over was incredibly valuable for me for learning how to become a better writer, and also, occasionally giving my own stuff workshops. It's like peer review. It's like, if it doesn't kill you, it makes you stronger. So you got to go through it. And that was just really valuable. And also, even that's a New York-based group, the one that was started at Columbia, but there was a chapter of it in London. So when I moved to London for my postdoc, I joined the chapter there, and that's actually how I got involved in writing a book. So that group, both in terms of the mechanics of science writing and kind of the career knowledge that comes with it, that was really valuable. And I also went to ComSciCon, as Allie mentioned. It's a workshop and conference for grad students interested in science writing.
Great. A couple of things that I heard in there that I think are really important to bring out. You know, I think when people think about science communication, they often think of it as like something extra that you do on top of your real job, at least to get started. Your real job as a scientist, that is. And I loved hearing from you that, especially when you were an early grad student and feeling really pressed for time in your own work, that you were able to use these communication experiences, you know, to further your science, right? To help you understand things or read outside your area. There was a purpose to it. It wasn't just, you know, a service you were doing to the world. You had something to gain from it, you know, actually too. I think it's important to line things up like that.
It can be selfish, yes.
Yeah. Well, you need to be, right? There are a lot of demands on your time. So I think you need to be able to sell. It's not wrong. All right. Thank you, Grace, for sharing that. Next up, we'll have Mark Humphreys. Mark, can you tell us a little bit about your experience? All right. I think, is everyone else getting some broken audio there as well? All right. Oh, Mark, looks like you unfroze. You want to try one more time?
Yeah. Can you hear me now?
Can now, yeah.
Yes, right, yep.
All right. It looks like Mark is frozen again. So sadly, I think we're having some internet connectivity troubles with Mark there. So we'll see if we can get that corrected. But in the meantime, would love, let's see, can we try one more thing? Can we try and turn off video, Mark, and see if that helps anything? If we can just get your audio here. Try one more time, Mark.
Yeah, I'm still here.
Okay. Yeah, let's try this again and seeing if having the video off helps.
Okay, cool. Yeah, just jump in if you lose me again and I'll restart and you can pick up somewhere else.
Okay.
Yeah, what I was saying. So I was saying, yeah, so I came to SciComm really late. So I didn't really click for me until I was already a PI. So I'm like, I know I speak to many people who are enthusiastic grad students, postdocs who really want to get into science, deeply enthused by science communication, but it didn't click for me until
all right, I think we're losing Mark here again. So I'm sad because I love his writing on the Spike. I think it's full of humor and insight and information, and was really excited to hear his perspective here. But I think we're just having too many technical troubles. So I apologize, Mark, but I think we're going to kind of move on around the circle for now. Next up. Yeah, Mark, I see you with the message that you'll try and restart and rejoin us. So let's move on from there to Tim Reekwarth. And I apologize, Tim, am I saying your last name correctly? Is it Reekwarth?
I accept all pronunciations. That one works. That's fine.
Okay.
I didn't come up with this last name, so it's up to whoever.
All right, Tim, love to hear some more about your experiences and engagement with science communication.
Yeah, so I went to graduate school with Grace actually at Columbia, and I think we met in the Neurite group that she was talking about, or it's at some event associated with it. And I had a sort of writing background before I entered science. Unlike Mark, I came late to science, and so I had always been interested in a lot of the broader issues surrounding it and widely interested in many fields of science. And so in some ways, the PhD was a bit of an anomaly where I really focused on one particular question. And I did some writing during graduate school at the same time that I was doing my thesis work. And pretty soon, I would say probably 3 years into my PhD, I had pretty much decided that I would not be pursuing scientific research and would be developing a sort of journalism portfolio to work as a freelance after I graduated. And so that's what I do now. And I also teach still at New York University. And it's really great. It's a really wonderful way, as I think, people were alluding to. even if you're still in science, it's like a really wonderful way to engage with a broad range of different sciences and think about it from lots of different perspectives. And I would hope that it could inform, the science that you're doing or the, science communication you end up doing.
Great, fantastic. It's, I think, it's uncommon to see people, go to do a PhD, especially if they, if they have an inclination that they may not want to be a full-time scientist afterward. So I'm curious to hear about that process for you. Because you hear sometimes that when people make decisions after PhDs to go into other types of careers, like non-conventional careers, that they feel a lot of pressure and maybe some criticism from their mentors about it. You sound like you were very confident in that decision, at least midway through your PhD. You started building a portfolio. I just wanted to ask, did you, as kind of the one of the vocational scientists here, did you feel pressure to stay in science as a active researcher rather than a communicator?
Yeah, I mean, it's what academic researchers know. I mean, the first thing we should say is that you might call that like the conventional route, but it's not the most common one. I mean, the alternative career is becoming a PI, right? That's like the minority of graduate students do, right? So I think that first of all, we need to reverse that framing. But second of all, I've had a fantastic relationship with my PI and the, program and department as a whole. But it's what they know. They know they were the ones who did stay in academia. There's a vested interest in graduate student labor for their own goals. And so, yeah, they want you to be working on their projects and your projects because it's in their interest, even if they're fantastic people. And so to say, there wasn't any, untoward pressure, but the environment you're in, and, this is a larger structural question around science, the environment that you're in doesn't particularly encourage these kinds of activities or make space for them.
Yeah. I want to get back around the circle, but while we're off on this little tangent, I just want to circle back to Ali for a second as the other person that is vocationally a communicator, for your full-time job, and ask you, basically the same question. Did you experience maybe not overt pressure from PI or something, but just did you feel a pressure when you were making the decision to go into communication rather than follow this alternative, but maybe more expected track of continuing on to be a PI and then a research scientist full time?
Absolutely. I mean, I think it wasn't that I necessarily felt pressure to go into an academic track as much as once I said I didn't want to go the academic research route, a lot of people basically just checked out of my professional development, and I kind of had to take care of all of that myself. So I had to build my own network of mentors, had to really figure out how to navigate the non-academic job market, which is a very different ballgame. But I mean, I still get that. I actually literally just had a comment on a video the other day that said it was underwhelming that I now worked as a science communicator because I had gotten a PhD in neuroscience. And, it's frustrating. I think especially, finishing graduate school, like, I think everyone coming out of grad school kind of goes through this like weird transition of like, you've really had this identity as a graduate student for a long time. And it's really like, it's what you've been doing and it's the community you've been a part of. And it's been like your whole life is doing grad school and being a grad student. And so that's a hard transition no matter what you do after grad school. And then when you add this level of people kind of looking down on not going the academic route, it sort of adds this sense of like, did I make the right choice? Did I screw up? Am I contributing to the leaky pipeline? Why did I choose this? Is it because I'm a bad scientist? There's a lot that goes into that. So yeah, I mean, I think it's still really common, but as Tim said, like it's what they know, right? Like faculty often don't really have any awareness of other careers because this is what they've been doing. So I don't necessarily like hold a grudge or anything for the people at my university, but it definitely would be nice to have more faculty who are aware of other careers.
Yeah, fantastic. All right, thanks for indulging that little tangent. I want to get back around our circle here and hear from Theanne Griffith. Theanne, will you tell us a little bit about your experiences in science communication?
Yeah, sure. I'm really happy to be here. So I I think I'm only recently feeling comfortable almost calling myself a science communicator. So I'm a children's book author. I'm the author of the science adventure series, The Magnificent Makers, which is a chapter book series that's published by Random House Children's Books. And looking back, so I'm currently actually a PI at the University of California, Davis. That's, my main job, if you will. And looking back, I didn't intentionally go into science communication. I've always had two very strong passions, and one has been science as well as science education, and another has been storytelling or just kind of reading and writing. I've always enjoyed both of those. And so traditionally, my science communication was more directed towards science outreach. So I did a lot of brain fairs and went to elementary schools and spoke with children. And I've always been really passionate about getting kids excited about science. So I've always been excited about science and had access to quality scientific education, and I wanted that for all children. And so it's kind of a funny story how I began actually writing. I was on maternity leave with my oldest daughter, and I was sitting on the couch and I was breastfeeding her, and I was kind of probably watching like the Great British Bake Off or something like that. I was sitting there thinking, Thean, you've always wanted to write. You've always loved reading. You've always loved writing. You've always kind of played with this idea of writing books for kids. Like, why don't you just do it? Like, just do it. And so I did. I started writing books for kids. I started focusing initially on picture books. I was listening to a bunch of podcasts of how to break into the publishing industry because I had no idea what I was doing. And I kind of started getting really active, not only in science Twitter, but in, children's book Twitter as well, and started pitching agents on Twitter to try and get them to represent me so I could then submit my book to a publisher. And throughout all this process, I was actually emailed by an editor at Random House. And she asked me whether or not I wanted to, give my hand at writing a STEM-themed chapter book series. And I said yes right away, because this is exactly what my end goal was, to publish a traditionally published children's book about science. And so kind of to make that long story short, we did a lot of back and forth, and then the Magnificent Makers were born. And again, I don't think even upon the publication of this book, I realized that I was engaging in science communication. My main goal was to get children excited about science through reading. And a secondary goal was also to really feature brown and Black children on the cover of science books and highlight diverse characters being excited about science. And that's more or less how I stumbled into this. And it's been such a fun and amazing ride. And it's also allowed me to realize that indeed I am a science communicator, and maybe my target audience are 7-year-olds, but that's still a very, very important audience. And it's just been such a fun ride.
That's great. I think communicating to 7-year-olds is if anything more important than adults, because that's where we need to get them and start building science literacy, so we can have conversations in society with people who understand at least a little something about the scientific process in the scientific world. So I'm grateful for all that you all are doing. I heard once that, an analogy basically that, someone without a scientific background writing about science, it's like they're trying to paint a picture by looking at a photograph. Whereas scientists who are doing science communication, they're looking at the object. They have that firsthand knowledge of the processes and the phenomenon that they're trying to describe. And if we can make that really effective, it's better for everyone involved. In fact, we even have something in the Q&A posted here about, don't let anyone ever make you feel bad about doing science communication. There are examples of people, we won't have to go into details, but people, even being threatened or disparaged for it. So, Allie, you said there were some negative comments on your YouTube channel, but hope they didn't rise to that level. So, I would love to hear some thoughts on a couple of topics. I want to get to some practical nuts and bolts things that a few of you mentioned about breaking into the business. But before we get to that, I wanted to ask maybe a little bit more abstract question. I'm just coming out of the discussion that we had with the CNN correspondent, Tom Foreman, in the last hour. And he said something that I think is really important, but I don't feel like I understand how to do well. He said, you really have to connect with people by emphasizing why this matters to them today, not 50 years from now, why it matters to them today. You have to talk about impact. And I think those of us on the science side, many of us are doing basic science. We're not doing things that are intended to translate clinically. We, in fact, don't always know what the impact is going to be. It's curiosity-driven science. So I would love to hear from you all the thoughts about how you have tried to make basic science ideas. And by that, of course, I mean things that are not translational. They're not targets of treating diseases or something like that. Just curiosity-driven science about the world. How do you describe that in your various media in ways that communicates the impact of the importance, let's say, of that work, now, even though we don't know what it's going to be used for in the future? Who has his thoughts or experiences about that? Because I would love to learn more about that myself.
I mean, I can quickly just jump in and say, again, with my target audience being 7-year-olds for the most part, I'm not necessarily trying to convince them of the importance today, but I will say that I think regardless of audience and regardless of age, if you can tap into not just the impact, but the excitement. So if you're researching something that doesn't necessarily have an immediate translational impact, I think that's fine. And I would almost disagree that you have to demonstrate the specific impact. What you need to do is get people excited. Because when we go into the lab and we do science that's not translational, I'm just excited about it. So when I write my books, what I aim to do is just get kids excited about thinking about science. And I would imagine that same thing can work for adults. So if what you're doing or the science that you want to communicate may not necessarily have be directly related to treating disease, if you can just really get people excited about the science for science sake, I think that is a great tie-in, and even if it's just, talking about, let's say, transcription and how that works and how these little molecular machines are translating this cool gene into an mRNA and just kind of really bolstering up the excitement. I think that's a great way to get people engaged when there's not an obvious impact of the science.
Yeah, that's great.
Yeah.
Yeah, Tim.
Yeah, I would add to that. I think that's a great point that, for a particular kind of mainstream journalism, the idea of impact and relevance to people's lives might be an important consideration. And I think for those writers or journalists, the big decision comes at story selection. So you don't pick to write about things that have a bullshit relationship with disease or whatever, right? But I think that you can tap into other ways to connect to people if you're not writing for CNN, which is a sense of wonder or curiosity. I mean, we wouldn't even have an entire industry of space news. What does space news have to do with anything? Nothing. But it's just cool. And there's some of the most popular stories all of the time. So I totally hear what he's saying, but I just think that's a slightly limited view of science communication.
Yeah. Yeah.
I would also say that with neuroscience, it's almost it's pretty easy to get people interested in the brain. And so you can, I think maybe there's 2 routes to making people care about or get excited about it. You can just tell them the endpoint, the hope is that we understand the brain, and well, that would be great, obviously, and that's cool. So that will get people excited. Just that's the endpoint. So what can we do to get there? It's really complicated. And then also I think there's, and this isn't a surprise that people like to hear stories about people, but the details of a scientist's life are probably sometimes weirder than most people realize. I do computational work now, so my life is not that interesting. I sit at a computer or whatever. But my first exposure to a neuroscience lab was as an undergrad researcher injecting rats with cocaine. And like, I would tell that to the other undergrads that I knew, and they're like, what are you talking about? So just like the weird details of a scientist's life are actually kind of engaging. And then, you know, they get you into a discussion about the process of science and why it's as weird as it is and all of that. And I think the process of science, kind of the philosophy about how you determine something is true when there's like so many unknowns and like really working at the edges of what we know, like that is philosophically interesting. So that can be applied to any science.
Yeah. I have a good friend here who is a scientist at another institution in Atlanta, Sam Sober at Emory, and his claim to fame, or one of them, is building tiny headphones to put on songbirds to study how they learn to sing. And our families are friends. He and his family are frequently at my house. And let me tell you, he is a popular dinner party guest among my non-scientist friends because they can't wait to hear about the tiniest headphones in the world that you put on finches. It looks like Mark has rejoined us here. I would love if we could, take a minute and break and see if we can, get his summary of his experiences engaging in science communication, and then we can circle back to this topic. Mark, you want to go ahead?
One last try. We're having some serious internet issues this end, unfortunately. Yeah, what was I saying? So I was a late starter with science communication. It didn't really click for me till I was a PI. So I was a PI. I'd been a PI for. Can you still hear me?
Yep.
Yeah, cool. You all froze again. Good. So I've been a PI for about 3 years by the time it really clicked for me. So I'd got the lab started, got people hired, and was and key was my kids had turned from babies to toddlers, so I had slightly more breathing space. I took a moment to breathe somewhere around 2015 and thought, what should I be doing now? What should I be doing? As a and a science now.
Mark, I think we're losing your audio again here on.
Yeah. Okay.
Oh, looks like you're back. It unfroze. Let's see, maybe give it one more shot here, and then we may just have to abandon ship on this one.
Yeah, all right, sure. Where was I in my spiel? Oh yeah, so psycho, right? So the short version. So I started thinking, all right, I didn't have to talk about theoretical neuroscience was the breakthrough. Breakthrough was realizing I didn't have to talk about my work particularly, or I could just talk about all the work of other people that I really loved. So I'd always not enjoyed very much standing up and talking about my work at conferences and meetings. So I thought, oh, okay, cool. I can talk about other people's work. That's much easier. It's much nicer. And so I started giving some public talks, test the waters, and then I just started writing some posts, some blog posts, just to just start writing. So I've always loved writing, but I wanted to get into this habit of writing some posts about papers that I loved. And then sort of the fourth post I wrote went massive. So I thought, oh, this is working pretty well. So I'll do something structured with this. So I founded the Spike publication on Medium as a home for this stuff, and committed to a regular writing schedule to really sort of make time for it. Because as you said at the beginning, some of us do this in our spare time. So my day in, day out is running a lab, doing research. So I was writing blog posts on the train, on the way home, on evenings and weekends, whenever I could squeeze in the time. So I set a regular schedule to make it happen. So like this was once every 2 weeks for 8 months. I managed to keep that up, I think. And obviously that grew the audience, and that led to commissions from Medium for a whole series of essays. That led to me reaching out to other writers to come and join the Spike to write for it, and others approaching me, and a whole little community building up there. And the inevitable book. So I got approached by an agent sometime a couple of years ago, said, do you want to write a book? I said, yeah, sure, why not? It's fun. I don't know if Grace will describe it as fun, but it seemed to be fun at the time. So that's been in the works. So I had to finish it off as lockdown started in March, which was fun. And that's going to be, this is called, as you said at the beginning, The Spike, A Journey Through the Brain in 2.1 seconds. And that's going to be out in March. Yeah, and that's where I've got to. I think also you asked us to comment a little bit on the things that we liked most about science communication. And I think the thing that I particularly liked was the freedom to write in the way that I wanted to. So having written many, many academic papers, they're very constraining, right? You try to put any kind of style in, any kind of entertainment, any kind of story or anecdote or nuance, and the referees jump on it like you can't do that. So it's the freedom to be able to communicate the science how you prefer it to be done. That's the thing I like the most, I think.
Great, thank you for that. We have some questions coming in on the Q&A that I'd like to get to, but I just want to make sure if I cut off the previous discussion, Ali in particular, I felt like I cut you off. You were about to say something on the previous one. Do you want to chime in with anything else?
Oh, I was just going to echo what Grace said. And basically everybody has a brain, everybody has a body. And I think it really does a disservice to people who aren't scientists if you think that scientists are the only ones who are interested in those things. Yeah. Like people are curious and have a sense of wonder and want to learn. So I think it's not that hard to get people excited about science as long as they haven't been turned off of it already. Yeah,
that's great. A couple of questions from the Q&A that I want to bring into the discussion. The top one here that I see is essentially about whenever you're describing complex phenomena, you have to simplify it in order to communicate it to a broader audience. And there's a danger that this person feels, of doing that in a way that creates what they're calling a neuromyth, right? I think we've all heard these, right? If I hear one more time that we only use 10% of our brains, I'm gonna scream into a trash can or something, right? So the question is, how do you approach this problem in your efforts about science communication? How do you guard against neuromyths arising through your simplification? And what sort of advice do you have for practicing this skill set and others to aspiring graduate students? So anyone have thoughts about that they want to chime in with? Anyone feel like they've created a neuromyth that they want to share?
I'm definitely very cautious of this with writing these books for kids. And it actually is quite tricky, especially when you're trying to communicate to like young children where you really have to worry about vocabulary and simplifying things down. But I think really that is where the power of your scientific training comes in, because sometimes, I'm sitting there and I'm typing something and I especially for book 2 about the brain, and I started to write, I'm like, oh wait, is that true? Is that actually true, Thea? No, let's circle back and let's re-explain that. But because you have that scientific background, you kind of have that switch. So even if what's coming out eventually as you're simplifying it almost turns into a little bit of a neuromyth, you have that like editor guide that, a red flag comes up and you can kind of revisit that. So I would just say that that's the power of your scientific training. And as long as you can recognize when you're creating a myth, then you have the ability to kind of go back and correct it. And in terms of practice, I just write or vlog or, blog, whatever your avenue is, just do that a lot and share it with people. If you want to write for kids, write something and share it with your niece or nephew or son or daughter or whoever, and see what they think. And if it made sense to them, get feedback, I would say, for sure.
Yeah, I think the feedback is really important because it seems to me like a lot of the really bad kind of neuromyths probably get started through a game of telephone where someone wrote kind of a technically correct description and someone else simplified it and someone else simplified it and also added a twist for their own ends and that kind of thing. So if you can have a bunch of people read it and they can tell you maybe, what they took from it. And if you're like, oh no, that's not what I wanted you to take, then you can rewrite to make sure that it doesn't kind of spawn a bad thread.
I had the opportunity to see Alan Alda speak a couple of years ago, and he said something that I think about a lot on this topic, which is never underestimate your audience's intelligence, but always underestimate their vocabulary. And kind of what I took away from that is that, sometimes you're limited by space or time, but in general, you don't really have to like dumb things down or simplify things that much. Like people are capable of understanding complex information. It's just that they don't always have the same vocabulary that we do to understand how it all fits together. So I tend to think really carefully about how is my audience actually going to understand the words that I'm using. And this is something that comes up when I'm working with faculty to talk about their research, because as a scientist, you're taught to be extremely precise with your language, and words that mean things in a scientific setting don't always mean the same things outside of that setting. And so really thinking about, okay, how is somebody who is not a researcher really going to interact with and understand this information?
Yeah, I would add to that I really don't like the phrase dumbing down. And since we're talking to a room of maybe a lot of scientists, I can use this sort of metaphor, but I think about it as like a low pass filter, right? You want to preserve the most important parts of the signal and filter out the stuff that's maybe not necessary to the core idea. And with these neuromyths in particular, I feel like there's another thing going on, which is it's really more about the culture and the reader and what they want to hear in this stuff. And you know, the neuromyth of 10% of your brain has deep connections, has a long history and has deep connections to like wanting to realize your inner potential, right? And like those are forces that can't be corrected with like better science communication. So I think understanding the role that science communication plays in the broader culture, that you can't just like cram information down people's throat. You have to like understand how it works in the world and be a little bit more sophisticated about the relationship between science, communication, and culture.
Yeah, I think that's great. Yeah, it doesn't exist in a vacuum, right? There are things going on in the world, and there is a context to anything we put out there. I want to make sure to have a few minutes to talk about some very kind of practical tips for people who are aspiring. There's one in the Q&A, and I have one that I want to ask myself. We'll start with Jesse Parent's question, the Q&A. Any tips for taking notes about science-related events so you can create better written pieces of science communication later on? You know, at least I have a way that I would take notes as a scientist, right, about things that I want to remember, but not having worked, you know, vocationally as a science communicator, I would love to hear, are there different ways that you take notes when your end target is a piece of science communication rather than for your own life as a scientist?
I do take notes differently as I do as a scientist. As a scientist, I'm kind of very brief and just, you know, writing down references you want to look up later or something like that. For the purposes of writing something, especially because usually when you're working as a science writer, you are like reporting on something that's not exactly your field. At least that's been my experience writing for like the Simons Foundation and other things. So I'm much more comprehensive. Like, it's almost like verbatim, trying to get down kind of as much as I can, including noting where I'm actually writing down a literal quote, because sometimes you want to put a quote in the piece, so you got to mark that and everything. And just, you know, putting down phrases, even if you don't understand them in the moment, to look up later and all of that. So yeah, I'm just very quickly jotting everything when I'm doing it for the purposes of writing something. Because also if you're crafting the piece later on, you don't know actually which parts are going to be relevant. You might kind of change the angle based on something that happens later. So I just try to be comprehensive. And also I'm just, I like doodle anyways. So to have my hand doing something is good for my focus as well. So.
Anyone else have any thoughts?
Working as an institutional science writer, most of the kinds of notes that I'm taking are usually in conversation with a faculty member whose work I'm writing about. And so typically in that case, I am, you know, mostly transcribing or almost transcribing our conversation, but I especially listen for quotable lines. So I listen for like the soundbite, right? Like, what is this person saying that is either really going to give a glimpse of their personality or something really unique about this study, not necessarily the results of the study, but maybe something that was especially challenging about it, or that was really weird and interesting behind the scenes. But if I'm doing an interview on something that I know is going to be like really important and newsworthy, I'll often even record it, because especially now when we're all virtual, like I'll let them know that I'm recording ahead of time so that I can then go back and transcribe the interview directly if I really want to get those sound bites.
Well, then I'll chime in with my own kind of last question here, as we just have a minute or two to wrap things up. You know, many of you talked about ways that you engage that involve, you know, convincing an agent or some other, you know, some other party to invest in you, right? You have a book contract or you're freelancing your work. You're not just putting out a blog post yourself. Any tips for people who are aspiring to try and engage with agents or other people to contract work and actually do this vocationally and not just as a hobby?
I can speak to, if you're looking to traditionally publish books in kind of like the traditional market, definitely lean into the fact that you're an expert. Even if you're a PhD student and you don't actually have your PhD yet, you still probably know more about whatever your field is than the general public. So definitely lean heavily into that expertise, but you also have to know the market. You have to know what is out there, where your book fits into the market and where it can fill a hole. You know, what is missing in, you know, the market that you're trying to enter and how can you fill that? And also, again, leaning into your expertise would be my top 2 pieces of advice.
This hasn't come up yet, but I'm actually also writing a book and have been thinking about this because a friend of mine just published a book too. And I think a big key is to make yourself visible. And that's regardless of whether or not you're looking to write books or to freelance or to move into another kind of science communication career in industry or in institutional. Have a website, have a social media presence. You don't have to be super active. It doesn't have to be super detailed. You can be extremely professional. Like, this is not something that, I know some people are very social media shy, but people want to know who you are and what you do. And the reality is that we kind of live in an era where like everybody sort of has to have their own brand. So sort of figure out like, what is it that you want to do? What is it that you care about the most? And then sort of create a presence online that people can find and kind of verify who you are. Like having this presence online led to an agent approaching us and asking us if we wanted to write a book. So I think that's a really big part of the process right now.
Great.
Yeah, I would add, not specific to books, but there's a lot of very mystifying steps in these process. Like a book proposal would be one of those. Like, what does an agent do? What is a book proposal? And really getting to know people who have done that and sort of figuring out what the steps are from point A to point B, which are not always obvious. And in regards to like magazine, newspaper, or website writing, there's this weird intermediate stage called a pitch, where you have to pitch the editor what it is you want to write, and that's its own art form. And so you can get that demystified too. And there's some resources, particularly geared towards science writers. And I'd make a plug for the Open Notebook, which I'm sure many of you are familiar with, which has like a pitch database that gives you 200 pitches about how to do that. So by learning some of these little details, you can't just like wake up one morning and say, I'd love to write an op-ed for the New York Times because I know what I'm talking about, right? You have to hone a whole series of intermediate skills, and like you need to demystify those. So that would be my advice.
Great. I think given the time, we have to end on that note. Panel, I am so grateful for your time. Allie Caldwell, Grace Lindsay, Mark Humphreys, Tim Requarth, Theanne Griffith, thank you for spending this hour with us. Thank you for these tips and this insight. I'm sure there are a lot of aspiring science communicators and science journalists out there who are going to benefit a lot from it. So thank you again. You'll have to be satisfied with my solo clapping.
Thanks, Chris.
Thank you.
We are live on Zoom and YouTube is in the making.
Okay, well, thank you, Amit. And hi, everybody. My name is Ina Puce, and I'm going to be your MC for today. And I am very ably assisted by Amit Rahane today, who's doing the host on the back end, and we're very grateful to have him. We have 3 really interesting presentations today. We have 3 presenters presenting on BMI, and what I'm really excited about today is that everyone usually always talks about the motor aspects of BMI, and everyone forgets about the tactile system, and that's so important. It's so critical, and so I'm really happy to see that the work that people are going to be presenting today is on tactile systems. And so what we're going to do is we've had a little bit of a technical glitch. So what we're going to do is we're just going to change around our order today. So our second speaker's going first and our first speaker's going second. And we're going to start, and they both come from the same lab. So it's not the end of the civilized world as we know it. So we're going to introduce Luke Osborne first, and so he's going to be talking about sensory stimulation for improving phantom limb perception and control. So take it away, Luke.
Sure, Dr. Puce, thanks for that introduction. Yeah, so my name is Luke Osborne, and I'm a postdoc at the Johns Hopkins University Applied Physics Laboratory. And a lot of this work I'm talking about was actually started at Johns Hopkins University in the Department of Biomedical Engineering, where Katherine and I had worked together on this. But basically, the idea here is that we can use sensory stimulation to enhance this idea of phantom limb perception, and then that leads to improved control, which is really, really fascinating. So just to give you a brief overview, this idea of phantom limb sensation, it exists after an individual has a limb amputation. And so their limb no longer exists physically, but they can still feel it, and they have that sensation of that limb. And what's interesting is the regions of the brain that represent the limb are still there, even though the hand might not be. And so one of the things we can do is use signals like electromyography to capture muscle activity while somebody is trying to move their phantom hand. And we can collect that information and then generally decode it to understand what type of movement they're trying to make. But something we saw, which is really interesting, is that you can provide sensory feedback, so stimulation to the nerves that are still there, and that actually helps improve the ability for somebody to move their phantom hand, and then our ability to decode that information. And so what this looks like is we can find regions of the residual limb, so the limb that's left after an individual has an amputation, and we can electrically stimulate it. And what that does is it creates a tactile perception in the phantom hand. And so this image here is showing a few individuals that we've worked with that when we stimulate parts of their limb, they can feel it in their phantom hand. And they describe these sensations maybe as a pressure or a vibration or something like that. But what we saw and what everybody would say after we do this stimulation is that it felt like they had a better perception of their phantom hand. So, you might expect this is if we're stimulating the sensory aspects of the phantom limb and they can feel it, then they it's more front and center in their mind, so to speak. But one thing that we weren't quite expecting that we saw is that this actually leads to an improvement in their ability to make movements with their phantom hand. So what we did is they would come in, say in the morning, and we would show them pictures of different hand gestures. So maybe pointing your finger or closing your hand all the way, and we would record the muscle activity. And then we would take a break and go do some sensory stimulation. And then we would come back to this same movement task, and we saw that people were getting better later in the day without necessarily having changed anything about where we were putting the electrodes or the images that we were showing them. So this is pretty interesting because generally you think of sensory feedback being used for if you're going to grab an object and then you can feel how hard you're grabbing that object. So we wanted to see if there's some long-term effect. And so we tracked an individual over 2 years, and we saw that the perception of his phantom hand, these sensory maps remained relatively stable over a 2-year period. And his EMG control over a period of about 1 year didn't have a huge increase in performance, but rather we saw some short-term improvements. So within a single day, we were able to see these little bursts of improvement between before having received any sensory stimulation and then after receiving sensory stimulation. Their EMG, our ability to decode that EMG signal was improved. And so this really just translates into better prosthesis control and movement. And we did this where somebody used their prosthesis to grab an object and move it. And we did this task both before and after the stimulation. And we found that people were generally getting faster at this task after having received some sensory information. And very quickly, I want to close with another exciting aspect, and I think Katherine will talk a little bit more about this in her talk, but you actually see changes in the brain regions that more or less represent motor activity. So, you know, we basically recorded neural signals while they were making these movements, while they were receiving stimulation, and then after they had received stimulation, and what we saw was this heightened sense of activity, even after we had taken away the sensory stimulation. So it leaves us with a whole bunch of interesting questions, and I think maybe the interactive portion of this talk is a good place to maybe get into that a little bit more. So I'll pause briefly and hopefully answer any questions, or we can maybe dig into some of these discussion points.
Yeah, well, thank you, Luke. That's certainly a very, very nice, comprehensive introduction to the lovely work that you guys are doing at Johns Hopkins. And I don't see right now, Amit has not given me any questions from YouTube, and I don't see any in our Q&A yet. So let me just let me ask you a couple of things that occurred to me. You know, you had the different kinds of sensations that were listed that these people were experiencing in their phantom limb, but I noticed that one was missing, and that was pain. And so that is interesting to me, because that, of course, uses, you know, the small C fiber pathways. And so were these this person was not experiencing any painful sensations in that phantom limb?
Yeah, it's a really interesting question, because there's a couple of different types of painful sensations. You know, there's what you and I might think of discomfort or pain if you were to grab a sharp, pointy object, right? There's that mechanical pain. And then there's also this idea of phantom limb pain, which is maybe a persistent discomfort that you have in your phantom limb after an amputation. And so in these particular individuals, they weren't describing having had phantom limb pain to a great extent. I think one of the areas that, you know, is emerging, and something that we're hoping to look into, is does this type of sensory stimulation actually help mitigate something like phantom limb pain? So while we're not showing any painful perceptions here in this image, that is a fairly common occurrence, but there's some evidence where people have shown that, well, you know, sensory information can actually help reduce this discomfort of phantom limb pain. And there's also other evidence that shows that by training with your prosthesis over time, you can actually help reduce that sensation of phantom limb pain. So some of this work we're showing here, you know, it might fit really nicely into this idea of how can we further mitigate or get rid of painful sensations that people experience after a limb amputation, because, you know, we know that additional sensory information should help mitigate that, as well as continued prosthesis use. But we're also seeing this interesting effect where the sensory stimulation seems to also be driving prosthesis controllability. So maybe there's a way that we can design these interesting stimulation paradigms that will, you know, help even further reduce these painful sensations. And so that's, you know, one of those open-ended questions right now, which is exciting because it gives us additional things to look at and think about.
Mm-hmm. Cool, thank you for that. And the other thing is, I said to the other speakers in the session, feel free to unmute and jump in with questions if you've got questions for Luke too.
Yeah, if you don't mind, Luke, I do have a question. So you mentioned that even with without the limb being intact, there still is that representation in the somatosensory cortexes. I was wondering if after, if you had checked after these procedures, if there was any change in the activity over the somatosensory cortexes, or cortices, if there was any change after the training that you had done with them.
Yeah, that's a really, really good question. And I think it brings up a lot of interesting points. We didn't necessarily check, before and after amputation, for instance, where you might expect to see, or traditionally you would think that you might see some changes. But what we did notice were changes in general neural activity, depending on the type of task that was being done. So, for instance, this B image is showing like what the neural activity more or less looks like while you're stimulating, but they're not moving. And you start to see some, okay, maybe there's some sensory motor activation here in this area. It's interesting because, some people might say, well, the limb is gone, and so that cortical region doesn't represent the hand anymore, but there seems to be evidence that might not necessarily be true, and there's still some part of the cortex that still represents the limb. But I think what's interesting is, say, for instance, we perform some sensory stimulation and we see activity in the sensory motor regions of the brain. And then we take away that stimulation. But then if we look, if we peek back in 15 to 20 minutes later, which is kind of what this, the far right image is showing in the green, you still see some heightened activity, if you will. So it's exciting because, it says, oh, look, there's something here that we should be paying attention to. But we also don't know exactly what causes that or why we're seeing this. But I think one of the takeaways we had was, well, there seems to be some short-term residual effect from sensory stimulation that is still influencing the sensory motor regions of the brain, even after you take it away, which is exciting, and that might have some implications for short-term or long-term improvements in how somebody might use their prosthesis.
Well, that's very cool. And the other thing too, Luke, is it makes me think of, particularly now that you've got that map up there, that second topographic map makes me think of mu rhythm. And that's you're probably looking at that 10 hertz component of the mu rhythm. There's no movement. The limb, they're not trying to move. And of course, that distribution changes as the movement occurs, and they're watching the screen, they're watching the cue, they're getting the visual cue, the distribution of activity changes. And so that's a really nice demonstration. So I have a quick one for you. What about the beta component, the beta sort of component of the mu rhythm? Have you had a chance to look at that?
No, we haven't, but that's really a good question, because now it gives us something else to do in the next, in the next several months, right? That's another thing we can start looking at. So thank you for that. Yeah.
Okay. Well, on that note, because Katherine is coming in from the same lab, but let's get Katherine a chance to get settled, because she had a bit of a technical hitch. So Katherine, let's see if you can get your slides started and unmute and start your slides. I'm not saying that properly. Beautiful. And Katherine, also you've got 5 minutes, and what I'll do is I'll hold up my finger like this when you've got to 4 minutes and you've got 1 minute left. Okay?
Okay.
Thank you.
Thank you for the introduction. Hi, everyone. I'm Katherine, and today I'm going to share the work on studying the effects of sensory stimulation on cortical sensory motor processing in individuals with upper limb amputation. And this is joint work done at Johns Hopkins and the National University of Singapore. So here is an illustration of the brain. And when we think about a bidirectional neuroprosthesis, there are two distinct paths. One is from human brain to machine for generating motor movements, and the other path is from machine to human brain for somatosensory functions. And we term the latter system a machine to brain interface. And recent developments of sensory stimulation techniques in our lab and in others as well demonstrates the ability to elicit these touch-like phantom sensations that Luke just described in individuals with upper limb amputation. But here specifically, what we are interested in answering is the following question. That is, how does sensory stimulation affect and aid the perception of phantom sensations and movement at the cortical level? We are also motivated by several recent studies, and just to show an example, the work by Serino showed that through target muscle and sensory reinnervation surgery, it improves functional connectivity between primary motor and somatosensory regions, but not with other higher order processing regions. And therefore, in our study, we want to focus on sensory motor interaction and multisensory processing using functional connectivity analysis. So this is the same or similar experimental paradigm. We used EEG to record brain signals and transcutaneous electrical nerve stimulation, or TENS, to elicit phantom sensations. And we asked each participant to associate TENS activity regions with a particular hand movement. So at different stages of our EEG recording, the participant received different combinations of a visual cue to perform the hand movement and sensory stimulation to activate the corresponding regions in the hand. And we focused on stages 1 and 3, that is making a hand movement with and without sensory stimulation. And we did this experiment with 2 amputee participants and 3 able-bodied participants. We made use of the temporal resolution of EEG and selected the beta band activity. We constructed a dynamic brain network first through source localization and then computing functional connectivity with a sliding window approach. And this gives us a dynamic functional connectivity network as shown in the cartoon here. So our experiment involved a visual cue, sensory stimulation, and motor movement. And we selected 4 functional systems that are relevant to our experiment, shown in 4 colors. We focused on functional connections to the motor system. And here I want to highlight our results that show sensory stimulation inducing increased number of connection paths. And each circular plot here shows pairs of functional connections to the motor system that showed a significant increase with sensory stimulation. And the right and left of each plot indicate the right and left hemisphere. We observed that the paths that start from S1 and S2, so primary and secondary somatosensory, the blue bars indicated by numbers 7 and 8, are to the premotor system, so numbers 4 and 5. And in amputee participants, we further see a greater number of connections from the multisensory processing region, the green bars 10 and 11. And these increases suggest that sensory stimulation enhances functional connectivity between the somatosensory, multisensory processing, and motor regions. To further understand the temporal profile of the increased number of connection paths, we divided the total 2 seconds of experiment into 3 time intervals. And interestingly, we observed that the early phase showed the most increase in connection paths. And we observed that all paths from S1 to the motor increase in the early phase, while from S2 to motor, they show up mostly in the middle phase. And additionally, we observed that the extended increase is involved in multisensory processing regions over the first 2 phases, which further suggests that through stimulation, it recruits higher order processing regions to aid the subjects to complete the motor task. And so really brief summary, we show that sensory stimulation enhances functional interaction between the somatosensory, multisensory processing, and motor systems. And these increases are most significant during the early phase of sensory stimulation. And here are a list of further questions for discussion, including the multisensory integration, use of EEG, and others. With that, I want to thank you for listening.
Thank you, Katherine, and that's it's great to have those questions as well for us to dwell on. But I do have a question for you, and I noticed that the late activation phase brings in the visual networks, And so obviously that, yeah, there you go, the late phase, just on that top there in that first amputee subject. And I'm just wondering what would happen to the system, and obviously those visual systems are active initially early as well because they're watching, you know, what's on the screen. But what do you think would happen if the person was actually moving, say with an auditory cue, and they were asked to move or think about moving their hand? What kind of connectivity profile would you see then?
Okay, I think so. If we're blindfolding them with the so they're without visual cue, but instead using an auditory cue, I think we would probably see a similar activation in the early phase, because at first they are given this cue to make this movement, and it's possible that this activation will kind of die down sooner, because for auditory, if it's just like a one moment cue, then afterwards, if they're not receiving any other auditory, it's possible that we won't see auditory activation in the late phase as we see here in visual.
But here's the kicker though. Do you think that they might also visualize, even if you don't show them the visual movement? Do you think that in their mind's eye, whatever that thing might be, that they might be visualizing moving their hand, and that you might actually see this late phase activity in those visual regions? Would that be possible, do you think?
That's really interesting thought. I think it will be interesting if we actually observe this, but I do think it's possible. It also, I think, kind of depends on what instruction we give them, in terms of if we want them to actually imagine the movement if they're not seeing, or if we want them to restrain from imagining this. That might create a difference.
That would be really interesting to check out, I think. That'd be really, really cool.
Yeah.
So Giana, do you want to ask Katherine a question about her work at all? No, you're good. Okay, very good. Okay, so we have a very shy audience here. So perhaps, Katherine, you might want to go to the questions, the discussion questions, just so any of the three of you can jump right in. About which one would you like us to tackle first, Katherine?
I think in general, it would be really interesting to think about how do we really incorporate multiple sensory modalities in terms of rehabilitation for these participants, and how can we make use of them in a long-term way?
Yeah, and so when you say that, are you thinking of having a naturalistic type of paradigm for experimentation, or are you thinking more of nailing things down with set kind of auditory and visual kind of stimuli? Talk a little bit about how you might see that unfolding.
Yeah, I think initially we might start something like more in a lab setting, where with set and pretty unnaturalistic cues. But later on, it'd be interesting to look at how if we're in a more naturalistic setting or an actual daily living situation, what can we make use of these stimulation modalities?
Okay, Katherine, now you do have a question from our audience, and they say, "Hi, great talk, thank you. Were the sensory percepts only tactile, or were you able to elicit the sense of any movement or proprioception within the phantom limb?" That's an interesting question.
Yeah, I think from our experiments, most of the sensations elicited were just tactile. And because we were asking the participants to associate activated regions in the hand with a movement, they kind of think about where in the hand they feel when they're making a certain movement, but I wouldn't necessarily say that that is proprioception.
Okay, well, thank you. Thank you for asking that question. And we have another one, the question actually coming in from Hannah Block. Do you have any ideas about what multisensory activity is contributing to motor cortex?
Okay. I think if I understand the question correctly, I think for multisensory processing in our study, it is mostly visual tactile. And here we're terming it as mostly just kind of a place in the brain that incorporates both visual information and tactile information in our case. And so for further experiments, it would be interesting to actually introduce multisensory integration, which kind of gives them a visual feedback of what they're actually doing.
Mm-hmm. Yeah, that's a really good way to do it, and maybe to do, and maybe to have tasks that have different granularities of spatial resolution too. You know, ones that have grosser motor movements, ones that maybe have finer motor movements. Perhaps that might also be something interesting to go for. That's really fascinating. Really fascinating work. Okay, so we've talked about multiple sensory modalities.
Do you mind if I ask a question to
Of course.
Katherine? So do you have a sense of if certain hand movements might create more, say, increased connectivity than other types of movements, right? So you showed that sometimes like the participants saw different hand movements, but if you just picked out a few hand movements, would you expect some to be better than others in creating some enhanced connections, or are they all more or less equal?
I think in our analysis, we kind of grouped all the movements together. And so if a participant made two movements in different trials, we just grouped them together. If we look at movement-based activity, it's possible to see differences, but also I would think that we might not have the fine resolution to actually distinguish those.
Okay. Well, I think we're probably ready to move on. Thank you, Katherine, for that. And that was a very interesting discussion. So thank you, everyone, for weighing in. And now we move to Giana Canestro, who she's from Florida Atlantic University, and she tells me that the paper on this work that she's presenting is being written as we speak. And she's going to talk to us also about tactile perception and human neuromarkers in tactile perception. Giana.
Okay, so let me go ahead and share that. Okay, so we're going to be looking at the human neuromarkers of tactile perception, kind of discussing some issues and things we need to work on in that area. So of course, we want to restore some sense of touch in those who are limb absent, whether traumatic or congenital. We need to develop these tools for unobtrusive study to implement them into a sort of bimodal interface, kind of like Katherine mentioned, having from prosthetic to brain and the other way around. We do need to look at the user's brain for these responses and trying to make sure that we're keeping the tactile event as uninterrupted as possible to keep it as natural as possible in terms of the recording of the sensory input there. So the sense of touch is, I'm sure as the panel is familiar, one of the least well understood senses here. It has a very complex pathway. While we would ideally have a figure like this look like this lovely freeway, it often looks more like this with converging and diverging pathways here. So for this particular talk, we are looking at both more simple and complex sensory qualities here. So just a quick overview of some apparatuses that are being used. There's a lot, and I'm sure quite a few of us are familiar with a lot of mechanical stimulation that are being used that are custom or purchased specifically for that purpose, that then make it difficult to reproduce those experiments, those results, and get more of a universal response there, more specific. So for oscillations, we have the theta, we have some sigma, mu, or alpha, which the naming of that in itself is also an issue in the literature as well. Beta, and from the literature review that I'm currently doing, there's a suggestion that there's potentially a difference between beta that can be entrained and other beta, gamma as well, and then the separate sigma kappa versus the ultra fast there. And this is just from the overview that has been done, just to see what responds to what, where we see these oscillations presenting themselves. Some of them, like mu that we were discussing earlier, tends to present, in the suppression rebound and is often coupled with some beta. Gamma is a little bit more picky, sometimes with pain and things like that. And then, of course, there is the fun confounds and covariates that like to throw in our little, throws in a monkey wrench there. So these are just some of the things we do see for these oscillations for each specific frequency band. We do see that different covariates and confounds here are affecting them differently. So theta, mu, based on attention, suppression, but some, as the beta entrainment there as well, don't necessarily have any identified, the same with the sigma and kappa, the ultra fast, that aren't as well studied. And even affect, like Luke was mentioning, what may be painful for one person may not for another. So these qualities of what is pleasurable, what is painful, can also affect all of these, the expression of these oscillations that we're looking at as well. So there's a lot to do. We've got a fun little checklist here. So we do have to work to kind of level the playing field here and to understand each of these oscillations and how they correlate to their confounds and covariates as well, with, again, specific attention to the naming, the recording methods, all of the nitty-gritty details in there. And then also the development of specific stimulation techniques, specifically hybrid interfacing using, pressure and vibration, or, any combination of simple tactile events. But it also needs to be very precise, both spatially, time-wise, in the recording and application too. And of course, this has an application then in the rehabilitation and teleoperation and the development of prostheses that work bimodally as well. So any fun? Seems like we've got maybe some fun questions.
Okay, thank you very much, Giana. That's you really highlighted a real issue, nomenclature, and this is why I'm a best practice aficionado. And we've got together guidelines, Cobitus guidelines, which are available on the Open Science Framework, and that was the first article that I put there about nomenclature and frequency bands. There is a and then I've put in a perspective article to Nature Neuroscience where we discuss that. Very, very important, particularly for people trying to do meta-analyses and trying to understand the literature like you're trying to do. People are not using guidelines that the International Federation for Clinical Neurophysiology advocate. And this is stuff that we've also tried to incorporate in our COBITUS guidelines for OHBM. Very, very important. And thank you for mentioning that. It's a real problem. And particularly when we get into these sensory motor rhythms with, we're in the mu region and they have two components. One is sort of in that 10 hertz region, the other vicinity, the other one's at about the 20 hertz region. People name them alpha and beta. And that confuses people in literature because their reactivity is very different to the posterior rhythm that we call alpha. So that's a real challenge and a real problem. So thank you for highlighting that. And I'm sorry, I'm going to get off my soapbox now. Do the other speakers have questions for Giana?
Sure, yeah. John, thanks. That was really interesting. You mentioned the need to develop a stimulation apparatus, and one of the main points being you wanted to have good spatial, temporal, and functional precision. And you highlighted a lot of different types of stimulation, like mechanical, right? And then maybe there's electrical. If you had to guess, or what you're thinking on which method or modality might be best in some regards, or do you think some stimulation approaches might be good at one thing but not others? And is there a way of working around that so that you get the best of both worlds? And sorry, that's a really hard question because obviously it's something everybody's trying to find the answer to, and it seems like you thought a lot about this. So I'm just curious, like what your thoughts and opinions are on, what type of modality you think might be most fruitful or not.
I do think that the development and utilization of stimulation apparatus that can potentially apply different sensory qualities, like the one that I mentioned. One of the developments in my lab is a vibrotactile, but also pressure applying. It's an armband. That's something that the reliability of. You can have one or the other. You can measure the specific application time and duration and things like that, as well as choosing to do multiple or just alternating or just one. I think a lot of the temporal precision is not only in the specific stimulation application, but also on the recording side as well. I think there needs to be a lot of development in the creation of these stimulation methods, but it also needs to become more of a across the board acceptance and utilization of these techniques, because even if they're there, if we're still using the things that we've been using forever, it doesn't really help us get that nice even comparison across the board.
Sure, and it may be interesting to think about, if you say you have an apparatus like that, it'd be cool to think about adding in additional modalities like temperature, right? Like imagine you're able to put in like a little thermal heater or cooler in addition to your vibration and your pressure, right?
Yeah, for sure. I think the most that we can get into one while still maintaining the integrity, the precision of that would be ideal.
Absolutely.
It's very, very. Lots of new developments. Let me ask you a question, you guys, about EEG. Of course, is really developing now with these portable EEG systems, and you want to talk a little bit more about bringing this stuff out of the lab and home to the person's home, and how you see that developing. And this is a question to any of you.
Yeah, maybe I'll start. I guess anytime I see anything that has like the translation or mobility aspect of it, I get very, very excited. And then seeing how well it works is maybe a different story. But I think something like an EEG cap that you can wear around and perform activities of daily living unencumbered, that's pretty exciting, because maybe like the work Katherine and I were showing earlier, everything is very structured and in the lab, but what happens if it's not structured? Do we see the same effects, and is that a good thing or a bad thing? So it makes me excited, and then it's one of those things that makes me very excited.
Giana, Katherine, you want to comment about that?
I think this is actually my third question, that what role does EEG play in this context? And I think mostly what we see right now is that it kind of looks at the brain level activity and serve as a validation of experimental interventions. And I think this is, I think it's a question that I have and I ask myself all the time, and it's just like, why do we use EEG, and what can we, is there a value to bringing it out of the lab? Because we see the reality with these experiments is there's a very long preparation time, but if we move to, let's say, fewer channels or the dry electrodes, do we still get similar observations that we see here? That's a question.
Mm-hmm. Giana, you want to weigh in on it?
I think, Katherine and Luke both had really good points. I think the development of EEG caps or apparatuses that you can use and take with you, definitely, I think it would have its place for sure. Again, my concern, similar to what Luke was saying, is maintaining the integrity of the quality that we're receiving there. But I think if, all of these, every little step, every little blip is always, moving forward still. And so its eventual development of a quality and reliable portable EEG is something that I would really look forward to, especially for that precision, that temporal precision.
Yeah, we've been playing a little bit with portable EEG, not that it's something that I particularly want to develop in the lab, but we played a little bit with it. And it's remarkable the kinds of things that can happen when you take it out into the real world. Electronic scooters, if they have the same Bluetooth frequency that your portable EEG device, can stop the data acquisition. Crazy things can happen out there in the wild. And so that's something that we have to think about dealing with. Now, I do have a question here, and it's for Luke, and it comes from Emmanuelle Tognoli. And she asks, and she's got a question relating to micrography, actually, and how it isolates one pathway at a time. And Westberg seemed to be working on that with a forthcoming MEG study, which should be interesting because MEG, of course, has got excellent spatial localization. Past that, we need a graded approach, dosing more or less of multiple pathways to pass out the different contribution of Meissner, Merkel, Pacini, Ruffini, and C fibers. So pulling out the different receptor types in the limb. So, Luke, what do you think of that?
Yeah, that's a really great point. And it especially if you're thinking of stimulation, right? Like using microneurography not just to record the individual fiber responses, but then potentially pump current in and stimulate. Yeah, it's absolutely a great point, because you can then start to think about, maybe you only want to produce the sensation of pressure, and so maybe we'll isolate a Meissner and a Merkel cell and try to stimulate specifically those afferents. But I think as we get better at that, and can incorporate all types of receptors in the skin to produce very targeted effects, that's maybe the goal for when we think about tactile sensation for prosthetic limbs. But with that comes, it's necessary to now develop stimulation models that are able to capture those different aspects, those different fiber properties, and that's some work that people have started to explore. So basically, how do you design your stimulation paradigm so that you target these specific properties, or that the stimulation behaves in such a way that you feel mainly something like a pressure or something else.
Or you can even take that one step further, and Emmanuel's idea even one step further, where if you do what you've suggested, Luke, and you've got your known profiles of stimulation for the different types of receptors, then you can start adding the different kinds of, so you might want to have, a couple of them. You might want to bring in Meissner's and Pacini, receptors, and you make these complex profiles of stimulation. I mean, there's a lot of things that can be done. I think it'd be incredibly exciting in the future.
Absolutely.
So I think we've run out of time, and I would like to thank all of these three speakers for an absolutely fabulous discussion, and also fabulous presentation, very intellectually stimulating. And I love the somatosensory system. I haven't worked in it for years, and it was a great, absolutely lovely ride that you took us all on today. So thank you so much, and everybody have a rest of good NeuroMatch, and we'll see you all later. Bye, everybody.
Thank you. Bye-bye.
Thank you. Bye.
Bye.
Talking. I need to ask what's going on. Okay, great. We will be starting in 1 minute. Okay, well, it looks like we will have to get started in any case. I'm still a little puzzled. I want to apologize. I have reasons to assume that we have a technical glitch on our side. Let's wait another minute or so. I apologize. It's the first time we're running into this specific problem. I'm not quite sure what's going on. Okay. In any case, let's already welcome the people that have joined us here so far, and it's possible that most people are joining us through YouTube. So after this delay, why don't we get started? We will also positively have the video so that everyone can join us afterwards. So it's a great pleasure for me to introduce Helen Beup, who is working on human brain organoids. And this is this technique that all my friends have been telling me about for a couple of years. And it's just really magical once one starts thinking about it, all those opportunities afforded by that. And so let me introduce the talk. So she will be talking about modeling the neurodevelopmental disorder tuberous sclerosis using human brain organoids. Helen, I'm very much looking forward to it.
Okay, great. Thank you so much. Can you hear me okay? All right.
Perfect.
Well, thank you. It's a pleasure to be here virtually at the NeuroMatch conference and to tell you a little bit about some of the things we've been working on in our lab, where we've used this relatively new or emerging technology of human brain organoids to try to understand the cellular and molecular changes underlying neurodevelopmental disorders. Okay, so first I'll just start with a brief introduction. So as neurobiologists, we're very interested in understanding this pathway that leads from genes to complex behaviors and brain functions. Okay, so as you all know, our specific pattern of gene expression in cells in our brain encode proteins and molecular pathways that determine neuronal type, neuronal structure and function, as well as the structure and function of glial cells. This complex array of neurons and glia need to be connected where they communicate via synapses. And all of these cells form neural networks, the activity of which ultimately underlies our brain functions and behaviors. Okay, so if we want to understand this path all the way from the very molecular genetic level up to complex brain function, one way we can think about this is trying to understand perhaps what goes wrong in disease states. Okay, and this is something that my lab has been particularly interested in, and we've focused primarily on neurodevelopmental disorders. And the good news is that we now have very good understanding of the genetics behind many nervous system disorders, including neurodevelopmental disorders. So we have a large number now of genes, mutations in which we know confer risk for different diseases. And of course, we know what happens to behavior or cognition or brain function when these genes are mutated. This is the disease state. But what we don't know, or which is harder to decipher, is what's going on in this box here, which is how do mutations in these particular genes alter neural development, neuronal structure, function, connectivity, plasticity, and activity to ultimately give rise to this end state, which is the disease. And this is a question that I've been very interested in, and that motivates a lot of what our lab does. As I mentioned, we've been primarily interested in neurodevelopmental disorders, and we've been interested in a particular signaling pathway which is known to be altered in actually several neurodevelopmental disorders, but also other diseases of the nervous system, including neurodegenerative disease. And that's this signaling pathway that I'm showing here, which has at its center this kinase complex called mTOR complex 1. Okay, and I'm showing a relatively simplified version of this signaling pathway. And what mTOR complex does is it phosphorylates a number of downstream targets, all of which control essentially cell growth or cell metabolism. And it controls these targets in a way that when mTORC1 is active, the cell becomes in an anabolic state where it's growing and dividing. And when mTORC1 signaling is turned off or suppressed, the cell goes into a catabolic state where these processes are suppressed. And so these downstream processes are things like protein synthesis, mitochondria biogenesis, lipid synthesis, and also the regulation of autophagy. And so this mTOR complex and its targets are present in every cell in the body. They are regulated by several upstream mechanisms. And the key one for today's talk is this TSC complex, which is made up of these two proteins, TSC1 and TSC2. And these two proteins form a complex that negatively regulates mTORC1 activity through this small GTPase Reb, such that in the absence or when TSC1 or 2 function is turned down, mTOR signaling is upregulated. Okay, and this complex integrates a number of intracellular and extracellular signals that control the level of mTOR activity. Okay, and as I said, this signaling pathway is present in every cell of the body, but we've been most interested in how it might contribute to neuronal development and neuronal function, because when this pathway becomes dysregulated, there are profound consequences for the nervous system. And one of the most well-studied disorders that's directly due to dysregulated mTOR signaling is this neurodevelopmental disorder called tuberous sclerosis complex, or TSC. And this is a relatively rare genetic disorder affecting about 1 in 6,000 people. The disorder affects multiple systems, so individuals present with benign tumors in multiple organs. But really the neurological and psychiatric problems are the most debilitating for patients and perhaps the least well understood. And so those neurological manifestations include the presence of these so-called cortical tubers, which you can see here, which are focal regions of malformed cortex that are observable by MRI. These cortical tubers are going to be the focus of my talk today. About 90% of patients have epilepsy, which can be a very severe form. It often has childhood onset and can be intractable. There's varying degrees of intellectual disability, and there's a high prevalence for autism spectrum disorder and other psychiatric and behavioral conditions. So a number of neuropsychiatric and cognitive impairments can occur when these TSC1 or TSC2 genes are mutated. And the consequence of mutating these genes or losing the function of these genes is to have constitutively upregulated or uncontrolled mTOR signaling. And so, as I said, what my lab has been very interested in understanding the functions of these TSC1 and TSC2 genes, as well as how mTOR signaling influences neuronal development, neuronal function, and synaptic connectivity. And we'd like to understand at the cellular level how this genetic insult leads to this constellation of neuropsychiatric problems. So for the purpose of today's talk, again, I'm going to focus on these cortical tubers, which are these focal regions in the cortex that are malformed, that arise during embryonic development. And I will say we have studied TSC and mutations in these TSC1 or TSC2 genes specifically. However, TSC is representative of a larger class of disorders, which are collectively called mTORopathies, which result from mutations in a number of genes that encode proteins that regulate the activity of mTOR complex 1. Okay, and so each of these proteins here in pink has a mutation that's associated with a neurodevelopmental disorder. And all of these mutations affect proteins, again, that impinge on mTOR signaling. And interestingly, they share a number of common features. So all are associated with these focal cortical malformations, or in the most extreme case, this can be hemimegalencephaly, which is essentially overgrowth of an entire hemisphere of the brain. They all have early onset epilepsy, some varying degree of intellectual disability, high risk of autism. And an interesting aspect of these disorders that I find particularly fascinating is that in many cases, the mutations in these genes can be somatic, meaning that they can arise spontaneously during brain developments, and they can therefore affect, just a small region of the cortex or the small region of the developing brain. And this is an interesting aspect of these diseases that we have tried to capture in our models. So by understanding something about the role of these TSC1 and TSC2 genes and how dysregulation of mTOR signaling leads to altered cortical development, we hope to gain insight into this broader class of neurodevelopmental disorders. Okay, so let me show you a little bit more about these cortical tubers. So again, there are these regions that essentially look like a potato. That's why they're called tubers on an MRI. And if we look closer, so if we resect one of these cortical tubers, so these cortical tubers will sometimes be surgically removed as a treatment for intractable epilepsy, as these tubers can often become the foci for seizures. So these seizures can be surgically removed, and we have a collaboration with Brenda Porter's group at Stanford University to look at some of these cortical tubers and have a look at the cellular level, what's going on. And so one thing you can appreciate is that within these cortical tubers, we actually have a diversity of different cell types. So we have so-called tuber neurons. We have things that appear to be astrocytes. And then we have these very unusual types of cells that are really only found in tubers and these related cortical dysplasias, which are these so-called giant or balloon cells. And in each of these cases, these cells appear very dysmorphic. These cells within tubers have very high mTOR signaling, and we can read out mTOR signaling here by looking at the phosphorylation of a ribosomal protein called S6. And so we can see these cells within tubers that have very high levels of phospho-S6 compared to the surrounding cells. They're very enlarged and dysmorphic. So this is a neuron that's staining for the cortical marker TBR1, and it looks very abnormal. And same thing with this astrocyte, we can see that it looks very large and has a number of processes. Some suggest that these could be reactive astrocytes. And again, we have these strange giant or balloon cells, which in some cases can have multiple nuclei. So maybe you can see here that this cell actually has 3 or 4 nuclei. And they're not obviously neurons or glia, and not much is understood about how these abnormal cells develop. Okay, and so because this is a pathology that arises during embryonic development, it's been challenging to study. One important thing to note is that mouse models or rodent models tend not to develop bona fide cortical tubers. in that we can see some dysmorphic cells when we have mutations in these genes in rodent models, but we don't generally robustly see these really abnormal giant or balloon cells. So we have a number of open questions about these tubers and how they arrive. Specifically, what is their developmental origin? From what cell do they develop from? What are the genetic requirements for their formation? And I'll explain more what I mean about this. And how does dysregulation of mTORC1 signaling lead to these really abnormal developments at the cellular level? And so, as I mentioned, we use rodent models in the lab, and they've been really helpful to understand many aspects of disease pathology. But there are fundamental differences between rodents and human brain development. Although many things are shared, there are some unique features. And perhaps that's very clearly shown in this, this schematic where we have a coronal section of a mouse brain. And you can see this relatively thin, small strip on top, which is the cortex. And of course, a coronal section from a human brain where you can see this remarkably elaborate cortical structure. And this is what defines humans evolutionarily, is this massive expansion of the cortex in particular. And so we thought perhaps if we want to understand this cortical developmental pathology, we might need to work with a human-specific cellular system. And so here's just a very basic kind of overview of some of the key steps in mammalian cortical development. So these steps are shared across all mammals. So at the very early stages, we have these neural progenitor cells that line the ventricles that divide symmetrically to produce this initial progenitor pool. These cells will eventually differentiate into what we call radioglia that have these fibers that span the thickness of the cortex. And these radioglia will produce different types of progenitor cells and will ultimately undergo asymmetric division where they will produce neurons. And these will be the cortical neurons that are going to form the cortical layers. And they do this in waves where we produce different cortical layers at a time. And after these progenitor cells, these radioglia are done producing neurons, they undergo a fate switch, which the details of which we don't fully understand, whereby they begin producing astrocytes. And so astrocytes are born after this period of neurogenesis. Okay, and again, this basic sequence of events is shared across all mammals. However, I just want to highlight one key difference here. So here is a schematic of a mouse developing cortex, where we have these radioglial cells here, and we have the newborn neurons that migrate up and form the cortical layers. And in humans, we have the same thing, although this is greatly expanded, except one unique feature is that we actually have the presence of additional types of progenitor cells, which are not found in rodents, which are enriched in humans. And these are the so-called outer radioglia. And they form this unique progenitor proliferative zone, which is thought to be one of the reasons why we have this greatly expanded cell number in the human cortex. And these outer radioglia are particularly interesting because in recent work from Arnold Kriegstein's lab at UCSF, it was shown that these outer radioglia cells have particularly high levels of mTORC1 signaling and may have differential expression of mTOR pathway regulators than other types of progenitor cells. So we felt that these cells could be particularly important into this developmental pathology involving dysregulated mTOR signaling. And so we wanted to develop a model system that would capture these cells and this kind of human-specific aspect of cortical development. And so this was work that was carried out by a very talented graduate student, John Blair, in the lab, who just graduated and is now a postdoc. And so what we did is we, as many of you know, we now have the capability to take either somatic cells, skin cells from people with different disorders, or embryonically derived human stem cells that we can perform gene editing on to introduce disease-relevant mutations. And we can generate these pluripotent stem cells, which can then, in theory, be differentiated in vitro into any cell type of interest. And we now have quite robust protocols for differentiating these stem cells into neural progenitors, to different types of neurons in these two-dimensional cultures, and more recently in the past 5 or 10 years into these 3-dimensional structures that we call brain organoids. And when we started out this project, we started out with 2-dimensional cultures of neurons, and we've moved almost exclusively now to these 3-dimensional cultures because they do have greater complexity in terms of the cell types that they contain. They also have the advantage that you can maintain them in culture for very long periods of time. So we've maintained these brain organoids for years, and they actually continue to develop over that time. And the interesting thing is that they continue to develop on essentially a human-specific timeline. So if we differentiate these brain organoids and culture them for 6 months, and we look at the transcriptional signatures or other properties of the cells in those organoids, they roughly resemble about a 6-month human fetus. And so they follow the timeline of human development quite nicely. And so what we did is we decided we wanted to develop a genetically controlled system whereby we could assess the consequences of these mutations in TSC1 or TSC2 in these human cells. And so we made an isogenic panel of human pluripotent stem cell lines with heterozygous or homozygous mutations in these TSC1 or TSC2 genes. And I should say that patients with TSC have the mutation either in TSC1 or in TSC2, and essentially the presentation is very overlapping. Here we had an opportunity to compare them side by side to see if we could see any differences in whether TSC1 or TSC2 was the gene that was mutated, and the short answer is that we didn't see major differences. The only thing we found was that the TSC2 mutations tend to be more severe. And so here you can see the consequences of disrupting TSC1 or TSC2 in this case, looking at this Western blot, and we can see robust activation of mTOR signaling, again, looking at the phosphorylation of S6 as our readout that our gene engineering worked. And so, as I said, we were interested in using this 3-dimensional brain organoid protocol that was developed by Sergio Pasca's lab about 5 years ago that is designed to model these early stages of human cortical development. And so here's kind of this recipe for this particular differentiation protocol. So these organoids go through a period of early neural induction that generates these early neural progenitor cells. We expand these progenitor cells by giving the organoids growth factors. And then after about a month, we induce the differentiation of neurons by adding different trophic factors. And then after this point, we let the organoids develop. And from this point on, they show essentially self-directed development where they continue to mature and differentiate according to that timeline that I showed you that represents human cortical development. And so here's an example of what one of these human brain organoids or cortical spheroids looks like early on. So this is around 1 month post-differentiation. And what you can see if you section one of these are these interesting ventricular-like zones, which are zones in which the progenitor cells are dividing and forming what resembles this ventricular zone. And these stain positive for markers of these progenitors. And in these organoids, you can see that we can get, many different numbers of these progenitor zones that are present early on. Okay, and so we then wanted to look at the consequences of these TSC mutations on this cortical development. And so we looked at this very early stage of cortical development, again, where we have these early neural progenitors that are dividing symmetrically, that are providing the progenitor pool that will give rise to the cortex. And here we stain for some canonical markers of these cells, PAX6 and SOX2. We also stained for this mitotic marker to look at the number of cells that were dividing, and none of this was strongly affected by these mutations in TSC1 or TSC2. And you can see these neural rosette, these clusters of progenitor cells look fairly normal across the different genotypes. So this very early stage of cortical development seemed to proceed normally in the case of these TSC mutations. However, when we let these organoids age, so now these organoids are about 5 months in culture, this is after the period of neurogenesis when the organoids start to undergo astrogenesis. Now we could see some pathology that started to resemble what we observed in the patient tubers. So here's a section that we've seen for MAP2 to mark neurons. and phosphorylated S6 in red, which marks cells that have high mTOR activity. And hopefully you can appreciate that these homozygous knockout TSC1 or TSC2 cells are looking abnormal. So they're greatly enlarged, they have kind of thick, abnormal looking processes, and they have very high levels of mTORC1 signaling. And interestingly, we saw that these heterozygous cells, which have obviously just one gene copy mutated, looked pretty normal and seemed to be developing similarly to the wild type cells. And so these observations are quantified here. So if we just quantify the amount of MAP2 protein, which is a general neuronal marker over time, we can see the emergence of neurons during neurogenesis in these organoids in this black line in the control. And we can see that these TSC1 or TSC2 knockout organoids are delayed and potentially even impaired in generating neurons or undergoing appropriate neuronal maturation. And if we look at another marker, NuN, which is another canonical general neuron marker, we can see that this is reduced. So this suggests that not only are the neurons that these mutant organoids making dysmorphic, they actually seem to be impaired in making the neurons in the first place. By contrast, if we look for markers of astrocytes like GFAP or S100B, we could see that these were strongly upregulated in the homozygous knockout cells compared to wild type. And so looking at this, it looks like we've kind of shifted the balance between neurogenesis and astrogenesis in these organoids when we have disrupted the TSC1 and TSC2 genes. And so how might this be? So to try to understand better what might be going on, we just examined mTOR signaling across this developmental window of brain organoid growth. And so here we're looking, we harvested brain organoids at different time points across developments and looked at mTOR pathway signaling. And so these are some canonical downstream mTOR targets that we can use to assess how active mTORC1 signaling is. And what you can probably notice is that here in these early days, so day 0 is the pluripotent stem cells, and days 10 and 20 are when we have these rapidly dividing early progenitors, we see very high mTOR signaling at this time point. However, between day 20 and 30, when we switched from expanding the progenitor pool to differentiating those progenitors into neurons, we see a really massive downregulation of many downstream targets of mTORC1 signaling. And again, this is happening normally in the control cells. So that we can quantify here, a really strong downregulation of this mTOR signaling as these spheroids transition from undergoing division to undergoing differentiation. And this kind of makes sense because I told you that the mTOR pathway is a key regulator of cellular anabolic processes. So rapidly dividing cells like stem cells or progenitor cells would require high mTOR signaling. But as we begin to differentiate and the cells become post-mitotic, it appears that those cells are suppressing mTOR signaling again because they're no longer rapidly dividing. And so what we see is in the organoids that have mutation in either TSC1 or TSC2, they fail to downregulate mTOR signaling, or they're unable to downregulate mTOR signaling during this transition into neurogenesis, such that mTOR signaling remains high throughout organoid development. And we think that this high mTOR signaling might be impairing the normal differentiation and developmental processes. And I mentioned in the slide before that one phenotype we saw is what appeared to be an overabundance of astrocytes or glial lineage cells and an impairment in the ability to actually make neurons properly. And what we looked at is a canonical signaling pathway that's been shown, at least in rodent studies, in other animal models, to be a key regulator of gliogenesis, and that's STAT3. So normally when cells in the cortex transition, progenitors transition from neurogenesis to gliogenesis, we know that STAT3 activity is turned on to promote gliogenesis. And here what we found is that in these TSC knockout organoids, STAT3 signaling was higher than controls, and it was higher at these earlier time points when the organoids should be undergoing neurogenesis and shouldn't be doing gliogenesis. And so we came up with the idea that maybe this activation of STAT3 signaling due to dysregulated mTOR activity is driving premature or precocious gliogenesis in this model. And if I have time, I'll show you some recent evidence that we think that's the case. But let me go back to this idea that I introduced in the beginning, that some of these mTORopathies are actually not due to germline mutations, but rather are due to somatic mutations. And a hypothesis in the TSC field for why we get these focal cortical malformations, why these tubers are kind of discrete regions of the cortex, is that maybe what happens is during development, the progenitor cells acquire this so-called second hit somatic mutation. And I should say, before I go into that TSC patients have a germline heterozygous mutation. And I showed you just now that the organoids with a heterozygous mutation seem to develop fairly normally. But it was the full knockout organoids that had problems. And so how do we reconcile that? Well, the idea is that the majority of the cells, or all of the cells, are heterozygous for TSC1 or TSC2 mutation, but that some progenitor cells acquire this somatic mutation during development. And this somatic mutation doesn't have a strong effect on progenitor cell division or expansion, probably because high mTOR signaling is actually beneficial for rapidly dividing cells. However, when those cells that have this second hit mutation need to differentiate and form neurons and form cortical layers, they are impaired in doing so. And so that generates this focal region of a cortical tuber that is derived from this lineage of cells that had this somatic mutation. And so this is the hypothesis that's been out there in the field, but again, it's been challenging to model this because this is something that would be happening during embryonic brain development. And so we wanted to do this with our organoid system. I won't go into the genetics of how we did this, but using CRISPR-Cas9, we developed a cell line that was heterozygous for TSC2. So one allele of TSC2 had a constitutive loss of function mutation. And then we engineered the second allele to have a Cre-dependent conditional mutation. So this cell line is essentially heterozygous until we add Cre. And in that case, Cre will delete the functional copy, mimicking this second hit and creating a complete TSC2 knockout cell. Okay, and we can see when we add Cre, we get complete loss of this TSC2 protein and very strong activation of mTOR signaling. And what we did is to model this somatic mutation happening early in development, we wanted to add Cre recombinase to the organoids early in development during this neural progenitor expansion phase, but we wanted a way to visualize the cells that got this second hit mutation and be able to follow them and their progeny over time. So we did another genetic engineering step where we introduced this Cre-dependent TD tomato reporter into a safe harbor locus. So now what we have is we have these early organoids composed of these neural progenitor cells. We add a subsaturating amount of Cre to mimic a second hit that would just happen in a few small population of the progenitor cells. The cells will turn red due to this TD tomato fluorescence, and then we can watch their development over time. And so here is what one of those organoids looks like, where we've done this second hit mutation. And so in blue is labeled glial lineage cells, in green are labeled neurons, and in red are these second hit cells that have this full TSC2 mutation. And what you can see is these regions that we think actually resemble cortical tubers in one of these developing organoids. And if we zoom in, you can see these really enlarged, kind of strange looking dysmorphic cells that look quite similar to what we see in our patient tissue. And here's just some other views of these really kind of abnormal looking cells. And here I'm showing that they also tend to express these glial markers like vimentin, and they tend not to generate very many neurons, consistent with what I showed you before. And if we do the exact same thing in a cell line where we are generating a single hit with Cre, so these cells are all wild type, and then the cells that are that express Cre will knock out one copy of TSC2 to generate heterozygous cells. Again, these cells look pretty normal. They don't look anything like these tuber cells, which suggests to us that we really need this kind of second hit event to get complete loss of the gene to induce the formation of cortical tubers. Okay, And so just quickly show you a comparison of, here's another one of our cortical organoids in comparison to a sample of a fetal cortex that's mid-gestation, roughly the same developmental period as our cortical organoid. And you can see this developing cortical tuber, these balloon cells that have high phospho-6, and in our organoids, these cells look quite similar. And you can see some more examples of these abnormal looking tuber cells here. And so what we found is that in this genetically mosaic human brain organoid system, we found a cell autonomous change in the differentiation capacity of these cells that had the second hit. So now what we have in these cortical organoids are the majority of the cells which are heterozygous for TSC2. Again, we think these develop mostly normally. And then we have a small population of cells that are labeled with TD tomato that are complete TSC2 knockouts. And you can see they're highly abnormal looking. And overwhelmingly, they stain for glial lineage markers and not neuronal markers, such that we are generating a much larger number of glial cells and astrocytes compared to neurons with this manipulation compared to the neighboring heterozygous cells. And lastly, what I want to show you is we know that this phenotype, this tuber cells likely arise due to this aberrant mTORC1 signaling happening during development. And there are drugs available that will potently suppress mTORC1 signaling. And one such drug is called rapamycin. So we applied rapamycin to these organoids throughout development to block mTORC1 signaling to see if we could rescue the development of these tuber cells. And indeed we could. So here are these abnormal looking tuber cells that were treated with vehicle. And here are those exact same TSC2 knockout cells, again labeled with TD tomato, in the presence of rapamycin. You can see that we get much more normal morphology, and we get much more differentiation down neuronal lineages here. So many more of these TSC knockout cells now stain for neuronal markers instead of glial markers. Okay, so let me just summarize what I've shown you here. So we've used these human brain organoids to model these early stages of human cortical development, from the stage of neural progenitor cell expansion through neurogenesis, through neuronal maturation, and eventually the generation of astrocytes. And in normally developing organoids, we see that mTOR signaling is typically very high in stem cells and these neural progenitors because they have high metabolic and anabolic demands. However, there's some mechanism that we don't know what that is yet that suppresses mTORC1 signaling. And this seems to be important to allow neurogenesis, neuronal differentiation to happen normally. And then at later stages of development, we can see mTOR signaling actually start to come back up a little bit together with the birth of astrocytes. And when we have mutations in these TSC1 or TSC2 genes, we can no longer dynamically regulate mTOR signaling properly. And we think that this leads to the precocious birth of astrocytes, potentially the maintenance of some of these radial glial stem cells, and an impairment in ultimately producing neurons. And so this altered development gives rise to these abnormal cortical tuber cells, which are, again, overwhelmingly expressing markers of glial lineage. And I think I will probably stop there in the interest of time. I'll just quickly highlight kind of what we're doing now. So of course, we have a number of open questions that we'd like to address with our model about the mechanisms by which this dysregulated mTOR signaling affects neuronal differentiation and how it might be altering the lineage generation of these tuber cells. And so what we have done now is a relatively large scale single cell RNA sequencing experiment whereby we can better assess all of the different cell types that are in these organoids, how the TSC mutation affects their development and affects their transcriptional programs across development. And just one quick bit of data here. So here is a plot showing the results of our single cell RNA sequencing experiment. You can see all of the different cell types that are generated by these cortical neurons, by these cortical organoids, and we can look for some canonical markers to identify the cell types. And I'll just leave you with this last bit of data where now I'm showing color-coded the control TSC2 heterozygous cells in gray and the red TSC2 knockout cells. And what you can see is that they're not evenly distributed throughout these different clusters, which are representing different cell types. And as I showed before with the marker staining, we are overwhelmingly generating these glial lineage cells when we have this mutation in TSC2, and we think that these glial lineage cells are actually becoming these giant or balloon cells that we see in the tubers. And so this is still very much a work in progress. I'll just skip this last part here. And so what I've told you about today is that neuronal differentiation during cortical genesis requires, we think, very precise coordination of transcriptional and translational programs, right? As well as precise changes in cellular metabolic status. And because mTORC1 signaling is a really key regulator of many of these things, an inability to properly regulate or dynamically control mTOR signaling likely interferes with this coordination. Interestingly, we see that this leads to a promotion of astrogenesis at the expense of neurogenesis, and we think these giant balloon cells that are in patient tubers might be abnormal glial cells. And what I didn't get to show you in that last slide is that we think these astrocytes that are generated are not just normal astrocytes, but maybe these reactive astrocytes, which could be contributing to the pathology within cortical tubers. And so in the future, we're interested in understanding more about the functional consequences of these mutations on neuron and astrocyte function, and doing more comparison between these brain organoid models and these primary samples that we get from patients. So thank you very much. I'll end there, and maybe there's time for a question or two.
Great, thanks so much. Let me first clap for everyone else who you can't hear. We have a few questions. Anatoly asks, what stops further development of the organoids beyond the 6-month stage?
Oh, that's a good question. So I should have, yeah, they don't stop developing at 6 months necessarily. So you can culture these for very long periods of time. There was a study in Sergio Pasca's lab where they cultured published 3-year-old organoids. And very cool thing in that study, they showed that, so the neurogenesis is complete by a few months into the development, and then the astrocytes begin to be born, and then even later on you can see the development of other types of non-neuronal cells. And what Sergio Pasca's lab shown is that sometime around 9 months in culture, the astrocytes that are generated actually shift their transcriptional signature from a fetal state to more of a postnatal state, which is quite remarkable. So they will continue to mature and progress along their developmental trajectory for very long periods of time. And the longer you let them mature, the more kind of mature cellular states you can achieve.
Great. Next question is, do the cells in the organoids form functional connectivity? And if so, how does it drop off with distance?
Great question. So sorry, what was the second part? I didn't catch the second.
So functional connectivity usually drops off with distance, where you have lots of local connections and then a few more long distance connections. So I think it's just a question about like, how brain-like are they?
Yeah, that's a great question. That's a very good question. So they definitely do form connections. One thing that I think it's important to keep in mind is that these brain organoids really represent fetal development. And so their activity and their connectivity is quite immature and as appropriate for what you might see during normal human fetal development. So they don't represent fully complete, fully functional, highly complex neural circuits that you would see in a fully developed brain, but they definitely do, the cells definitely do connect with each other. We have started to look at this, and other labs have reported that you can see spontaneous neuronal activity in these organoids. It takes a little while to emerge. So the longer you culture them for, the more mature the cells are, the more competent they are to form circuits. But definitely they can form circuits. Obviously, we don't have every cell type of the cortex, present in the correct stoichiometry, present in the correct anatomy. It's really a ball of cells. That's another key point. So, but just like you would, make a neuronal culture where the cells spontaneously form connections, the same thing is happening here. And then in terms of the distance, the organoids are several millimeters big. So they're fairly large, but I think that the the connections could in theory span that distance. So I think you can have fairly long range connectivity, but again, it wouldn't be in a necessarily orchestrated or directed way. It would be just a spontaneous occurrence.
Very, very interesting. I have a question. Like, I come from the neural networks kind of corner of the world, and in a way, when I see the networks of MTOG1 and how it connects with all the others, it very much seems like a network inference problem for me. So at some level, the graphs as you draw them are binary graphs. Now it says this one affects this one. But if we want to understand it like as a dynamical system, we want to understand how it's regulated. And if you want all these errors between them, ultimately they have reaction kinetics or something on them. Do you see a transition happening in that direction?
That's a great point. I mean, I think the field of systems biology tries to address that question, to look at these signaling pathways in more kind of dynamic ways. As biochemists studying signal transduction, we grind up a tissue and do a Western blot and look at a band, right? And that way we can get these, at least that allows us to put arrows on our signaling diagram so we can at least make directionality within those networks, right? That this one controls this one and controls this one. But of course, you're right, it is much more complex. And I haven't really shown in that diagram all of the feedback that happens. And of course, when you change one node of the system, you will have reverberating effects through different feedback mechanisms on different timescales that are resulting in very complex set of changes. So yeah, those I haven't really touched upon here, but definitely that's an important thing to keep in mind. And part of my lab is interested in restoring signaling balance in the face of these perturbations. And classically, the drugs we use, like rapamycin, for example, just completely shuts off mTORC1 signaling. And that leads to also a cascade of downstream effects that, it doesn't restore the system to balance, let's put it that way. So we are trying to think, how can we kind of tweak, the expression or the signaling of some of these key nodes in a way that rebalances the signaling and rebalances the system, rather than just kind of pushing it one way or another, which will have other, consequences. So yes, you're right that the signaling is much more complex and dynamic than I've represented it here. Good point.
Great, awesome. Well, thanks so much. Let's clap again and thank the speaker. Thank you. And thanks so much for the beautiful talk and discussion. And thanks everyone for tuning in.
Live. Hi everyone, welcome to the third day of NeuroMatch 3.0. My name is Medina Sarvastani. I'm going to be your on-screen host, and we have Kevin Roosh in the background running the tech side of things. And before we get started, I just wanted to introduce sort of the idea of this session, since it's new to most people. This is an interactive session, so it's essentially meant to be the virtual version of a poster session at a real conference. So it should be more casual, less structured, with hopefully a lot of interaction between the panelists and the audience members. So feel super free to use the chat to post your questions in the Q&A. If there are several questions, upvote the ones you like, because we're going to go through from top to bottom. And just generally, it's less restrictive than a traditional talk where you can't interrupt the speaker. So we have 3 speakers. Each will take a total of 15 minutes for their overview, discussion, and Q&A. And what else? Yeah, I think that's about it. And we have a third speaker that should, oh, okay, he's here, great. So we have everyone on board, so we can get started. Cool, we have 3 very interesting talks today on various approaches to detailed neuronal modeling. And we can go right to our first talk, which is going to be jointly presented by Nathaniel Opsal and Pete Canfield, who are both undergrad research assistants in the Neural Engineering Laboratory at the University of Missouri. And they're going to tell us about segregation of current modules in modeling detailed single neuron models. All right, guys, take it away.
Can you all see that area?
Yep, that looks good.
Cool. Yep, so this is segregation of current modules in modeling detailed single neuron models. So the motivation behind this is we're working on a project, we're modeling the CA3 region and trying to get theta power in that region. And with that, we needed a biorealistic CA3 pyramidal cell. One thing that those cells show pretty ubiquitously is they show current pulses that have triplets, so like high current pulses. And during current injections, they have an initial burst and then they slow down to tonic spiking. So to match that, we use the segregation method to create an initial bursting module, and then we expanded from there and made a tonic bursting module. And then we took that tuned cell and we put it back into the network to see how it affects the theta. And in the future, we plan on taking this approach and automating it using machine learning. So just as an overview, the segregation idea is basically you take channel activation curves, and then at the low end values, you basically slice them off to help get rid of some things that we don't like to see in modeling, like endogenous spiking and things like that. So the initial approach began with a passive module, which is H currents, as you can see on the right here, and then a spiking module, which is the NAT and KDR currents. We're expanding that into also having an initial bursting module and a tonic bursting module. So first, the initial bursting module. We got this with an NAP and a KM channel. As you can see on the right, these two plots here at the top is with the channels both segregated. So we see an initial burst on the right side, and then it slows down to a tonic spiking. And we also see with the current pulse, we get that triplet we were looking for. But then if you leave KM unsegregated, for instance, you see on the bottom left there, you only get a doublet in that pulse as opposed to the triplet. And if NAP is left unsegregated, we get endogenous spiking, which is not what we want to see. So segregation really helps us in those two ways for this module. And then the second module is the tonic spiking module, which we got with CAS, CAT, and KCA channels. The top plot here shows with these channels segregated, and it shows, basically a tonic bursting, all pretty even. But then you'll see at the bottom there, if we unsegregate the KCA channel, for instance, we see bursting that is not very constant. It starts out with a long burst and then a short burst and then a long burst. It's not really what we're looking for when you think of a bursting module.
Right, so if you remember back to our motivations, one of the things that we were planning on doing is trying to show that this doublet style spiking is important for generating theta power in a model CA3 hippocampal network. So we replaced the prior Ezekvich model, which was developed by Uri Maoz, with our developed cell to investigate the effects of doublet style spiking on theta oscillations. Inserting the biologically realistic CA3 cell into the network preserved the theta oscillations recorded in the LFP of the hippocampus network. So as you can see here, there are two figures. The figure on the left is Ali's results, and you can see that there's a theta power is spiking at around 0.14, and in our model on the right, we get a very similar shaped plot, and these plots are power spectral density plots, by the way, at about a peak of 0.12. So it's very similar results here. We are currently in the process of investigating the relative importance of bursting versus tonic spiking on theta oscillations. So what are the mechanisms which lead to theta generation in the hippocampus network? Theta generation occurs due to the interactions between CA3 pyramidal cells and Oriens lacunosum moleculaire, otherwise known as OLM cells. CA3 pyramidal cells receive input from the entorhinal cortex in the dentate gyrus in our model, causing significant levels of doublet style spiking. So this figure here over on the right shows the number of occurrences of high frequency bursts in the CA3 cell during the duration of a 15 Hertz Poisson input experiment in Ali's original model. So from this plot, we can definitely see that high frequency bursts do occur in that model. OLM interneurons inhibit CA3 cells, causing theta oscillations. We hypothesized that the bursting dynamics in the CA3 cells is critical for generating theta, and that tonic spiking is insufficient. Jupyter, to kind of extend this to be more accessible to, and also to allow for the rapid development and tuning of these models, we developed a Jupyter notebook of this cell. We developed an intuitive interactive Jupyter notebook model, which demonstrates the process of using segregated current modules, the segregated current modules method, to develop biologically realistic bursting cells. Jupyter notebooks can also be directly fed as simulators to the SBI machine learning algorithm for automatic tuning of conductance values. All of this will be made publicly available at scineuro.org. In an accompanying interactive talk that I think you guys will hear later, we explain a new algorithm in machine learning which effectively infers or efficiently infers biophysical parameters. Our plan is to automate the segregation scheme proposed here using that inference scheme. Our overall goal is to enable automated design of biophysical cell models with multiple features to more closely mimic in vitro and in vivo characteristics. Thanks for listening, and we're happy to answer any questions that anyone might have at this point.
Okay, awesome. Yeah, if the other panelists are let's see. Okay, great. Yeah, feel free to unmute yourselves and sort of engage in a discussion. But I have a couple questions for both of you guys. Can you tell me a little bit more about the segregation method? So you end up with a reduced model, but how does it compare to just like a point source integrate and fire model? Can you discuss it in terms of multiple compartments or not? I'd just love to hear a little more about the general approach.
So basically, the idea, as I understand it, is that this comes from like not a paper that me and Pete were a part of. So it comes from the Alturki et al. 2016 paper you can see there. So that'll probably explain it in a better way than I could. But basically the idea, as I understand it, is that you get, in nature, we plot these curves with, our activation curves, V-halves and everything. And if you maintain those V-halves, but then at very low values, just basically steepen the curve so that it cuts off earlier, you don't see like large changes, but you like in what the cell's modeling, but you do see like a cleanup of some of the things like we said, like endogenous spiking and things like that, and it just generally makes it easier, gives you more tools to model. So I don't know if that answers your question particularly.
I think it does. So I assume that it's computationally more efficient and you have less parameters. Is that fair to say?
I think so, yeah.
But you still, okay, yeah.
It definitely reduces the parameter space. I would say it's different from an integrate and fire model in terms of, these are single compartment typically what we're doing with this project. So for one thing, you have the space, you have the integration of dendrites, and you can have synapses on an exon if you want to, things like that, which an integrate and fire model wouldn't be able to do. Now, when you expand it into multiple compartments, things get a little more complicated. And that's, I think, some future work for us on this project.
Okay, so the overall idea is a reduced model, reducing single compartment model that can still exhibit pretty complex spiking behavior. It still maintains a resting potential. I see, that's cool.
Yep, you got it.
Okay, and then the second question, I don't know if I missed this, and I'm not an expert in theta bursts or hippocampal circuitry, but can you tell me more about why the double spikes, the double initial spikes are necessary or contribute to theta bursting?
Yes, so the idea there, you can go ahead, Pete.
No, go ahead.
Okay, so basically the idea there is that the theta happens as an interaction between the OLM inhibitory cells and the CA3 pyramidal cells. So if the CA3 pyramidal cells spike 3 times, then that'll be a stronger connection to the OLM, which will then inhibit it harder, which will then ideally cause blocks that will allow us to have theta, basically. So like it'll be stronger blocks where like there's definitely no spiking here, and then we'll see the theta in the other areas. But I mean, if you want to add to that, you can go ahead.
Yeah, I think the only thing that I would add is that oftentimes like the input being provided into these cells is some sort of like synaptic summation. And this means that the overall current injection that's actually happening in this cell is relatively strong and short. And this is where that burst comes into play, most prominently.
Okay, cool. I see, and Satish Nair is saying in the chat that, yeah, this approach is also applicable to multiple compartments. Yeah, I'd be curious to see a head-to-head. I mean, there's an infinite set of ways, depending on your needs, that you could build single neuron models, but it would be interesting to see a head-to-head comparison of sort of computational cost. Okay, great. That's all the questions I have. Unless the panelists or attendees have more questions, we're good on time here and we can move on to our next speaker. Yeah, okay, great. Okay, thank you guys. Our next speaker is Daniel, right? That's the right order?
Yep.
Okay, great. Daniel Dopp, also from University of Missouri. Actually, all of our speakers are from the same lab, if you guys haven't noticed. He's going to tell us about automated estimation of morphology of a neurocortical neuron using in vivo LFB data. And Nathaniel and Pete, you guys set Dan's talk up really nicely. I'm really curious to hear how your two approaches integrate.
Okay. So the general problem that we're looking to solve is that given an observation of like an extracellular voltage recording in vivo, how do we get a model that can produce an output similar to that? In our case, we're dealing with, so the idea that this came from was that there's been recent advances in cell recording technology, or technology to record local field potentials. And we had some recordings from, we were given recordings from the mouse motor cortex. And our goal was to build a model that can match that. And normally we would end up, a more brute force method would be like making a bunch of different samples from a parameter space and then generating models and coming up with sort of rejection criteria and selecting through this to end up with a good model. But there's this tool that the Mackey lab has put out that is called simulation-based inference, and they combine a machine learning algorithm, the sequential neural posterior estimation, with Bayesian inference to help with problems like this, where you're trying to find a parameter set to get that model. So the model we used for this was a stylized cell. It just had the soma with two basal dendrites, apical dendrites, trunk and tufts. And we're looking to adjust the length and radius of each of those. So far, we've only handcrafted those. We haven't put that through the SBI. Okay, yeah, this is the sort of the latest electrode array they're using for these recordings. It has 4 parameters that we're using to find the location. The idea is to get the location of the cell with respect to the probe. and then also to be able to tell something about its morphology. So the probe here has then 4 parameters, just the x, y axis, h and phi for the cell's location orientation. It's a 4x96 2D array, and each of these cells are recording sites or channels. Our simulated probe uses an average over every 4 electrodes for this and turned into a 1D array. So our in vivo data that was given to us is we took that and averaged the waveform over all the spikes, or we averaged their averages. Our recording here on the left shows what we end up with. And this is a heat map. For our model, there's a current pulse that's injected into the soma to give us an extra potential instead of a synapse, although we'll move on to that later. So the general method of this algorithm is to use it uses that Bayesian inference in the machine learning algorithm SNP. For inference, our hypothesis is that stylized model with those 5 parameters, including cell's location orientation. And again, our goal is just to estimate what those parameters are that will give us that, and that's shown in the posterior given by inference. The general flow is that it draws samples from the prior, puts them into the model or simulator, and then we have an output, which in our case is actually a set of statistics that summarize the LFP. It's not the actual LFP. And then that's trained on a network, and then inference is used on that's trained on a network to create a posterior distribution, and then inference is used to sample from that distribution, select the parameters that are most likely to give us or show us what parameters are most likely to give us the same output as the in vivo data. The summary statistics we use for doing this are we just take an average of the voltage across those 96 channels. We take the average for each channel, the maximum and minimum voltage, and the time difference between the minimum and maximum. And for each of those, we take the mean, standard deviation, minimum, maximum for each measurement over all the channels. And this is what's fed into the neural network for training. So to start off with, making sure it can handle as many parameters as we're giving it in our simulation. We start with just some random ground truth parameters. It generates an LFP like this. And then using SBI automatically just runs through the SNPE and inference to generate this posterior distribution that redlines the ground truth parameters, which produces this plot, which is a pretty good fit. Then we trained it on the in vivo data, and that struggled to do that with all the parameters. We're working up to that, but we were able to find within the posterior a set of parameters that gives us this, which is a little closer. And these are just heat maps to compare. Since we're also interested in later inferring the morphological parameters, for now we just handcrafted or changed the stylized model to give us show us how each morphological parameter would change. And this is the trunk length, if you remember the stylized cell, reducing it by half and then doubling it. And this will be what our default morphology is. Reducing it seems to get us a little closer to what the in vivo data looks like. And then we also changed soma radius for that. The amount I changed it by was based on if it still gave a action potential. If it didn't, I couldn't go over much past this. Also changed trunk radius. And it's not clear how that's going to help us. It does look like the trunk length is probably what we're going to infer first. So yeah, our future work is switching to synaptic input rather than current injection, and then inferring some of the morphological biophysical parameters. And then after that, we'll go to synaptic parameters like strength and delay. And we'll also be using a convolutional neural network rather than our summary statistics, or to give us our summary statistics for training.
All right, cool. So let me make sure I got this straight. So you have, first of all, when you say LFP, you mean the extracellular signal that's picking up action potentials from nearby neurons. So these are single unit or multi-unit extracellular recordings.
Yes, like the transmembrane currents at a distance are picked up by the electrode.
Okay, perfect. So what we usually mean is this. Okay, so the big idea here is that you can use multiple electrodes on a laminar probe to infer both the position of multiple cells at a time, their orientation, and you can do that fairly reasonably well right now. Eventually, you'll add to that morphological parameters like trunk length and other factors. And eventually, you'll add biophysical parameters. So from the extracellular potential alone, you'll infer essentially all of the structural and biophysical properties that should allow you to sort of close the loop and simulate the action potential of the cell you're recording from. Is that the idea?
Yeah, that's the long-term goal.
Okay, that's pretty cool. So how does that, so A, does this scale? So can you do this for multiple, so these laminar probes, you know, the idea is that you can record from, I don't know, 300 neurons at the same time with the NeuroPixels probe, for instance. So does the scale from a couple neurons inference to many?
Yeah, I'm not sure. So far, I think all we have is from a single.
Okay, that's pretty
That's all we've
cool.
been doing.
And then can you tell me a little more about how this would integrate with the previous talk, with the segregated current modules? Is that part of how you would infer the biophysical parameters?
So if I recall, they're using a different technique for matching a model to in vivo data. Is that?
Yeah, and this is a question for Nathan or Nathaniel and Pete too.
Yeah, so if you'll start with just a voltage trace, then this can definitely take that, and then whatever model you feed it, it will train the network on that, and then infer from the posterior develops to try to give you a match to the observed data.
Okay, cool. And generally, I'm not sure why it's important to infer the position of neurons.
Oh,
Why
right.
do we want to do that?
Like with respect to the electrode.
Yeah. I mean, I imagine for spike sorting, actually, that would be a really useful parameter to be able to infer. And if you have multiple electrodes, you can sort of triangulate the different voltage traces to pull out distance. But aside from sort of spike sorting needs, is there an application there that I'm missing? Why does it matter where the neuron sits in the brain relative to the probe?
I'm not sure.
Well, for spike sorting, it would be pretty useful. So Satish Nair, and yeah, unfortunately, so I'm happy to unmute or bring anyone from the audience up on stage, but unfortunately we have to sort of do that one by one. But Satish Nair is saying that this is a general method for any number of neurons. Okay, so the plan is to categorize the entire set of recorded neurons of all types. I see. Position and layer is important for studying gamma oscillations. Oh, I see. Yeah, absolutely. So for gamma and beta oscillations that are exhibited or that are picked up in different lamina, then it really matters what the position of neurons is. Okay, great. So unless the panelists have questions, and I see that Dao Chen has their hand up. I've allowed you to talk if you'd like to. Yeah, go ahead.
Yeah, I'm one of the authors of this presentation.
Okay, great.
So I just want to add something. So I think this in vivo data come from our collaborator. I think he already had the spike sorting after getting the multi-electrode data. So I think it's after the spike sorting and select this single cell that nearby the electrode, and potentially it can pick up several multiple cells nearby this one electrode probe.
I see.
Yeah,
That's very
after
cool.
spike sorting, and we average the waveforms only for this particular cell.
I see. Okay. Yeah, I was actually wondering how the averages seem to be so tight. Okay, I see. Okay, great. If there are no more questions, we are right about 9:30, so we can move on to our last speaker. Okay, great. Our last speaker is Ben Latimer, also from the same group. Ben is a PhD student in electrical and computer engineering at the University of Missouri. He's an NSF graduate research fellow. And we also have the co-first author of this work, Aidan Aberbach, in the audience with us. And he's a high school senior and research assistant with the Neural Engineering Lab. Ben, the floor is yours.
All right, can everybody hear me?
Yep, sounds good.
All right, so do I need to put this in presentation mode or is it showing?
It's showing, but you should put it in presentation. Okay. Yeah, great.
Like this? Yep. All right, so this project's probably a lot more straightforward than the last two, require a lot more explanation. I think this one is pretty simple. Basically, what we're doing is we have a detailed pyramidal track cell from layer 5 in Cortex, but that part doesn't much matter. It actually could be done to any cell, but the point is we're making a detailed cell, so we faithfully reproduce all the dendritic morphology exactly as it is in the brain. So that's kind of a new thing for us, coming from single compartment or 5-6 compartments. It's a whole new thing. And basically we want to try to model in vivo function, just like the other talks. And so these particular neurons, they're kind of considered the main output nodes of cortical computation. So stuff happens in cortex, it goes out through these pyramidal tract neurons. So it's really important to know how do these cells integrate and convert their presynaptic spikes to output spikes. So that's what we study here is, what role does inhibition, this balance of inhibition and excitation, and rhythmic inhibition, what roles do those play? And particularly what we look at is input resistance is an important characteristic of the cell. So what you see is that in vitro, input resistance is much higher. So if you're not familiar, input resistance is like, if you inject some current, if you have a big input resistance, you get a big change in voltage. If you have a small input resistance, it's a small change in voltage. So you can imagine, big input resistance means the same synapse might be converted to a spike, whereas small input resistance means that same synapse doesn't go through. So it's a very important characteristic of neural computation. And what you find is that in vitro, the input resistance is much higher than in vivo. In vivo is about maybe like 50% or less of in vitro, which is, very curious. People have been wondering a long time, why is this? Is it because of the synaptic bombardment going on? There's so many synapses, tens of thousands on a neuron. So is that why it's lower? Is it because of, the biophysical conductances in the neuron? And so we kind of endeavored to answer those questions. And so we set up this detailed cell and we bombarded it with spikes in different conditions. So incoherent spike trains and rhythmic spike trains, basically. So this is our model. The one on the right is the detailed morphology. So you can see in the bright sort of red, we have the basal dendrites. Oops. And then the maroon are the apical dendrites. And then the soma is down below near the red dendrites. And we matched micro EPSPs. So these are membrane potentials that are independent of spikes. So they happen because of random neurotransmitter release. So on the left, you'll see a typical in vitro trace. So this is where you inject current and you see if the cell spikes. We injected negative current and then positive current. And you see if you compare it to the one on the right, the same current is this trace in blue on the left. That's the same current being applied to the in vivo cell on the right. So you can see that input resistance drop by like a third or more than half. It's about 30%. So actually I put the numbers here. Yeah, so in vitro we had 50 mega ohms, in vivo is 13. So it's actually like a quarter of what it was in vitro, which is totally what you see. Intracellular recordings, of course, are notoriously difficult to do in vivo, but when they are done, you see this very small input resistance. The tau also changes a lot. This is because the capacitance of the cell is already charged up. And so it doesn't take as much time to reach full charge. And so what we found was we had two types of synapses, right? Excitatory and inhibitory. The first row here is the high excitation state. And so if we have high excitation and high inhibition, we get this input resistance around 10 mega ohms. If we subsequently lower the inhibition, so we're decreasing those synapses, those GABAergic synapses, the input resistance goes back to closer to what it was in vitro. So it turns out the inhibitory synapses are really contributing to that decrease in input resistance. Because you can see even when we lower excitation and keep inhibition high, it doesn't change much. I think I cut the synapses by like a 1/10 here. And you can see, if you can see the light gray traces, there's tons of spiking going on because the excitation was so high. Here I turned it down and you get almost no change in input resistance. It goes from 10.6 to 11.8. Whereas if you cut your inhibitory synaptic weights, the input resistance goes up a lot. And so this is a important effect. We need to try to understand why the inhibitory synapses have this effect of decreasing the input resistance so much, because inhibition hits on the soma. So it's very, it's a big influencer of the sort of input-output relationship of the cell. This just shows the spike trains. So you can see excitatory spike trains are kind of low frequency. There's fewer of there's more of them, but they're lower frequency. So in this particular simulation, we had 10,000 excitatory spike trains and 1,000 inhibitory. But because the inhibitory are much higher firing rate, they look much denser in this picture. So I just wanted to show that. This is kind of a future direction we're working on. We're doing linear regression, basically just relating the cell's parameters. So like average excitatory firing rate, average excitatory weights, the standard deviation of the weights, et cetera, relating that to the firing rate of the cell. So, if we find a good correlation there, we can examine the parameters of the linear regression. And we literally just did this today, so we still need to flesh this out a bit, but you can see the standard deviation of excitatory synapses is, these are the model odds, by the way. A number greater than 1 means the coefficient is positive, a number less than 1 means it's negative. So a lot of these are hovering right about 1. That means they're about a 0 coefficient. But the mean excitatory firing rate is positively influences the firing rate of the cell. And then this is gamma rhythmic inhibition. So same inhibition as before. The only thing we change is the way the spike times are lined up. So instead of being incoherent, now they're aligned to the gamma phase, which this gamma happens to be 60 hertz. And there's some noise, there. If the top is zoomed way out, but then if we zoom in, the bottom one, you can see how these spikes line up in time, right at about 60 hertz. And so these guys are going to hit the soma of the cell at 60 hertz. And the theory being that when that inhibition wanes, that allows an opportune time for excitatory synaptic inputs to go through. And so this is kind of the tail end of it. Basically, we're applying the gamma compared to the incoherent inhibition and seeing, why does the cell decide to spike at certain times during gamma compared to other times when it's not gamma. We need to run this simulation for a long time, so we haven't gotten to it yet, but you can see like a subcellular gamma here because the synapses are, the bottom is the histogram of synapses. And so when they hit, they form this, what they call intracellular gamma, which is like the membrane potential itself is gamma. We're not talking like the LFP, of course, will be gamma too, but this is the intracellular voltage trace. And yeah, this is a conclusion. So basically the change in input resistance in vivo can largely be attributed to GABAergic synaptic activity. Changing the excitatory synaptic activity didn't affect much. And in the future, we want to know, how does gamma rhythmic inhibition affect spike timing? And further than that, which inputs, coming on the apical tree of the dendrite or basal, that will affect, which cells get selected by gamma. So that's what we want to look at for the future.
Okay, cool. That was a little simpler as in more big picture, and for a visual neuroscientist, I'm interested more of that. That's really interesting. So this high conductance state is mostly being carried by the inhibitory synaptic inputs, and the excitatory inputs have a reduced effect. And if you were to speculate, you're thinking it's just sort of the relative position of the inhibitory synapses, which are closer to the soma, so they can have a bigger influence.
Yeah, I think that's part of it. And it's the reversal potential of GABA too, because it's shunting.
Mm-hmm. Yeah.
We actually set the reversal of GABA to -75 here, and the cell is resting like right at 75. So it's just, it's not really hyperpolarizing or depolarizing. So there's something interesting happening there that we need to dig into. And I can't rule out that it's not active conductances in the dendrites that are contributing to the high conductance state, because we didn't test that, but we will. And I don't think it has as much of an effect. I've played around with it a little bit. And if we turn off the active conductances, it doesn't make that big of a difference compared to turning off the inhibitory synapses.
Okay. And then this inhibition or inhibitory spiking that's synchronized to local gamma rhythms. Is the idea there that the synchrony helps to time spiking precisely so that communication out is more effective? Like along the feed-forward pathway or something?
That is definitely one part is, does gamma organize basically, does it make the spike times less variable? Are they more predictable, like on a schedule, so that they can be read by downstream neurons? That's one part of it. But yeah, there's definitely lots of different things. Like one thing you might wonder is like if a weak synapse comes during when gamma is waning, so there's little inhibition, it might be able to hop through and create an output spike. Whereas if the inhibition was incoherent, that same little excitatory synapse would just get lost. So it's a way of selecting, weaker inputs that would have been ignored in an incoherent state and pushing them through in a gamma state.
Okay, and then how general are these findings, do you think, to cortical layer 5 pyramidal cells? Can I sort of assume this in different cortical areas that have more or less distinct lamination, that have more apical dendrites in layer 1? How general is this, do you think? I don't know if that question even makes sense, but.
No, it does. Yeah, because if the morphology matters, that's a big question, especially because we actually mostly work in the amygdala, so the morphology is totally different there. Yeah, I was working on a simulation right before this. I was going to try to show it's from a layer 4 neuron that the first result I showed with the where the inhibitory synapses changed the conductance, that result was held. As far as the gamma part, I just don't know. We haven't done that, but yeah, I think it'll be important to sample cells from all around the brain. And as computational modelers, it's easy for us to do that. We don't have to, get animals or anything. So
yeah, you have that advantage. If there aren't questions from other panelists or attendees, I have one last kind of another broad general questions. If I remember correctly, these different rhythms, gamma rhythms and beta rhythms, are thought to be implicated differently in sort of propagating along feed-forward and feedback networks. So I wonder if you can, again, speculate largely on why gamma? Does that particular frequency matter relative to the time constant of these neurons, or to the sort of global time constant of the network for whatever it needs to do?
Yeah, I mean, I won't pretend to be an expert on gamma, but yeah, that's my understanding is, the gamma rhythm is pretty close to the synaptic time constant time. So like, gamma is 60 hertz. So we're talking about tens of milliseconds, which is about what you see as in terms of like an AMPA synapse, rise and decay. So yeah, I can't comment on like slower rhythms. I don't really know what those are for, but as far as gamma goes, I think it has something to do with selecting which cells fire.
Okay, cool. All right, well, we're a little bit over time, but that's okay. Thank you, Ben. Thanks, Nathaniel, Daniel, and Pete, and everyone in the audience. Thank you, Satish Nair, for your helpful information in the chat, and to Kevin for running a very smooth tech session. Good luck with your work of NeuroMatch 3.0. I'm Medina Sarvastani. I'm your on-screen host for this session, and we have Kevin Rush, your off-screen host. And just a few quick reminders before we get started. These sessions are ideally interactive, so please put your questions in the Q&A and upvote each other's questions. We'll also try to switch questions from the YouTube stream to here, so you can do things that way too. The chat is also yours, so feel free to put comments or paper references or whatever in the chat. It's casual and it's friendly here. And otherwise, this is a session focused on understanding the influence of sleep on, broadly speaking, cognitive performance. We'll have 3 talks, each a total of 15 minutes, including Q&A. Our first speaker is Thomas Andrein from Monash University, and he'll tell us about wandering minds, sleepy brains, lapses of attention, and local sleep and wakefulness. Thomas, take it away.
Thanks, and thanks for the organizer for doing this amazing 24-hour conference. I realize that it must be quite late for many places around the world, so I'm very thankful if people are watching live or watching this asynchronously. So today I will be talking about mind wandering. So these instances when we are thinking about something else than the task at hand. And I will try to connect these instances of mind wandering, these moments where our attention lapses, with episodes of local sleep, of sleep intrusion that will occur during our wakefulness. So it's a work that was done at Monash University in collaboration with now Tsuchiya Genuines and 2 very bright and dedicated students, Angus Birds and Tegan McKay. But I will start talking about this concept of local sleep. So sleep is classically defined as an all or nothing phenomenon. So either you're awake during the day and it is supposed that all your brain will be awake, or you're asleep and then all your brain will be asleep. This vision of sleep as an all or nothing phenomenon has been tempered a bit recently with the notion that sometimes your brain can actually display in different brain regions patterns of activity that are reminiscent of wakefulness or sleep. Typically during the day, that means that when you start getting tired, your brain regions start sometimes to get tired, and the most tired of this brain region can start display sleep-like activity while the rest of the brain is awake. And a similar phenomenon can happen during the night where part of the brain can wake up in a context of a globally sleeping brain. So how do this modulation of sleep-wake activity at the regional level affect the way we attend to or the external world? So to make this parallel between what happened at the physiological level and on the one hand, behavior, so the way we interact with our environment, but also with phenomenology, so the way we feel, the way we experience, we decided to apply a quite classical paradigm of sustained attention. So in this task, which involved 26 healthy adults, we asked participants to do the classical sustained attention to response task. It's a task where participants are in the digit version, which is a classical version. They are asked to monitor the appearance of digits on the screen that are presented in random order. And it's a classical go, no-go paradigm where participants are asked to press a button for all the digits except the digit number 3. So classical no-go, no-go paradigm, and with lots of goes and a few no-goes. We replicated this SRT in a slightly different version, including this time face stimuli, because we're interested in visual perception for some aspects of this task that I won't talk about today. So participants had to do the same kind of experiment where they had to press a button for all the neutral faces, and they had to withhold their response for smiling faces. So all the participants had to do these 2 versions of the task, which were intertwined in the whole session with 10 minutes blocks and breaks between these blocks. During a block, participants were interrupted from time to time in an approach that's called experience sampling, where they were asked about their subjective experience right before the interruption. And in particular, this interruption were every minute or so, we asked participants to indicate whether they were focusing on the task before being interrupted, whether they were thinking about something else, so this phenomenon of mind wandering. We also included an option to report moments where they had the impression of not thinking about anything or not being able to recall anything. So a phenomenon of mind blanking, as if they will, the interruption will awake themselves from a state of blanking. So the idea with this task is that we're able to collect information about their behavior, their phenomenology, and to make a link with the physiology recorded through EEG. The third thing we did was to examine how much time they declared spending on task, mind wandering, or mind blanking. And we replicated a very, very common finding in the mind wandering literature, especially in the context of easy and undemanding tasks, is that participants reported being on task only half of the time. And as you can see, I mean, all the dots shown on the screen depict a given participant. There is quite a lot of variability between individuals, but on average, they were focusing on the time only 50% of the time, and the rest of the time they spend it either mind wandering 40% of the time or mind blanking. And the proportion of these states was modulated throughout the task. So mind wandering and mind blanking tend to increase block after block, and within a block we also see time on task effects. The state of the state of attention of these participants also impacted the behavior before an interruption. As I told you before, the task was a go-no-go with lots of goes and a few no-goes. And what happens is that participants get carried away, and they very often press a button during the no-go trials. And what we could see here is that when they declared being mind wandering, mind blanking, these instances of no-go errors were more numerous. What was more interesting was looking into the pattern of reaction times, because what we observed is that when people declared being in a state of mind wandering, they had the tendency to respond faster, as if they had become a bit more impulsive. And this could be related to their state of mind wandering. But when they were mind blanking, they had actually the tendency to slow down, as if they were in a state of sluggishness. And this has been interpreted in previous studies as mind wandering reflecting a state of high arousal. So you become a bit jittery, a bit more impulsive with your behavior and your own thoughts, and mind blanking being associated to a state of low arousal. However, when you ask participants about their vigilance, the subjective ratings of vigilance, we found that both mind wandering and mind blanking were associated with a state of low arousal. So it's not as if when they are mind wandering, they are feeling more awake, as if mind wandering was kind of a way to escape the boredom of the task. And these subjective ratings of vigilance were also confirmed by a more objective assessment of vigilance that was collected through the pupil diameter. So when recording the pupil size, which is a good proxy for arousal, we notice also a reduction in both mind wandering and mind blanking compared to on states. So hinting to the fact that both mind wandering and mind blanking are reflective of a lower arousal state. So to dive more into this understanding of how a low arousal state could lead to both mind wandering and mind blanking, we decided to use this concept of local sleep to determine whether both mind wandering and mind blanking could be associated with this sleep intrusion. So these sleep intrusions are defined quite easily. So when you look at scalp EEG, they are defined as low frequency, high amplitude wave that are reminiscent of the kind of slow waves that are observed in non-REM sleep. We know from physiology invasive recordings in animals and humans that this high amplitude, low frequency wave correspond to episodes of neural silencing. And they are called local in the context of wake because they can happen in an isolated way. So you will see globally awake activity, and suddenly you will have such low frequency, high amplitude events, but they can also be local in space. You will see it in one electrode and not the others. How these were detected in practice was by taking the EEG, filtering the signal, detecting the negative peaks of these individual waves, computing the amplitude of each wave, and selecting the top 10% of this wave. So we are interested in certain frequency range and a certain amplitude range. This operation allowed us to select, in a rather arbitrary fashion, of course, these local sleep events. So now it's how this local sleep event looks like in wake, and what will be their correspondent in sleep. You can see that the temporal profile of these local sleep events is quite similar between wake and sleep, with some differences in the wake case. They are smaller in amplitude, of course, and they start with a theta component. But what's important here is this negative deflection that you can see that has been associated with this phenomenon of neuronal silencing. Now that we have detected this local sleep event, we can see whether or not state of mind wandering and mind blanking are associated with more of these local sleep events. And that's what you can show here. So these local sleep events are usually more predominant in central frontal areas. And you can see that in the case of mind wandering and mind blanking, we had more of this local sleep event. They had a higher amplitude and they were steeper, which is typically associated with a bigger local sleep event. Since these events are defined at the level of electrodes, we can use the detection of local sleep event for each electrode and see whether the detection of a local sleep event can be predictive of a given behavioral variable. And this is done at the single trial level. So for each trial, you determine whether or not it was associated with a local sleep event. And when you do that with misses, for example, you can see that misses can be predicted by the occurrence of local sleep event in the back of the brain, in sensory and associative areas, where false alarms were positively predicted by the occurrence of local sleep in the front of the brain, which makes sense given the involvement of frontal cortices in executive control. So what this result will indicate is that local sleep events can not only predict attentional lapses, but could predict the type of attentional lapses depending on where these events occur in the brain. If they impact frontal areas, you will become more impulsive. If they impact visual areas, you will become less able to process sensory information. And this is reflected as well in the reaction times, where local sleep in the back of the brain was predictive of a slowing down of reaction times, while local sleep in the front of the brain was predictive of an increase in reaction times. We could replicate these findings to a certain extent with the phenomenal reports of participants, and we observed that mind wandering compared to on-state was associated with higher amplitude event and steeper events in the front of the brain, while mind blanking was associated with steeper event in the back of the brain. So still indicative of this notion that consequences of local sleep depend on where it happens in the brain. And this result could be replicated using a modeling approach, using drift diffusion modeling. We could extract variables explaining the behavior, and we could again see this frontoparietal divide, where accumulation of evidence for ghost trials was reduced when local sleep was occurring in the back of the brain, and accumulation of evidence for no-go trials were also reduced. So here it's positive, but since it's a negative drift, this actually shows a reduction in the front of the brain. So what's important to notice here is that local sleep in the front and the back of the brain do not only differ by their location, but also by their spatial extent. So local sleep events in the back of the brain tends to involve more brain region, as you can show here. More neighboring electrodes will also show local sleep event. So it could be that the association between local sleep in the back of the brain and mind blanking could be related to their location, but the fact that also it seemed to be a larger event. So as a take-home message, I would like you to remember that when we get sleepy, we can observe this sleep-like activity in the brain, and it can be associated with behavioral lapses. And this local sleep event can predict your subjective experience and your tendency to mind wander. So if you're interested in know more about this, this has been published in a preprint recently, and I will be very, very happy to answer any question you might have.
Thank you, Thomas. That was really interesting and a lot of new concepts for me. So just from personal experience, it seems like, and I'll ask this question quickly and then we can go to the audience. It seems like the relationship between attention and sort of fatigue or local sleep, as I should call it now, is bidirectional. If I'm sort of sleepy, if I focus, then I can get my mind to sharpen and focus on the task. So is there evidence that the same networks are involved here?
So yeah, I mean, sleepiness is obviously something that we can modulate by being motivated, by being engaged in a task to a certain extent. So if you really sleep deprive heavily individuals, they will lose actually their ability to self-regulate their state and behavior. And I think this is actually related to the fact that one of the first regions to be impacted will be the prefrontal cortices. And what typically happens when you get really, really tired is that you don't even realize that your performance start decreasing. So you wouldn't be able to monitor your own performance and say, oh, maybe I should refocus here. So it could be actually, it's actually very interesting to see how different brain region might be differentially impacted by local sleep. And sometimes the very mechanisms that are safeguarding us from fatigue will start to fail us because of this local sleep intrusion.
It's very interesting. Let's go to a question from the audience. Aiton is asking, you showed that the wake slow waves are strongest in the frontal areas. Can you be sure that they're not affected by undetected eye blinks or related other eye artifacts that maybe are confounding the EEG?
Yeah, no, that's an excellent question, because indeed blinks are important to take into consideration here, especially when we're tired, we tend to blink more. So we took a great care about making sure we were not detecting blinks as slow waves. So all these results were, for example, replicated during an ICA that are removing blinks. We are also detecting blinks and check that the timing of the blinks was not associated with the timing of the waves. It is important also to note that the shape of a blink artifact and the shape of this slow wave, the temporal profile will be very, very different. Usually blinks are a positive deflection of our frontal areas. So we're pretty confident that these are not blinks.
Okay, thank you. And we have a couple more questions from YouTube, but we're out of time. Kevin, if you could put the YouTube stream link in the chat, then maybe Thomas can answer the questions there. That would be great.
With pleasure.
Okay, thank you. So let's move on to our next speaker, Pinnan Chen, who's from the University of California at Irvine. And she'll tell us about the vagolytic effect of zolpidem on sleep-dependent memory, the trade-off between working memory and long-term memory. Okay, the stage is yours.
Thank you for the introduction. My name is Pinnan Chen. So a little bit of background. We know that long-term memory and working memory are supported by both independent and some overlapping brain functions or neural system. And both domains change over time. For example, our long-term memory decay over time, and recent studies shows that our working memory can be improved by repeat training. So interestingly, both memory domains benefit from sleep, specifically non-rapid eye movement sleep. So let's take a look of what is sleep. So we have non-rapid eye movement sleep where we have stage 1, stage 2, and slow wave sleep. And we also have this rapid eye movement sleep during which we have vivid dreams. And during stage 2, we typically see this spindles or sigma power that range between 12 to 15 hertz. And during slow wave sleep, we see this slow oscillation between 0.5 to 1 hertz, and that's often coupled with spindles. So how does sleep benefit long-term memory? According to system consolidation, our memory were initially binded together in cortical module by our hippocampus. And over time, after replays, reactivation of memory, the memory traces becomes independent from the hippocampus. And this process is thought to be supported by the sleep oscillation, sleep spindles, which is nested in slow wave that drive the hippocampal memory replay. And many experimental studies have shown that increasing sleep spindles can boost verbal memory consolidation. For example, there's a recent study using electrical brain stimulation, increasing slow waves and spindles, and shows an increase in word pair recall. And there's also another study using Zoppium to increase sleep spindle and shows an improvement in verbal memory. However, on the other hand, how working memory is supported by sleep remain unclear. And there's a strong candidate, slow wave sleep, because slow wave sleep has been linked to synaptic plasticity and cortical reorganization. So it's thought to be an optimal brain state for modification of pre-functioning, such as working memory. However, among those few studies that look at EEG and working memory improvement, some of them suggest a critical role of slow waves or slow oscillation, but some of them show no EEG correlate. So the EEG neural mechanism of how sleep facilitates working memory is still unclear. And interestingly, there's another line of research looking into the autonomic cardiac control. So the neurovisceral integration model suggests that vagal activity, which is measured by heart rate variability, actually reflect the functioning of prefrontal subcortical inhibitory circuit that support our adaptive cognitive success. Many studies have shown that higher heart rate variability during wake is associated with better emotional recognition, better empathy, better theory of mind, and also executive function or working memory. And interestingly, the vagal activity is naturally boosted during non-REM sleep. So in this figure, you can see the high frequency heart rate variability, which is between 0.15 to 0.4 Hertz. You can see that during stage 2 in the blue line and slow wave sleep, the red line, there's an increase in power during non-REM sleep for high frequency HRV, which represent our vagal activity or parasympathetic activity. And on the other hand, the low frequency heart rate variability, which represent a mix of sympathetic and parasympathetic control, seems to be higher during REM. So to see how vagal activity can be critical for working memory improvement, in our previous study, we used a NAP paradigm. So we tested subjects in a operation span task before and after a period of a nap versus wake. We showed that working memory improved across a period of nap compared to waking. And more importantly, we replicated the natural boost of high frequency HRV during non-REM sleep and showed that this HRV can predict the amount of working memory improvement across the nap. And the prediction outperformed other EEG parameters. So the current study, now that we know non-REM sleep provide an optimal state for both long-term memory and working memory improvement. However, we don't know how different sleep features interplay to support both long-term memory and working memory. So an intuitive possibility is that, is there a manipulation that allows us to enhance one feature of non-REM but decrease the other, so we can causally manipulate sleep? Yes, actually it's zolpidem or Ambien. It's a common hypnotic and it's a GABA-A agonist, which has been shown to increase spindles and spindle slow oscillation coupling. And also it's able to decrease our vagal tone. So in this study, we recruited 38 young adults and we use a double-blind within subject design where we administer 10 milligrams of zolpidem or placebo. And we tested the long-term memory using word pair association task. And we tested the working memory using the operation spin task. And we tested these two memories 3 times across a 2-day period. So in day 1 morning, we did the baseline testing. And then in day 1 evening, we tested the second time. And before they go to bed, we give them placebo or zolpidem, and it's counterbalanced. The overnight sleep was recorded with PSG, and in the next morning, subjects were tested for the 3rd time. And to look at how EEG and autonomic activity interact during sleep, we use the effective connectivity. So we first spin the data into 5-minute chunk using 30-second moving windows. And within each chunk, we look at the sigma power as well as the HF-HRV. And then we used effective connectivity to analyze the causal information flow between sigma in the EEG channels and vagal activity in the cardiac channel. This allows us to quantify the information flow from sigma to HF and vice versa. So the result, we show that indeed, zolpidem increased sigma power or spindle activity during non-REM sleep, both stage 2 and slow wave sleep. And interestingly, we show that zolpidem decreased vagal activity during. So the placebos and pink purple lines are zolpidem. And if you look at low frequency, so effect,
I'm sorry, Pinchun, you've cut out a couple times during this slide. Could you take it from the top again?
Oh, okay.
Oh,
sorry,
I think we have a, okay, great, perfect.
Sorry.
No,
okay.
this happens.
Okay, so we shows that zolpidem decrease vagal activity, especially during slow wave sleep, where we see this drop. But if we look at low frequency HRV, there's no drug modulation. So it seems that zolpidem's effect on cardiac control is vagal specific. And then we look at behavior change for overnight and also over the 24 hours period. We found that indeed work pair association performance decreased over time. However, zolpidem, the purple one, seems to be able to rescue some memory or decrease their forgetting. On the other hand, the working memory showed the opposite direction. So the zolpidem decreased the amount of improvement in working memory. So then we correlate the amount of improvement with the vagal activity and found that there's a positive correlation between vagal activity during slow wave sleep and working memory improvement. Whereas there is a negative correlation between vagal activity during stage 2 sleep and the long-term memory improvement. And then for the information flow, we found that zolpidem increased spindle's control over vagal activity, then vice versa. And interestingly, this information flow can predict the difference between long-term memory improvement and working memory improvement. So the more spindle's control over vagal you have, the more long-term memory benefit overnight than the working memory benefit you have. So in summary, zolpidem decreased vagal activity while increased sleep spindles. Zolpidem increased the long-term memory retention, but decreased the working memory improvement. And we show an inverse relation between spindle-dependent long-term memory improvement and vagal-dependent working memory improvement. And zolpidem can modulate the causal information flow between vagal and spindle activity, which can predict the trade-off between working memory and long-term memory chain. And it seems that spindles and vagal activities are antagonistic mechanisms that alternate during non-REM sleep to support either the hippocampal-dependent memory consolidation or the prefrontal-dependent working memory enhancement. And zolpidem can switch the prefrontal dominant processing to the hippocampal dominant memory replay during sleep. And thank you for your attention. I want to thank our postdoc Hami for conducting the effective connectivity analysis and Lauren for conducting most of the experiment, and special thanks to my advisor, Sarah Mennick.
Thanks. That was a very interesting talk. So forgive me if this is a naive question, but so you've shown this pretty tight relationship between vagal activity during different stages of sleep and its influence on the two different types of memory. But I wonder if you can speculate, or if we know the mechanisms through which vagal tone, vagal activity influences working memory.
Right. It's actually vagal activity is not directly influencing our brain function. It's more like a proxy of prefrontal functioning that's easier to measure.
I see. Okay.
Yeah, and the mechanism of how sleep benefit working memory is still unclear. It's not like long-term memory. We have this hippocampal prefrontal dialogue replay. So it seems that from the working memory training literature, it seems that working memory can be enhanced by enhancing the entire brain function, or it's actually slow waves is clear up our trash in the brain, which allow us to have more plasticity or better executive function.
Okay, thank you. We have another question from the audience. Do you see how zolpidem affected spindle slow wave coupling, and how this could differently affect long-term and working memory?
Yeah, it's a great point. We actually didn't look at the coupling in the current study, but in other study from our lab, we showed that zolpidem can increase spindles and slow wave coupling, and that could predict long-term memory. But we haven't found any evidence for the coupling versus working memory yet.
Okay, thank you. If there are no more questions.
I have actually a quick question.
Please,
if there is enough time.
Yeah.
Thanks for your talk. I was wondering, as I'm sure you know, there are two groups of spindle, fast and slow spindles. I was wondering if you looked into this and whether your effects were related to one category or both.
I think the hard cutoff is more within the fast spindle range, but we didn't look at the slow spindle range because I believe most of the study looking into memory consolidation and sleep are about fast spindle, if I remember correctly.
Yeah, it could be a good control actually to show that you don't replicate the effect in the slow spindle range.
Oh, I see what you're saying. Yeah, it seems that zolpidem is shifting all the frequency toward the higher frequency band. So it actually shows decrease in theta power, which is lower than the spindles. And we also see decrease in delta power.
Thanks.
Okay, thank you.
Thank you.
Great. Our next speaker is Elaine Rose Pingle, also from Monash University, and she will tell us more about local sleep in the waking brain, and pairs attention.
Can you hear me? Sorry.
Yep, I can hear you and see your slides. Great.
Yep, so thanks everyone for coming and for giving me the opportunity to talk as well. I'll be talking about local sleep in the waking brain and how this can impair attention. So local sleep is a phenomenon that occurs in both sleep and wake. In wake, it refers to sleep slow waves occurring in some brain regions. So this is time dependent. So it depends on how long a person has been awake for. So the longer a person has been awake for, the more local sleep tends to occur. And it's also task dependent. So the more a person has been using a specific brain region, the more likely that local sleep will occur in this region. So it's been theorized that an increase in local sleep can impair sustained attention. However, past studies have relied on sleep-depriving individuals, so the direct effects of local sleep on sustained attention is difficult to determine. To improve this, we regulated the levels of local sleep using pharmacological means. So we regulated 3 neuromodulators, the first one being noradrenaline using atomoxetine. So noradrenaline is responsible for modulating attention, vigilance, and arousal, and it also inhibits sleep-promoting systems in the brain. An increase in noradrenaline tends to increase wakefulness and improve task performance. So atomoxetine works by blocking the reuptake of noradrenaline, and it's a non-stimulant medication used for ADHD. We then use methylphenidate to increase both noradrenaline and dopamine levels. So dopamine works very closely with noradrenaline and impacts reward processing and motivation. So methylphenidate is a stimulant medication used for ADHD as well, and it works by blocking the reuptake. It tends to improve reaction time in tasks, and it also has an impact on sleep. So the ingestion of methylphenidate is suggested to be early on in the day, as it can cause insomnia. Finally, we use citalopram to increase the levels of serotonin. So serotonin has been theorized to be involved in building up sleep pressure, and it also has inhibitory effects on activation systems. A subdivision of citalopram, escitalopram, was found to reduce activity in regions of the brain responsible for attention and arousal. So citalopram works by blocking the reuptake of serotonin. So the first aim of our study was to establish the effects of neuromodulators on behavior and local sleep. So we implemented a linear mixed effect model to look at the effects of treatment on behavior from a sustained attention task. So we looked at reaction time and missed targets, which in this study was defined as 1 minus targets detected. And we also wanted to see the effects of treatment on local sleep. So for methylphenidate and atomoxetine, because the increased neuromodulators involved in attention, we hypothesized that there would be an improvement in behavior, so that there would be a faster reaction time and a lower amount of misses. For citalopram, we hypothesized that there would be an impairment in behavior because serotonin is involved in inhibiting activation systems. So we hypothesized that there would be an increase in reaction time and an increase in missed targets. Similarly, for local sleep, because methylphenidate and atomoxetine, the increased neuromodulators involved in arousal, we hypothesized that there would be less local sleep detected, and that for citalopram, because serotonin is involved in increasing sleep pressure, that there would be more local sleep detected. So the second aim was to determine whether local sleep mediated the effects of neuromodulators on behavior. So we hypothesized that instead of treatment just having a direct effect on behavior, the local sleep was the middle ground or the mediator between these two variables. So the data that we analyzed was conducted a few years ago, and it was by Professor Mark Belgrove, and it has 2 papers published on it. It comprised of 32 male participants aged 18 to 45, and the design of the study was placebo-controlled. So each participant came to the lab at 4 different time points, and they were randomly administered one of these drugs. So both the participant and the researcher didn't know which drug they were administered. They completed a questionnaire at 3 time points, just before drug administration, before the sustained attention task, and after the sustained attention task. And the sustained attention task they completed was a CTET, or the continuous temporal expectancy task, and that's shown here. Participants were required to monitor this visual stimulus and the duration of the stimuli presentation. So the target stimulus was presented for a longer duration. To indicate that they had detected the stimulus, they had to quickly press a button. So each participant completed 10 blocks of this task, with each block lasting approximately 3 minutes. So before I go into results, I just wanted to reiterate what I looked at. So I looked at reaction time in seconds and also percentage of mean missed targets. I used the linear mixed effect model and used Bonferroni to correct for multiple comparisons. And I also wanted to look at the mean slow wave density per minute for local sleep for each treatment. So these were detected through EEG, and we looked at the delta band for each electrode and looked for the waves with the highest amplitude. We then compared this to the slow waves for placebo, hence the amplitude for the treatments had to exceed the top 10% of slow waves detected for placebo to be classified as local sleep in the study. We corrected for multiple comparisons by adjusting the p-value using false discovery rate. So the results that we found for the first hypothesis is shown here. The bar graphs show the effects of treatment on the behavior variable, which in this case is reaction time in seconds, in comparison to placebo. And the error bars represent the standard error of the means. So in line with the hypothesis, we found that methylphenidate had a lower reaction time compared to placebo, and this was evident across time. Atomoxetine and citalopram had a higher reaction time compared to placebo. Similarly, we found that methylphenidate had a lower amount of mean missed targets, whilst citalopram had a higher amount. So this figure just shows that the local sleep that we detected was very much centralized, and that it also increased across time. So again, in line with the hypotheses, we found that the mean slow wave density that we detected for methylphenidate was lower across time, and atomoxetine and citalopram were higher compared to placebo. And these topographical maps just show which electrodes had a higher or lower amount of local sleep in comparison to placebo. Again, consistent with the hypotheses, we found that methylphenidate had a lower amount of local sleep detected in the frontal regions, and this extended to the central regions and the parieto-occipital regions. For atomoxetine, we found a lower amount of local sleep as well in the frontal region, but we found an increase in local sleep as well in the left temporal region and the right parieto-occipital region. For citalopram, we also found an increase in local sleep in the left temporal region, extending to the central region, the right temporal region, and the right parieto-occipital region. So before I go into the mediation results, I just wanted to reiterate what a mediation tests. It tests whether the effects of treatment on behavior is mediated through a third variable, which in this case is local sleep. So we're trying to see if local sleep explains the causal relationship between these two variables. So we found that the effects of citalopram on local sleep of increasing it significantly mediated the effects of reaction time and also missed targets. So for our hypothesis about methylphenidate, our results were consistent with past studies, such as from Bedard and colleagues who tested the difference between atomoxetine and methylphenidate. Consistent with the results, they also found that methylphenidate had a lower reaction time compared to atomoxetine and had a lower amount of mean missed targets. These perhaps could be due to a decrease in local sleep in regions that regulate this behavior. For atomoxetine, our hypothesis was partly disproved. This could be due to the dosage of atomoxetine that they were given. They might have needed more or less for behavioral improvements to have occurred. Moreover, a past study by Montoya and colleagues found that improvements usually occurred at 6 to 8 weeks after continuous use of atomoxetine. Perhaps due to this study's single-dose cross-sectional design, improvements were not observed in behavior. The increase in reaction time may also be due to local sleep occurring in regions that regulate this behavior. However, despite this, it should be noted that we found a decrease in local sleep as well in the frontal regions. For citalopram, the results obtained are also consistent with findings from a past study by Wingen and colleagues. They found an impairment in vigilance after a single dose of escitalopram. Moreover, another study by Vyazovsky also found that with an increase in sleep pressure, a decrease in task performance was evident. These results also relate to the mediation that we found. So the results that we found for the mediation gets us closer to learning about the underlying mechanisms of these treatments. Past studies such as Bedard and colleagues have only looked at the drug and its direct effects on behavior, but these results could provide us with a better understanding of the mechanisms that could lead to a better prescription of treatments to patients. The effects found by Vyazovsky are consistent with the results found here, that an increase in slow wave mediates reaction time and also misses. However, it should be noted that the citalopram direct path for misses was still significant. This perhaps could be due to the threshold we had set for local sleep. We may have only taken into account specific clusters, and thus we may not have captured all local sleep present. This could also indicate that there are other mechanisms at play that citalopram affects that mediates the effects of misses. So to conclude, this study provides evidence on how these treatments and their effects on neuromodulators have an effect on local sleep. It also showed that an increase in neuromodulators involved in attention and arousal results in a decrease in local sleep. Moreover, increasing serotonin, a neuromodulator involved in increasing sleep pressure, resulted in impairments in behavior, but also an increase in levels of local sleep detected. Thank you for taking the time to listen, and I'm happy to take any questions.
Thank you, Elaine, for a very clear and compelling presentation. I have, again, a broad question because, you know, this idea of local sleep is new to me and I'm caught up on just sort of getting my head around it. So do you consider local sleep a sort of continuum where you a sort of irreversible continuum to where you have these local regions that are in a task-dependent way fatigued, and then you slowly go to global sleep, essentially? Or are they really local events that remain localized?
So I'm not too sure if I'll be answering your question. So do you mind just
speculate? I mean,
yeah, okay. So I do know that local sleep, it occurs when there's fatigue in certain regions. So it's that when that brain region is trying to how do I say this? So when there's okay, I've lost my train of thought. I'm so sorry.
Does it have to do with local sleep? Haha. That's just a pun. Okay, well, here's another question. Okay, so we do have a pretty clear understanding that local sleep increases with fatigue in a unidirectional way. That's probably a better way of asking my question.
Yes, so it's an objective marker of fatigue, yes.
Okay, great. And then do we know, as far as, you know, neuronal mechanisms, do we have any understanding of how we can have local sleep? Because everything, you know, in Neuroscience 101 that I've been taught is that sleep is really a brain-wide phenomena, in part because you have these sort of brainstem nuclei that send neurotransmitters worldwide. So can you speculate on how local sleep can remain local? I mean, this is a huge question, but.
That's a good question, and I'm gonna need to ponder on that.
That seems fair. That seems fair, and we're also actually a few minutes over time. So thank you so much, Elaine, and thank you, Pinnan Chen, and thank you, Thomas, and to everyone on YouTube and here with us on Zoom. Thanks to Kevin for running a smooth tech session, and I hope everyone enjoys the rest of the conference, and good luck with your work.
Thank you.
Bye.
Thanks.
Thank you.